Welcome to English Podcast. In this episode, we will understand the geographical foundations of India through concepts and spatial reasoning.
It's a pleasure to be here. And today, we're doing something a little bit different, I think. We're not looking at, current events or recent history. We're going to try to build a country from the ground up.
Literally from the ground up, we're not even looking at the map as we know it.
Not at all. I mean, when you picture India, you probably see the political map, right? With all the colorful states. You've got Maharashtra, Uttar Pradesh, Tamil Nadu.
Right, the classic school atlas image with the dots for cities and all the lines for roads and railways.
Exactly. And for this deep dive, I want us to just mentally delete all of that. Just wipe it clean.
So no borders, no capitals, just the land itself.
Just the physical geological puzzle. We're looking at a landmass that has been assembled piece by violent piece over the course of about 3,600 million years. We're diving into what's called physiography.
Which is the more academic term for the study of the landforms and features on the surface?
It is, but here's the crucial thing, and the sources we've looked at are really clear on this. You can't understand the surface, the mountains you might hike in, or the soil you grow food in, without understanding what's underneath it all.
The stratigraphy.
Yes. It's like trying to figure out why a skyscraper is so tall by just looking at the paint color. You have to look at the blueprints, at the steel beams, the foundation.
The actual structure. So, given the sheer scale of the Indian subcontinent, how do we even start to break that structure down?
Well, we can simplify this massive complexity into four major physiographic divisions. You can think of them as the four main chapters in India's geological story.
Okay, what are they?
First, we have the ancient foundation. That's the peninsular region, the oldest part. Second, you've got the collision zone, the Himalayas.
Right.
Third, there's what I like to call the Great Fill, the Indo-Gangetic Plains. And finally, number four, you have the edges, the coastal plains and the islands.
The foundation, the collision, the fill, and the edges. I like that. It's a really clear framework. So let's start where it all began, the foundation.
We have to go way back in time for this, deep time. We're talking about 3,600 million years ago. This is what geologists call the basement complex.
The basement, literally the bottom floor.
It is. The peninsular plateau is, without a doubt, the oldest and most stable part of India's structure. This piece of land was originally part of the southern supercontinent, Gondwanaland.
And the key word you used there is stable. What does that mean in geological terms? Is it just not moving?
It means it's a rigid block of the Earth's crust. It's incredibly hard. And most importantly, it has never permanently sunk beneath the ocean since it formed. While other parts of the world were folding and buckling and being reshaped, this huge triangular block has, for the most part, just stood there.
Weathering the storm for billions of years.
Exactly. We call this kind of formation a shield.
A shield. That name itself implies something defensive, something impenetrable.
And in a way it is. It's the solid anchor that everything else is built on or has crashed into. So let's do a thought experiment. Imagine we're standing somewhere in the middle of this shield, say near Hyderabad or Bangalore, and we start digging straight down.
Okay.
We dig past the topsoil, past the weathered rock. What is the fundamental bedrock we eventually hit?
That would be the Archean system.
Correct. And specifically, we hit a type of rock called gneiss. That's spelled Gneiss. These are incredibly ancient crystalline rocks. But there's a particular term the source material uses for them that I find just fascinating, azoic.
Azoic. So if zoo relates to animals and life, then azoic must mean without life.
Precisely, without life. These rocks are so unbelievably old that they formed before any life existed on Earth. There are no fossils, no trace of organic matter, just pure crystalline igneous rocks that have been metamorphosed, that is, twisted and cooked under immense heat and pressure for billions of years.
Well, if you're holding a piece of Archean gneiss, you're literally holding a piece of the planet's lifeless skeleton.
That's a perfect way to describe it. Now, this basement isn't just one uniform slab of gray rock. The research points out that there are actually different flavors of this gneiss, which helps us map out the subcontinent.
Right. The outline mentioned 3 distinct types.
First up, we have the Bengal gneiss. As the name suggests, you find it in West Bengal, but it also stretches down into Odisha and parts of the Carnatic region in the south. In the eastern Ghats, these rocks show up as something called condylites.
Condylites. That sounds like something you'd find on another planet.
It really does, but it's a very real, very ancient series of rocks. Then, if we move more towards the center of the country, we're talking Uttar Pradesh, Madhya Pradesh, Maharashtra, we run into the Bundelkhand gneiss.
And how is that one different? Is it just The location?
It's structurally different. It's a massive granite-like rock. But the key visual clue, if you're a geologist in the field, is that it's characterized by these really distinct coarse veins of quartz that cut right through it. It almost looks like it has scars.
Okay, so scar rock in the center, and what's the third type?
The third is the Nilgiri gneiss, down in the south. And this one is fascinating because it's a specific type of rock called charnockite.
Charnockite. The notes describe this as a blue-gray rock.
Yes. It's a plutonic rock, which means it formed deep, deep underground, and it has this characteristic bluish-gray color. And this is actually the origin of the name Nilgiri Hills.
Wait, you're kidding. The name Nilgiri, the Blue Mountains, it's not just about the haze or the flora, it's the actual color of the rock.
It's a combination, of course, but the geology is the foundation of it.
Yeah.
The charnockite rock gives that entire region its specific physical character, its color palette. So there you have it. That's your basement. The Archean gneiss.
But a basement is just the beginning. You have to build walls on top of it.
Of course. So let's move the clock forward a bit. We're still in the deep past. We're talking roughly 2.5 billion to 1.8 billion years ago. We're now in the era of the Darwar system.
The Darwar system. Now, I made a note here because this is where the research material sort of changes its tone. It goes from being purely academic to suddenly being very economic.
It absolutely does, and for good reason. The Darwar system represents the first sedimentary rocks in India's geological history. So sediment was laid down, and then it got cooked or metamorphosed. And that cooking process is everything, because that's where the money is.
This is the treasure chest of the subcontinent.
It is. The Darwar rocks are, by far, the most metallic, mineral-rich formations in the entire country. If you're looking for high-grade iron ore, gold, manganese, copper, you're looking for Darwar formations.
Okay, so let's map that out. Where do we find these treasure chests?
Well, they don't cover the whole peninsula like a single layer. They appear in these scattered patches or in narrow belts that geologists call geosynclines, usually flanking that older gneiss we just talked about.
And the most famous example has to be the one near Bangalore.
The Champion series, yes.
Mhm.
This is the location of the Kolar gold fields.
Legend.
Absolutely. The Kolar mines are some of the deepest in the world. And the reason they had to dig so deep is because the gold content in those quartz veins was incredibly high for a long time, around 5.5 grams per ton of ore. That immense wealth exists solely because of the specific geological history of that Darwar rock.
And it's not just the gold, as you said. There's also iron.
A huge amount of iron. That's the iron ore series. You find this in places like Singhbum, Mayurbhanj, and Keonjhar.
Which, if you look at a modern map, is basically the heartland of India's heavy industry.
It's no coincidence. The great steel plants, Jamshedpur, Durgapur, Rourkela, they were built there for one reason. The Darwar system put a massive deposit of high-grade iron ore right under their feet 2.5 billion years ago.
I love that. It's such a direct link that geology literally dictates the economy. You can't just decide to build a steel plant anywhere.
Precisely. In this sense, geography is destiny.
All right, let's keep building our layer cake. We've got the basement, we've got the mineral wealth. Now we're moving forward into the Proterozoic era. The notes call these the builders.
That's right, the Kadapa and Vindhyan systems. We can touch on Kadapa briefly. You find it in these deep, crescent-shaped basins in Andhra Pradesh. It's mostly things like sandstone, shale, limestone, useful for local construction, but it's not really the main event here.
The main event is the Vindhyan system.
The Vindhyan system is, you could say, the celebrity rock of India.
Celebrity rock, why is that?
Because it's the face of Indian history and architecture. This system covers a huge basin, stretching all the way from Chittagong in Rajasthan in the west to Sasaram in Bihar in the east. And it provides this incredible, durable, beautiful red sandstone.
So we're talking about the Red Fort in Delhi?
We're talking about the Red Fort. We're talking about the Jama Masjid, the great stupas of Sanchi, Agra Fort, Fatehpur Sikri. When the Mughal emperors or the Mauryan kings wanted to build something that would last for millennia, a statement piece, they weren't just picking up random rocks, they were quarrying the Vindhyan system.
So a huge part of our architectural heritage is basically a display case for Proterozoic sandstone.
It is. And it wasn't just building stone. There's a little bit of sparkle in the Vindhyan story, too. In certain layers, you find conglomerates, which are basically rocks made of older pebbles all cemented together. And in places like the Panna district and the Golconda region, these conglomerates are famous for something else.
Diamonds.
The great Golconda diamonds. The Kohinoor diamond is thought to have come from these formations. So from this one geological system, you get the walls of the palace and the jewels for the crown.
That is an incredible legacy for a rock formation. Okay, we have to make a big jump forward in time now. We're moving out of the ancient building phase and into something more fiery, the Carboniferous period.
We're now in the Gondwana system. This is roughly 350 million years ago. And the whole geological environment changes. We're not talking about deep oceans or metamorphosing rocks now. We're talking about forests and cracks.
Cracks in the earth.
Yes, rift valleys. A series of massive tectonic faults, or cracks, opened up in the supercontinent. The land between these faults subsided, forming long troughs or basins. And at the same time, the Earth was covered in these incredibly dense, lush, swampy forests.
And I can see where this is going. The land cracks.
And the forests fall in. Unimaginable amounts of biomass, trees, ferns, all of it, collapsed into these rift valleys. It was then buried by layers of sediment, compressed and cooked under pressure for millions of years. And that process, carbonization, is what turned all those ancient trees into coal.
And the sources gave a statistic on this that I actually had to read twice.
The 98% figure.
Yes. 98% of all of India's coal reserves come from this one specific geological event in formation.
It's an almost total monopoly. And because the coal formed in these specific rift valleys, it isn't scattered randomly across the peninsula. It's preserved in very specific river basins that basically trace the lines of those ancient cracks.
So the Damodar Valley, the Mahanadi, the Godavari.
And the Warda, exactly. So when you trace the path of the Damodar River today, through the industrial heartland of Karkand and West Bengal, you are essentially following the outline of the ancient rift that now powers India's electricity grid.
That's amazing. When you flip on a light switch in Mumbai, the power is likely coming from burning a Permian-era forest that fell into a hole.
That's the long carbon cycle in action. But speaking of heat, we need to turn the temperature way up now. We're jumping to the Cretaceous period. The dinosaurs are having a very bad day, and a whole lot of lava is on its way out. This is the event that created the Deccan Trap.
Now, the word trap is a bit strange here. The notes mention it's a Swedish word.
That's right, trappa, which means stair or step. And it's a perfect description of the landscape. If you travel through Maharashtra, you'll see these hills that are distinctly flat on top. They look like giant terraces or stairs climbing up the horizon.
And each of those stairs is a different layer of solidified lava.
Basalt, to be specific. From about 146 down to 65 million years ago, the Indian plate was drifting over a volcanic hotspot in the Earth's mantle, and magma just poured out, not from a single cone volcano like Vesuvius, but from huge fissures, massive cracks in the ground. It was a flood of lava.
The scale of this must have been apocalyptic.
It's hard to even comprehend. Today, it covers about 500,000 square kilometers, huge parts of Maharashtra, Gujarat, Madhya Pradesh, but it's the depth that's the real kicker. Around Mumbai, the layers of basalt are 3,000 meters thick.
3 kilometers of solid lava. That would bury most mountain ranges.
It was a world-changing event. But, from that destruction comes creation. Over the next 65 million years, this basalt rock started to weather and break down.
Right.
Basalt is very rich in minerals like iron and magnesium, and when it decays, it's a very specific type of soil. A black, clay-like, sticky soil that is fantastic at retaining moisture.
And that would be Rigar, the famous black cotton soil.
Exactly. So you have to ask the question, why is Maharashtra the heart of India's cotton industry? Why was the textile industry in Gujarat so historically important? It all goes back to that Cretaceous volcanism. No lava flood, no black soil. No black soil, no cotton.
It's a pattern that just keeps repeating. Every major economic region seems to be directly tied to a specific rock layer from millions of years ago.
Yeah.
Okay, so we've built the geological history of the peninsula from the basement up. Now let's look at its current shape, the physiography.
Right, the lay of the land today. We can break this down into two main parts. The central highlands and then the edges, the Ghats.
Let's start in the middle with the Central Highlands, and you have to start with the Aravallis.
The Aravallis are the grand old men of Indian mountains. They're this long chain running from northeast to southwest, basically from Delhi all the way down to Gujarat. They're what we call relict mountains.
Relict, meaning remnants,
Yeah.
leftovers.
Essentially, yes. They are one of the oldest folded mountain ranges in the entire world. In their prime, billions of years ago, they were probably as high and mighty as the Himalayas are today. But all that time, all those monsoons have worn them down to, well, stumps.
Just eroded away.
The highest peak now is Guru Shikhar near Mount Abu, and it stands at 1,722 meters. It's still respectable, but it's just a shadow of its former glory.
And next to them is the Malwa Plateau.
Right. And there's a really interesting spatial puzzle here. The Malwa Plateau is bordered by the Ara Valleys in the west and the Vindhya Mountains in the south, but the entire plateau is tilted towards the north.
So the rivers don't flow south to the nearby Narmada River or west to the sea?
No, counterintuitively they flow north. Rivers like the Chambal and the Betwa flow away from the sea northwards to eventually join the Yamuna River. It creates this very specific drainage pattern that doesn't make sense until you understand the underlying tilt of that whole block of land.
Okay, now let's move to the edges of this big triangular plateau. The Great Divide. The Western Ghats versus the Eastern Ghats. This feels like a classic question from a geography exam.
It is, and for good reason, because the contrast between them is so stark. The Western Ghats, also known as the Sahyadris, are essentially a continuous wall. They were formed when the western edge of the landmass faulted and warped downwards, sinking into what is now the Arabian Sea. So what you're left with is basically a steep cliff edge.
And continuous is the really important word there, isn't it?
It is. They form a solid block, a barrier. The average elevation is quite high, between 900 and 1,600 meters. And because they are a continuous wall, you can't just cross them anywhere. You have to go through specific gaps or passes.
The famous Ghat-Sthal-Ghat, Bor-Ghat, Palka.
Exactly. The Salghat is the route from Mumbai to Nashik. The Borghat connects Mumbai to Pune. Without these few geological doors in the wall, the massive port of Mumbai would be almost completely cut off from the interior of the country.
And the highest peak in the entire peninsula is in the Western Ghats.
It is Anaimudi in Kerala. It stands at 2,695 meters. It's the Everest of southern India.
Okay, so that's the West. A high, continuous wall. Now contrast that with the Eastern Ghats.
The Eastern Ghats are almost the complete opposite. They are discontinuous, meaning they are broken up into separate hills, they are highly eroded, and they are much, much lower, averaging only about 600 meters in height.
So why are they so broken up compared to the Western Ghats?
It was the rivers. The great rivers of the peninsula, the Mahanadi, the Godavari, the Krishna, the Kaveri, they almost all start in the Western Ghats and flow east, across the whole plateau. To get to the Bay of Bengal, they had to carve their way through the Eastern Ghats.
So they literally sliced the mountain range into pieces over millions of years.
They did. They carved out wide, sprawling valleys, which turned a once continuous range into a series of detached hills and mounds. So if the Western Ghats are a wall, the Eastern Ghats are more like a sieve.
And where do these two very different ranges finally meet?
They converge at the Nilgiri Hills, right at the southern tip. It's the geological knot that ties the two edges of the triangle together.
Okay, that gives us a really clear picture of the ancient peninsula. But now we have to address the biggest, most dramatic event in India's recent geological history, the collision, the birth of the Himalayas.
This is where we shift gears completely. We go from the ancient stability of the shield to the youthful, violent turbulence of fold mountains.
And we're talking about plate tectonics.
We are. The Indian plate, which was part of Gondwanaland, broke away and started drifting northwards at a pretty rapid pace, geologically speaking. And between the advancing Indian plate and the stationary Asian plate, there was a vast, shallow body of water called the Tethys Sea.
A sea where the tallest mountains on Earth now stand. It's almost unbelievable.
It is. As the Indian plate rammed into the Asian plate, the floor of the Tethys Sea, which was full of accumulated sediment, got squeezed from both sides. Imagine you have a rug on a polished floor, and you push it against a wall. It has nowhere to go but up. It buckles and folds.
And those folds became the Himalayas.
That sediment became the mountains. It's why you can find marine fossils, seashells, at altitudes of thousands of meters in the Himalayas. It's proof that this land was once an ocean floor. Now, this collision wasn't a single event. It happened in phases.
Right, it wasn't one big crash. Give us the timeline of the uplift.
The first major phase was in the Oligocene epoch. This is what pushed up the Great Himalayas, the highest range. Then came phase 2 in the Miocene, which raised the lesser Himalayas. And the final, most recent phase, in the post-Pliocene, is what raised the Shiwaliks, the foothills.
So it was a stuttering, pulsating collision over millions of years.
A slow-motion car crash that's still happening. And there's a feature here that's absolutely crucial for understanding the shape of modern India. They're called the syntaxial bends.
The outline mentioned, these look like hairpin turns.
That's a great description. If you look at the Himalayas from space, you'll see they form a great arc, curving across the north. But the extreme western and eastern ends, the mountain ranges take these incredibly sharp, abrupt turns to the south.
And where exactly are these bends?
In the west, the bend is near the mountain Nanga Parbat, where the Indus River carves its massive gorge. In the east, the bend is near Namcha Barwa, where the Brahmaputra River makes its dramatic U-turn to enter India.
So why do they bend so sharply?
It goes back to the Indian shield we started with. The hard, rigid northern corners of that ancient shield acted like two pivot points. As the softer sediments of the Tethys Sea were being pushed up, they were forced to wrap around these incredibly resistant corners of the peninsula.
That is a fantastic image. The ancient foundation is physically shaping the curve of the brand new mountains. Okay, let's quickly climb these ranges. The outline breaks them down from north to south.
Let's start at the very top, even north of the main range. This is the Trans-Himalayas. It includes the Karakoram Range with K2, as well as the Ladakh and Zanskar ranges. This area is mostly Tethys sediment.
Okay, then we step south to the Himadri.
The Great Himalayas. This is the spine of the system, a continuous wall of rock with a granite core. This is where the giants live. Mount Everest, Kanchenjunga. The average height here is 6,100 meters.
The average height is over 6 kilometers. That's just mind-blowing.
It's a fortress of ice and rock. Stepping down from there, you have the Lesser Himalayas, also called the Himakal. These are still very rugged, averaging between 3,700 and 4,500 meters.
And this is the part where people live, right?
Yes, this is the human layer. This is where you find the famous hill stations, Shimla, Mussoorie, Darjeeling, and the beautiful fertile valleys like the Kashmir Valley and the Kathmandu Valley.
And finally, the lowest step, the foothills.
The Shawaliks. These are the youngest and lowest of the ranges. In many places, they're not even solid rock yet. They're essentially made of unconsolidated sediments, gravel, mud, boulders that were washed down by the rivers from the still rising mountains above.
And it's between the Shawaliks and the Lesser Himalayas that you get these features called duns.
Exactly. These are long, longitudinal valleys that are trapped between the two ranges. They're often very flat and fertile. Dehradun is the most famous example.
I want to zoom in on one detail you mentioned earlier before we move on. The Karawas in the Kashmir Valley, it feels like a very specific but important local detail.
It's a beautiful story. During the Pleistocene Ice Age, the natural outlet of the Kashmir Valley was blocked by the rising Pir Panjal Range. This effectively turned the entire valley into a massive lake.
So the whole Vale of Kashmir was underwater.
The entire valley, yes. And for thousands of years, sediments from the surrounding glaciers and rivers settled at the bottom of this lake fine sand, silt, clay, pollen. Eventually, the natural dam broke and the water drained away, leaving behind these thick, flat, terrace-like deposits we call karawas.
And why are they so important today?
Saffron. The unique soil chemistry of these ancient lake beds, the karawas, is what allows Kashmir to cultivate some of the highest quality saffron in the world.
Once again, the ancient geology dictates the modern agriculture.
It always comes back to the rocks.
All right. We have the ancient peninsula, we have the towering Himalayas, now we need to fill the gap between them, the Great Fill, the Indo-Gangetic Plains.
This is the newest major physiographic unit of India. Geologically, it's just a baby.
So how did it form?
Well, think about the geometry. You have the rigid peninsular block to the south, refusing to move. You have the Himalayas rising rapidly in the north. This process created a huge depression, a trench running between them. Geologists call it a four deep.
A giant ditch hundreds of kilometers wide running across the top of the subcontinent.
Exactly. And for the last couple of million years, the great rivers, the Indus, the Ganga, and the Brahmaputra have been flowing down from the mountains and dumping trillions of tons of sediment into that ditch, filling it up.
How deep is all that sediment?
It's immense. In some places, the depth of the alluvium is up to 2,000 meters. So if you're standing in the plains of Uttar Pradesh, you are standing on 2 kilometers of river mud. That's why it's so incredibly flat and fertile. That's why it's India's breadbasket.
And finally, to complete the picture, we just need to look at the very edges. The coastal plains, west coast versus east coast.
And again, just like the Ghats, they are very different because of the way the peninsula is tilted. The west coast, the Konkan and Malabar coasts, is a submerged coastline. The land has dipped down into the sea. This creates lots of natural harbors, creeks, and estuaries, and of course the famous backwaters, or kayals, of Kerala.
And the east coast.
The east coast is an emergent coastline. It's wider with a more gentle slope. And because all those big rivers we mentioned dump their sediment here, you get these huge sprawling deltas. The deltas of the Mahanadi, Godavari, Krishna, and Kaveri are constantly extending the land outwards into the Bay of Bengal.
So to bring it all together, we have this incredible layer cake. The ancient shield at the bottom, the mineral-rich Darwar layers, the coal-filled Gondwana cracks, the volcanic Deccan steppes, the collision-borne Himalayas, and finally, the river-filled plains.
That's the structure of India in a nutshell.
So as we wrap this up, I have to ask the big so what question. Why does this deep history matter to someone living in India today?
Because you simply cannot separate your daily life from the rock you are standing on. This geology dictates where our energy comes from. That's the Gondwana coal. It dictates where our steel is made, from the Darwar iron. It dictates where we grow our food, in the plains. It even dictates the cotton in the shirt you might be wearing, thanks to the Deccan lava. We're living inside a house built by these ancient geological events.
It really puts everything into a much grander perspective. And one final thought to leave everyone with. Is the construction of this house finished?
Not even close. And that's maybe the most provocative idea of all. The Indian plate is still moving north at a rate of a few centimeters a year. The Himalayas are still rising. The earthquakes that we feel in that region are not an aberration. They are the growing pains of a subcontinent that is still being built.
So we are all living on a moving raft.
We are indeed. It's a work in progress.
On that fascinating and slightly unsettling note, thank you for guiding us through this deep dive into the foundations of India.
My pleasure. Thank you.
At this point, it is important to understand the geographical logic behind this pattern.
It really is. Because, when most of us look at a map of India, or any massive landmass for that matter, we just see these blue squiggly lines.
And we think water flows downhill.
Right. Simple as that. But if you actually stop and look at the geometry, the arrangement of how these rivers are laid out, you realize you're not looking at random squiggles.
You're looking at something else.
You're looking at a map of the Earth's hidden skeleton.
Hidden skeleton sounds a bit dramatic for just dirt and water.
Yeah.
Are you saying the river isn't just reacting to the slope of the land?
Oh, slope is definitely part of it, but it's more like a three-way brawl between gravity, the resistance of the rock underneath, and the whole tectonic history of the land.
And the river is just caught in the middle.
The river is the victim, exactly. It's a victim of the geology it flows over. And that struggle, that conflict, it creates very specific, almost mathematical shapes. We call them drainage patterns.
I saw those in the notes. Dendritic, trellis, radial. It sounds like geometry class mixed with, I don't know, gardening.
That is actually a great way to visualize it. I mean, let's take the dendritic pattern. You see this all over the Indo-Gangetic plains.
The northern plains.
The northern plains. And the word comes from the Greek dendron, which means tree.
So it literally looks like a tree branching out.
Precisely. Like a root system, really. You have your main river, the trunk, and then all these tributaries joining it at, these acute angles. They just branch and branch and branch.
And what causes that specific shape?
It happens because that skeleton underneath is completely uniform. In the northern plains, the ground is it's soft. It's massive layers of alluvium, just mud and sand deposited over millions of years.
So there are no hard rocks to get in the way.
Nothing at all. So the water can flow anywhere it wants. It moves organically, just following the path of least resistance.
Okay, so a dendritic pattern means the river has total freedom. It goes where it pleases because the ground is soft.
Exactly. Now, contrast that with the trellis pattern. If you look at a map of the Singphum region down in the Chuknagpur Plateau, suddenly that organic tree shape is completely gone.
It's rigid.
It's like the rivers have been put in a straitjacket.
Yeah, I'm looking at the diagram for it here. It almost looks like a grid. You have these tributaries flowing parallel to each other for miles, and then boom, a sharp 90-degree turn into the main river. Nature doesn't usually do right angles. What's forcing that?
Hard rock. In that region, you have these ancient folded mountains where you've got these long parallel bands of soft rock and hard rock.
Alternating.
Alternating, yeah. The river can't cut through the hard stuff. It's literally trapped in the lane of soft rock. So it has to flow straight until it finds a weak point, a little crack in that hard wall, and then it cuts through sharply to join the main stream.
That makes so much sense. It's like walking down the aisles of a supermarket.
How so?
Well, you can't just walk through the shelves. You have to go all the way to the end of the aisle to make that turn.
That is a perfect analogy. The geology is the shelving unit.
Okay. And the last one was radial.
Radial, yeah. This one is a bit simpler. Just imagine a bicycle wheel lying flat on the ground. The hub In the middle is the highest point.
The summit.
The summit, yes.
Mhm.
And in India, the classic example of this is the Amarkantak Plateau. It's basically a giant dome,
So the rivers flow outwards from the center?
like spokes on that wheel. You
Yeah.
have the Narmada River flowing off it to the west, the Sun River flowing to the north, and the Mahanadi system flowing away to the east. They all start from that same high point and just radiate outwards.
Okay, I buy the geometry. The land shapes the river. But there was one concept in the research that I had to read it 3 times. Antecedent drainage.
Ah, yes. It's a tricky one.
The notes claim that some of these Himalayan rivers, like the Indus and the Brahmaputra, are older than the mountains they flow through.
It is deeply counterintuitive, isn't it?
It feels physically impossible. I mean, if a river flows downhill, the hill has to be there first, right? You can't slide down a slide that hasn't been built yet.
Normally, you'd be absolutely right. That kind of river is called a consequent river. It follows the consequence of the slope. But the Himalayas are a very special case.
Yeah.
We have to remember the Himalayas weren't always there. Before the Indian plate smashed into the Eurasian plate, there was a Tibetan plateau, and rivers were already flowing south from it into the old Tethys Sea.
Yeah.
The Indus, the Satluj, the Brahmaputra, they already existed.
Okay, so they were there first, but then the ground starts rising. I mean, you had these massive tectonic plates colliding. Shouldn't that have just blocked the river, dammed it up, and created a huge lake?
It would have if the uplift happened overnight in some huge cataclysm. But mountains rise incredibly slowly. We're talking millimeters a year.
Right.
So think of it like this. Imagine you're pushing a log of wood very, very slowly into a spinning table saw. The saw itself doesn't move up or down. It stays level. But as you push the wood up, the saw just keeps cutting a deeper and deeper groove into it.
So the river is the saw blade.
The river is the saw. As the Himalayas rose up, the Indus and the Satluj just kept cutting downward, pure vertical erosion. They were eroding the rock at basically the same rate that the rock was being lifted.
Which is why they flow through those incredible gorges.
That is exactly why. When you look at the Satluj River at Shipgila, it's flowing through this impossibly deep, steep-walled gorge. It didn't find a path over the mountain range grew up around it, and the river just sliced right through.
That is just terrifyingly persistent. It's like geological stubbornness.
It is the very definition of power. And speaking of power and violence, we have to talk about river capture.
This sounded like something out of a crime novel in the notes. You see terms like beheading rivers and river piracy.
It is essentially piracy.
Yeah.
Let's look at the map of the Kosi River system, specifically one of its tributaries called the Arun, which flows in Nepal. Now, usually when a tributary joins a main river, it merges gently, right? It points downstream.
Like a highway on-ramp. You merge with the flow of traffic.
Exactly. But if you look at the Arun, it joins the Kosi pointing upstream. It makes this really sharp, hook-like turn just before it joins. We call that a barbed pattern.
Like a fishhook.
Precisely like a fishhook. And that hook is a scar. It's a clue. It tells us that the Arun didn't originally flow into the Kosi at all.
So it was flowing somewhere else entirely?
Probably north or east, maybe into the Sangpo.
Yeah.
But the Kosi is a very, very aggressive river. It erodes its valley backwards, that's called headward erosion, until it literally cut into the channel of the Arun.
It breached the wall between them.
It breached the wall and stole all the water. Because the Kosi had a much steeper slope, gravity just pulled all of the Arun's water into the Kosi's channel. It effectively beheaded the original path of the Arun River.
And the hook shape is the evidence of that hijacking.
It's the moment the hijacking happened, frozen in the landscape.
That brings a whole new meaning to hostile takeover. But if we're talking about massive changes in the planet's plumbing, we have to address the biggest theory in this whole stack of research, the Indo-Brahma River.
Ah, yes. The grand unified theory of Indian hydrology.
It sounds a bit like Atlantis to me. The idea that the Indus, the Ganga, and the Brahmaputra, which today flow in completely different directions, were once all part of a single, massive super river.
It sounds wild, I know. But the geological evidence, which was primarily championed by geologists like Pascoe and Pilgrim, is actually quite compelling.
So what's the theory?
The theory is that back in the Miocene period, there was this continuous depression that ran parallel to the rising mountains. And a single river, which they named the Indo-Brahma, flowed all the way from Assam in the east, across the top of the subcontinent, to Punjab in the west.
And emptied where?
It eventually emptied into the Gulf of Sindh, one river running the entire width of northern India.
Incredible. So what killed it? The notes talk about the Great Dismemberment.
The land moved again. Two major tectonic events happened in the Pleistocene, which is, geologically speaking, much more recent. First, the western Himalayas rose up, which really disturbed the flow. But the real knockout punch was the uplift of what we call the Delhi Ridge.
The same ridge that runs through Delhi today.
That's the one. It's actually a northern extension of the much more ancient Arrow Valley Mountains. During this period of upheaval, that whole ridge was lifted up, creating the Potwar Plateau.
Okay, so what did that do to the river?
Well, think of it like pushing up the center of a long water trough. The water can't flow across that hump anymore. It has to pick a side.
It created a watershed.
A water divide, exactly. The flow to the west of that divide became the Indus system we know today. The flow to the east actually reversed its direction and became the Ganga system. And the Brahmaputra was left isolated way out in the east.
So the trio was born from the corpse of this giant.
That's a great way to put it.
That actually explains the map anomaly I've always wondered about. The Yamuna River. It flows right next to the Delhi Ridge, very, very close to the Indus Basin, but then it takes that sharp turn east to join the Ganga near Allahabad.
That turn is the memory of that uplift. The Yamuna is essentially sliding down the eastern face of that new divide.
So, now that we have these three distinct systems, the western, central, and eastern wings, let's look at their personalities, because they really are like characters. Let's start with the west, the Indus system.
The Indus itself is massive, of course,
Yeah.
but I find its tributaries are even more interesting. You take the Jhelum, for instance, the river of Kashmir. It has a very, very strange behavior.
Strange how?
Well, rule number one of a mountain river is that it's fast, it's turbulent, and it cuts a deep V-shaped valley. They don't meander.
Right, meandering, that lazy looping back and forth. That's what old rivers do when they get to the flat plains.
Exactly. But the Jhelum meanders deeply, while it's still high up in the Himalayas, flowing through the Vale of Kashmir.
So is it just taking a break?
In a way, yes. It's a ghost of geology past. The Kashmir Valley wasn't always a valley. It was a massive lake millions of years ago. The sediments there, which called khairwas, are basically flat lake-bottom deposits.
I see.
So even though the Jhelum is high up in the mountains, for that stretch, it's flowing across a perfectly flat ancient lake bed. It thinks it's in the plains, so it meanders.
Until it hits the edge of the old lake?
Right. Once it hits the gorge at Baramulla, the vacation is over. It drops down and becomes a raging Himalayan river again. It's a fascinating, localized anomaly.
And then, of course, you have the Chenab, the largest tributary, and the Satluj, which, as we said, is the buzzsaw that just cuts right through the range. But I want to move to the center, to the Ganga system. This is the absolute heartbeat of North India.
The central artery, for sure.
We know its technical origin is at Prayag, where the Alaknanda and Bhagirathi rivers meet. But the sources spend a lot of time on a river that, well, isn't there anymore.
That's the Saraswati.
The Lost River, the Ghaggar-Hakra system.
For a long time, this was considered purely mythological, wasn't it?
It was. But modern satellite imagery and geological surveys have completely changed that conversation. We can now clearly see the dry bed of a massive paleo channel running all the way through Haryana, Rajasthan, and into Pakistan. So it was real. What happened to it? Did it just dry up?
It didn't just dry up, it was starved to death. And this goes right back to river capture.
Yeah.
The evidence suggests that in ancient times, the Yamuna River didn't flow east into the Ganga.
No. Where did it go?
It flowed west. It was the main tributary feeding the Saraswati system. And there's even evidence that the Satluj might have flowed into it as well.
So the Saraswati wasn't just some small stream, it was a mega river fed by Himalayan glacial melt.
Absolutely. But then tectonic tilting happened. Just a subtle shift in the Earth's crust caused the Yamuna to be captured by the Ganga system. It changed its course. Then the Satluj was captured by the Indus system.
And the Saraswati was left high and dry.
It was left with no glacial water source, only rain. And when the climate in that region became drier, the river just died.
It died.
That is tragic. It's like a bank run. All the major depositors pulled their water out at once.
And the result of that is the Thar Desert. The eastern margin of that desert is defined by where that great river used to be. Wow. Okay, so if the Saraswati is the river that died, then the Kosi is the river that kills. The notes repeatedly call it the sorrow of Bihar. I saw a stat here that I need you to explain because it seems impossible. It says in the last 200 years, the Kosi has shifted its course 160 kilometers westward.
It's staggering, isn't it?
160 kilometers isn't a shift, that's a migration. That's like the river moving from one city to a completely different one. Why is it moving so much?
It's a victim of its own energy. The Kosi drains a massive, incredibly high section of the Himalayas, including Everest and Kanchenjunga. So it comes down with immense speed, carrying a colossal amount of sediment, sand, silt, rocks,
The load, as they call it.
a huge load. But the moment it hits the perfectly flat plains of Bihar, it loses all its speed. It can't carry that heavy load
So
anymore.
just dumps it.
It dumps it. It deposits millions and millions of tons of sand and silt right in its own channel.
It blocks itself.
Exactly. It chokes its own flow. The riverbed itself rises up because of all the sediment. Eventually, the water level in the channel gets higher than the surrounding land.
Which is a disaster waiting to happen.
A total disaster. During the next big flood, it just bursts its banks, abandons that old clogged channel entirely, and cuts a completely new path through lower ground.
And if there happens to be a village or a district in that lower ground,
Then the river flows right through it. That is why it is the sorrow. It's wildly unpredictable. Engineering against the Kosi is one of the hardest challenges in all of Indian hydrology.
let's follow that theme of sediment and unpredictability and move to the east. The Brahmaputra.
The giant of the East.
It enters India through that famous hairpin bend at Namcha Barwa, that incredibly deep gorge. But once it gets into the Assam Valley, it doesn't look like a normal river on the map. It looks more like a braid of hair.
That's the perfect description. It's a braided river. This happens when you have a combination of very high water discharge and a massive amount of sediment.
More than the Kosi.
Even more. The Brahmaputra carries so much silt that it constantly creates these huge sandbars and islands right in the middle of its own stream. So the water has to split and rejoin, flowing around all these obstacles.
And this process creates river islands. The big one everyone's heard of is Majuli.
Majuli is both fascinating and frightening. It's the largest inhabited river island in the world. It has its own distinct culture, a unique ecosystem. But the river that created it is now eating it.
The notes mention that it's shrinking.
Drastically. It used to be around 1,200 square kilometers. The most recent surveys put it closer to 930, and it's still shrinking.
How?
The Brahmaputra is just eroding the banks, slicing off huge chunks of the island every single monsoon. It's a constant race between the river depositing new soil and the river taking old soil away. And right now, erosion is winning.
It really feels like the big theme of these Himalayan rivers is just instability. They're young, they're violent, and they're constantly changing the landscape.
Which is a perfect setup for the contrast. Because if you head south, past the Vindhya Mountains, you enter a completely different world. The peninsula rivers.
The Old Guard.
The Vedrans. Geologically, the Deccan Plateau is one of the most ancient and stable blocks of land on Earth. It hasn't been underwater for hundreds of millions of years. It's just a stable block of very hard rock.
So the rivers there are different.
Completely. The Godavari, the Krishna, the Kaveri, they aren't digging deep gorges anymore. They are, to use the geological term, senile.
I love that geologists use the word senile. It implies they're just sort of pottering about in the garden, their work is done.
It basically means they've reached equilibrium. Their valleys are broad and shallow. They have what we call graded profiles, which means they flow smoothly without many waterfalls or rapids, except for a few spots where the plateau drops.
But the notes highlight two rebels in this retirement home, the Narmada and the Tapi.
Ah, yes. The west-flowing exceptions. This is the classic geography quiz question. If the general slope of the Deccan Plateau is to the east, which is why the Godavari and Krishna flow east, why do the Narmada and Tapi flow west?
They're defying the slope.
They're ignoring the slope completely. They're following the cracks in the foundation. These two rivers flow through what are called rift valleys.
Explain a rift valley for us.
Okay, imagine you take a block of cheese and you pull it apart from both ends. The middle section will drop down between two cracks. That trench is a rift valley.
I see.
The Narmada flows in a geological fault between the Vindhya and Satpura mountain ranges. It's not flowing in a valley that it carved itself. It's flowing in a tectonic trench that was opened up for it.
So it's confined.
Tightly confined.
Wow.
Which is why, if you look at a map, the Narmada has almost no major tributaries. It's just a straight, narrow shot to the Arabian Sea.
And this confinement also explains why they don't form deltas at their mouths.
Exactly. To build a delta, that big fan shape of new land at the river mouth, you need calm, shallow water and a lot of sediment to deposit. The Narmada and Tapi hit the Arabian Sea at a very steep angle. The coast is deep there, and the tides are strong.
So the river dumps its dirt, and the ocean just flushes it all away.
Pretty much. They form estuaries, not deltas. It's a funnel-shaped mouth where fresh water meets salt water, but no new land is being built up.
Now, compare that to the East Coast. The Godavari, the Mahanadi, the Kaveri.
Totally different story. They flow gently into the Bay of Bengal, which is a very wide, shallow continental shelf. The sea is calm. So these rivers have had millions of years to build these massive, sprawling deltas.
And that's where the agriculture is.
The Godavari Delta is one of the great rice bowls of India, precisely because of all that fertile new land the river keeps providing.
The Kaveri is interesting for another reason, too. The notes call it the only truly perennial river in the south.
That's a crucial distinction. Most of the peninsula rivers are entirely monsoon dependent. If the rain fails, the river becomes a trickle. But the Kaveri cheats the system.
How does a river cheat?
By its geography. Its upper catchment area, up in Karnataka, gets all its rain from the southwest monsoon in the summer, from June to September.
Right.
But its lower basin, down in Tamil Nadu, gets its rain from the retreating northeast monsoon in the winter.
So it gets a double dose of rain every year.
It gets refilled twice a year. And that makes it uniquely reliable for agriculture in a region that is otherwise quite dry for much of the year.
Okay, let's zoom out a bit. We've talked about the veins, the rivers. Let's talk about the physical container itself, the mountains, specifically the gateways. Because when I look at photos of the Himalayas, it just looks like a solid, impenetrable wall. But humans have been walking through it for thousands of years.
Through the las. In Tibetan, la means pass. These are the crucial notches in the blade of the mountains. Without them, civilization in India would have been almost completely isolated.
The strategic importance of these passes is just wild. Take Zojila, for instance.
It is absolutely vital. It's the pass that connects the Kashmir Valley to Ladakh to Kargil and Leh. Think about that terrain. Without Zojila, Ladakh is basically an island in the sky, cut off from the rest of India.
So keeping that pass open is a matter of national security.
Literally a matter of national sovereignty.
And then there's Nathula over in Sikkim.
That's the historic trade route. It's a spur of the old Silk Road that connected India to Tibet and China. It was closed for 44 years after the 1962 war.
And it only reopened recently.
In 2006, yeah, it's incredibly high, over 4,300 meters. But it's a lifeline for trade.
And for sheer height, there's Kardungla.
Kardungla is the gateway to the Shiak and Nubra valleys. And crucially, it's the main supply route to the Siachen Glacier.
Which brings us to the ice, the third pole, as it's sometimes called.
And that's not an exaggeration. Outside of the North and South poles, the Himalayan region holds the most ice on Earth. The Siachen Glacier alone is 75 kilometers long.
That's a river of solid ice.
It is. And the Gangotri Glacier, which is the source of the Ganga, is about 26 kilometers long. These aren't just scenic whitecaps on the mountains. They are the savings account of India's water supply.
I like that analogy. The monsoon is the checking account. You get your cash in, you spend it. The glacier is the long-term savings.
That's a perfect way to describe it. When the monsoon fails or is weak, it's the steady meltwater from these glaciers that keeps the northern rivers flowing through the dry season. But here's the scary part.
We're spending the savings.
We are spending the savings. That data is alarming. Something like 75% of Himalayan glaciers are retreating. Gangotri is shrinking year on year. If that savings account runs dry, those perennial rivers, the Ganga, the Yamuna, they become seasonal.
They become like the peninsular rivers.
Exactly. And that changes absolutely everything for agriculture and for human survival in the plains.
And speaking of the plains, let's move down from the ice to the dirt. The Great Plains of North India. This is where the majority of the population of the subcontinent actually lives.
The Great Deposition Zone.
I want to understand the physics of this. How do you get a perfectly flat plain that's 2,400 kilometers long? The notes mention something called a four-deep.
Right. Let's use a mental model here.
Mm-hmm.
Imagine a very heavy person, that's the Himalayas, sitting on the very edge of a waterbed. What happens to the mattress right next to them?
It dips down, it creates a trough.
That dip is the four-deep. When the Indian plate pushed under the Eurasian plate to lift the mountains, the crust in front of the mountains buckled downward, creating this massive trough, a synclinal depression.
And the rivers just filled it in over time.
For millions and millions of years, the rivers have been eroding the mountains and dumping all that dust and rock and sand into that trough. The amount of fill, it's hard to comprehend. The alluvium, the river dirt, is between 1,300 to 1,400 meters deep.
Wait, you're saying we're walking on 1.5 kilometers of dirt?
You are walking on 1.5 kilometers of debris that used to be the top of the Himalayas. That is what the Great Plains are.
And it's not just one uniform stretch of mud, is it? There's a texture to it. If I were to walk from the base of the Himalayas south towards the river, I'd pass through different zones.
Distinct bands, yes. First, right at the foot of the mountains, you hit the Babar. This is a belt of rocks, boulders, and large pebbles.
The heavy stuff the river dropped first as soon as it lost speed.
Precisely. And here's the magic trick. The rivers disappear here. The ground is so porous, it's just a pile of loose rocks, that the water from the smaller streams just sinks straight down and flows underground.
So you could be standing on a completely dry riverbed, but a torrent is flowing right beneath your feet.
Exactly. Then, a few kilometers to the south, you hit the Tarai Belt, and this is where all that water reemerges.
The swamp.
Historically, yes. The Tarai is where the water table breaks the surface. It used to be this thick, marshy jungle famous for tigers and infamous for malaria.
But it's been reclaimed now.
Largely, yes. After partition and the population boom, huge areas were drained. Now the Tarai is prime farmland, perfect for water-hungry crops like sugarcane and rice.
And then, after the Tarai, we get to the main plains. The notes make a big distinction between Bangar and Kedar.
This is a distinction every farmer in North India knows by heart. Bangar is the old alluvium. It sits on the higher ground, on the terraces, away from the river. It's safe from floods.
Okay.
It's also full of these little calcium nodules they call kankar.
In Kedar.
Kedar is the gold. It's the new alluvium, right down in the floodplain, next to the riverbanks. Every single year, the river floods and lays down a fresh, new sheet of fertile silt. It renews itself.
So that's the most intensive farming land in the country.
Absolutely. The geography literally dictates the crop cycle and the value of the land.
Okay, let's push all the way to the edges of the subcontinent, the coasts. You mentioned earlier that the west and east coasts are fundamentally different. Looking at the map, the west coast looks much more jagged, more indented.
That's because the west coast is a submerged coast. Geologically, the land here has subsided. It has sunk down.
And what does that do to the shoreline?
It brings the deep sea right up to the land. And that's why all the best natural harbors in India are on the west coast. Mumbai, Cochin, Marmagao. You don't need to do a lot of dredging because the water is naturally deep right up to the coast.
And the east coast is the opposite.
It's an immersion coast. It's rising, or more accurately, the land is building out into the sea because of those massive deltas we talked about. The continental shelf there is very wide and very shallow.
Right.
If you stand on the beach in Chennai or Odisha, the water stays shallow for a long, long way out.
Which is bad for big ships, but good for beaches.
Bad for natural ports, for sure. To build a major port on the East Coast, you generally have to dig a deep channel for the ships.
And finally, the islands. We have two main groups, the Andaman and Nicobar Islands and Lakshadweep. And they couldn't be more different in their origin.
They are worlds apart. The Andamans are purely tectonic. They are actually the submerged peaks of a long mountain range that connects Myanmar's Arakan Yomer range all the way down to Sumatra.
So they're rugged, hilly islands.
Very rugged, hilly, and covered in dense rainforest. And they're volcanic, too.
Right, Barren Island.
Barren Island is India's only active volcano. It smoked as recently as 2017.
Whereas Lakshadweep.
Lakshadweep is a coral paradise. These are atolls. They sit on a submarine ridge, but the islands themselves are made entirely of the skeletons of coral, piling up over thousands of years. They are flat, sandy, and barely a few meters above sea level.
Which makes them incredibly vulnerable to climate change and sea level rise.
Absolutely. If the sea rises by even 1 meter, Lakshadweep is in serious, serious trouble. The Andamans have hills you can retreat to. Lakshadweep does not.
We've covered a lot of ground, but we can't ignore the engine that is driving all of this change, tectonics, the whole reason we have the Himalayas and, of course, earthquakes.
And that engine is still running. The Indian plate is still shoving northward into Asia at a rate of about 5 centimeters a year. That stress has to go somewhere.
And it's released as earthquakes.
Seismic zone V. The entire Himalayan belt, from Kashmir all the way to the northeast, plus the Rann of Kutch in Gujarat, is in the highest possible danger zone. We've seen the devastation with the Bhuj earthquake in 2001 and the Kangra quake back in 1905. The tension just builds up like a stretched rubber band and eventually it snaps.
And what about volcanoes? You mentioned Barren Island, but the notes talk about something called the Deccan Traps. That sounds like a horror movie title.
It would have been a horror movie for the dinosaurs. About 66 million years ago, right around the time the dinosaurs went extinct, the Indian Peninsula basically cracked open.
Not a single volcano, but a crack in the earth.
Fissure eruptions.
Uh-huh.
We're not talking about a single mountain blowing its top. We're talking about lava flooding out of these long cracks in the ground, just like water, and covering an area of 500,000 square kilometers.
500,000 square kilometers of lava.
Layer upon layer of it. In some places, the stack of basalt lava is 2 kilometers thick. It would have darkened the sky for years, maybe
And when
decades.
that all cooled down, it became what?
The famous black soil of the Deccan, the Rieger soil. It is incredibly fertile and moisture retentive. That ancient apocalypse is the reason that Maharashtra and Gujarat are perfect for growing cotton today.
That is a perfect example of what we've been talking about this whole time. The violence of the geological past, creating the economy of the present.
That is the core takeaway of all of this.
So let's try and synthesize this. Let's unpack that logic chain for everyone listening, because we started by saying this isn't just a map of random squiggle.
Right. Think of it as a domino effect. First, the tectonic collision creates the Himalayas and at the same time pushes down the four deep in front of them.
Domino 1.
Domino 2. The high mountains block the wind to create the monsoon climate, and they trap the snow to create the glaciers.
Okay.
Domino 3. The glaciers and the rain feed the rivers, some of which are ancient and cut through the rising mountains, the antecedent ones, and some are new and just flow down them.
Right, the conveyor belts.
Exactly, which is domino 4. The rivers act as conveyor belts, eroding the mountains and dumping all that sediment into the 4 deep
To fill the trough.
to fill the trough. And that is the final domino, number 5. That sediment creates the Great Plains, some of the flattest, most fertile, and most densely populated farmland on Earth.
It's a machine that builds India.
It's a machine that builds the stage for civilization. You simply cannot understand why our strategic borders are where they are in the mountain passes, or why our food grows where it does in the plains, or where our future water wars will be fought, without seeing this underlying skeleton.
And here's where it gets really fascinating for me. We look at a map today and we think, this is it. This is the permanent shape of India. But this deep dive has shown us that the map is just a snapshot of a moving object.
A very blurry snapshot at that.
The Saraswati was a mega river, and now it's a desert. The Kosi was 160 kilometers to the east. Now it's over here. Majuli Island is dissolving into the river. The Himalayas are still rising.
And the glaciers are retreating at an alarming rate.
So here is a final provocative thought for everyone listening. We fight wars over borders. We draw these incredibly strict, permanent lines on maps. But if geography is this dynamic, if rivers can be beheaded and islands can literally vanish, what does the map of this region actually look like 1,000 years from now? Are the permanent borders of our states and our nations actually built on shifting sands?
That is a humbling thought. The land outlasts the maps we draw on it, but even the land itself doesn't last forever.
Something to think about next time you look at a river. Thanks for listening to The Deep Dive.
Stay curious.
At this point, it is important to understand the geographical logic behind this pattern.
And when we say pattern here, we're talking about something on a truly planetary scale. This isn't just a bit of seasonal rain.
No, not at all. This is the Indian monsoon. And if you've ever been in India during that time, you know it feels less like weather and more like, I don't know, a fundamental force of nature.
That's a perfect way to put it. A force of nature. And digging through the sources for this deep dive, that's the overwhelming feeling. The scale of it all.
It's staggering. We're not just talking about clouds and rain. We're talking about this massive, rhythmic, atmospheric machine. An engine, really.
It is an engine. And it's the engine that powers the entire subcontinent. I mean, it drives everything from agriculture and the economy to culture and, frankly, to life itself.
So for our deep dive today, that's the mission. We're going to try and take this engine apart.
Look under the hood, piece by piece. First, we need to get into the mechanics, the why and the how of the monsoon itself.
Right.
What actually makes it tick?
And then follow the water. Once it hits the ground, it creates these incredible river systems that, as we'll see, are anything but static.
Exactly. They move, they shift, they have a life of their own. And finally, we have to look at the human story. How do over 1 billion people try to manage, share, and survive this resource that is so powerful yet so volatile?
Okay, let's start at the beginning then. The word itself, monsoon. It sounds so specific, but the origin is actually quite practical.
Very practical. It comes from the Arabic word mausim.
Which just means season.
Right. It wasn't a meteorologist who coined it. He was a sailor. For centuries, Arab traders navigating the Indian Ocean noticed something remarkable. The winds weren't random.
They were predictable. They had a schedule.
A perfect schedule. For about 6 months, the winds would blow consistently from the southwest, from the sea to the land. And then, like clockwork, they'd reverse.
And blow from the northeast, from the land back out to sea.
And that reversal, that's the technical definition of a monsoon. It's not the rain. The rain is just the cargo.
Yeah.
The monsoon is the seasonal reversal of the wind.
So the first question is the big one. What flips that switch? Why does this massive wind system do a complete 180 every 6 months? I remember the simple explanation from school.
Ah, the classical thermal theory.
Yeah, the giant sea breeze idea.
Proposed by Edmund Halley of comet fame way back in 1686. And it's the one we all learned because it's intuitive. It makes perfect sense.
It's the beach logic. You go to the beach on a hot day, the sand is scorching, but the water is cool.
Exactly. Land heats up fast, water heats up slow. So the air over the hot land rises, creating a low-pressure zone. It's like a vacuum. The cooler, denser, high-pressure air over the ocean rushes in to fill that space.
And Haley's big idea was just to scale that up. The entire continent of Asia is the beach, and the Indian Ocean is the ocean.
Pretty much. In summer, the huge landmass of Asia bakes in the sun, creating this enormous low-pressure system. Winds rush in from the ocean loaded with moisture. In winter, the land cools down much faster, the pressure flips, and the winds blow back out to sea.
It's neat. It's clean. But I'm guessing it's not the full story.
It's not wrong, but it's woefully incomplete. It's too simple. If it were just this giant sea breeze, the monsoon would build up gradually. As summer gets hotter, the winds get a bit stronger, the rain slowly increases.
But that's not what happens. It's famous for the burst.
It arrives with a bang. It's a sudden, dramatic structural change in the whole atmospheric circulation. It's not a gentle ramp-up. It's a switch being flipped.
Okay, so to understand the burst, we need a more complex model.
We need to move on to the dynamic concept. This brings in the movement of the planet's own wind and pressure belts. And that means we have to talk about the ITCZ.
The Intertropical Convergence Zone always sounds like something out of science fiction.
It really does. But it's basically a belt of low pressure that circles the Earth around the equator. Think of it as the planet's thermal equator. It's where the trade winds from the northern and southern hemispheres smash into each other, rise up, and create a lot of rain. It's the rainiest belt on Earth.
But it doesn't stay put over the equator.
No, because the Earth is tilted on its axis. So as the sun's direct rays appear to move north in our summer, towards the Tropic of Cancer, it drags this whole ITCZ system north with it.
So the equator's entire weather-making machine basically goes on a road trip up to India for the summer.
That's a fantastic way to put it. The northern ITCZ gets pulled right over South Asia, sometimes as far north as 30 degrees latitude. And when that happens, the trade winds from the southern hemisphere have to cross the equator to chase it.
And the Earth's rotation, the Coriolis force, gives them a twist.
It gives them a sharp right turn, and they become the southwest monsoon winds. But, and this is the really crucial part, even that isn't enough to explain the sheer violence and intensity of the Indian monsoon. There's a catalyst.
A turbocharger.
It's a geographical turbocharger. And its name is the Tibetan Plateau.
This was the part of the research that just blew my mind, because you think of Tibet and the Himalayas as cold. Ice, snow, high altitude.
Right, not as a heat engine.
But that's what it is, a giant heat engine.
A massive one. This was the key insight from the big meteorological expeditions in the 70s, like Monex. You have to picture the scale of Tibet. It's not just a mountain range, it's a plateau. 4.5 million square kilometers.
That's enormous.
And it sits at an average altitude of 4,000 meters. I mean, that is almost halfway up to the troposphere, the part of the atmosphere with weather.
Oh, okay, so it's a huge elevated landmass.
And in the summer, the sun just beats down on it. The air up there is thinner and cleaner, so the solar radiation, the insolation, is incredibly intense. The ground gets hot.
Hotter than the air around it.
Significantly hotter. About 2 to 3 degrees Celsius warmer than the surrounding air at that same altitude. So Tibet basically becomes a gigantic hot plate held up in the middle of the atmosphere.
And what does hot air do? It rises.
It shoots upward. You get this immense, powerful column of rising air, this incredible convection right over the plateau.
So all this air is rising, where does it go? It can't just go into space.
No, it hits the top of the troposphere, the tropopause, and spreads out. And all that outflowing air creates a massive, powerful, high-pressure system, an anticyclone. But it's an anticyclone in the upper atmosphere.
So you have low pressure at the surface, drawing air in, and high pressure at the top, pushing air out.
Precisely. And that high-pressure system has to vent. It creates a wind, a high-speed river of air flowing high above India.
The easterly jet stream.
Correct. And this jet stream is the final piece of the puzzle. It's the trigger. It flows from east to west over India and essentially acts like a steering mechanism for the low-pressure systems, the storms. On the surface, it pulls them deeper into the continent.
Wow. So let me see if I've got this. If the Tibetan Plateau wasn't there, or if it were at sea level.
The Indian monsoon might just be a mild, unremarkable seasonal rain. The sheer height and bulk of Tibet is what physically creates the intensity. It's a geological feature that turbocharges the entire atmospheric engine.
A geological accident that allows a billion people to eat.
Yeah.
That's incredible. But the machine is even bigger than that. The sources talked about global connections, teleconnections.
Right, the monsoon doesn't operate in a vacuum. It's plugged into the planet's wider atmospheric pulse. And the biggest connection is with the Pacific Ocean. We have to talk about ENSO.
El Nino and the Southern Oscillation. I hear about El Nino constantly, usually in the context of droughts in Australia or floods in California. How does it affect India?
Think of it as a giant pressure seesaw stretching from the Indian Ocean across to the Pacific.
Okay, a seesaw.
In a normal year, one end is up and the other is down. You have high pressure over the eastern Pacific, near Peru, and low pressure over the western Pacific, near Indonesia and Australia.
And low pressure is good for rain.
Yes. That setup, called the Walker circulation, reinforces the flow of moist air towards Asia. It's like a tailwind for the monsoon.
But in an El Nino year,
The seesaw flips. For various reasons, a pool of warm water appears off the coast of Peru. This reverses the whole pressure system. You get low pressure over the eastern Pacific and high pressure over the Indian Ocean and Indonesia.
and high pressure is the enemy of the monsoon.
It's a killer. High pressure means air is sinking, and sinking air is stable. It suppresses cloud formation. It puts a lid on the atmosphere. So when scientists see a strong El Nino forming and a negative southern oscillation index, they get very worried about the monsoon. It often correlates with weak rains or even severe drought in India.
So a farmer in Uttar Pradesh is basically waiting to find out what the sea surface temperature is off the coast of South America.
It's all connected. And there's one more piece, a bit closer to home, the Somalian current.
Also called the Findlater jet.
Right. This is a low-level, high-speed current of air that screams off the coast of East Africa near Somalia. It's like a booster rocket aimed directly at India's west coast.
And what powers that rocket?
A strong, low-pressure area near Somalia. The stronger that low pressure, the faster this jet of air flows across the Arabian Sea and the harder it slams into the Western Ghats. So a perfect monsoon needs a whole team to show up. A hot Tibet, a cool Pacific, and a strong kick from the coast of Africa.
It's like an atmospheric relay race. So let's assume all the runners do their part. The engine is primed, the winds arrive. Let's get to the main event. The burst.
It's such a dramatic term, but it's accurate. It isn't a slow start. One day it's hot and dry, the next day the sky's open. It's a sudden, definitive shift.
And it has a schedule.
A pretty reliable one. It typically hits the coast of Kerala, at the southern tip, around June 1st. Within about 10 days, say June 10th to the 13th, it's swept up to Mumbai and Kolkata. By mid-July, the entire country is under its influence.
And when this massive wall of wind and water hits the Indian peninsula, the geography of the land itself forces it to split.
Exactly. The triangular shape of the peninsula acts like the bow of a ship, cleaving the monsoon into two distinct branches. You get the Arabian Sea branch and the Bay of Bengal branch.
Let's follow the Arabian Sea branch first. It's heading east and hits the west coast of India.
And it hits a wall, the Western Ghats. This is a continuous range of mountains that runs parallel to the coast for hundreds of kilometers. They're not the tallest mountains in the world, but they are in exactly the right or wrong place.
They're directly in the path of the wind.
Directly. So this moisture-saturated air has nowhere to go but up. And as it's forced to rise, it expands, it cools, and it just dumps its moisture.
This is orographic rainfall, relief rainfall.
It's the textbook example. The windward side of the Ghats, places like Mumbai, Mangalore, they get absolutely drenched. We're talking 250 centimeters of rain, sometimes much more, in just a few months.
But then something fascinating happens on the other side of the mountains.
The rain shadow effect. As soon as that air crosses the crest of the mountains and begins to descend on the other side, the leeward side,
It starts to warm up.
it gets compressed and warms up. And warm air can hold more moisture, so
Got
it
it.
stops raining abruptly.
So you have a situation where it's a tropical rainforest on one side of the mountain and just a few dozen kilometers away on the other side.
It's semi-arid scrubland, the Deccan Plateau. It sits in the shadow of the mountains. You can literally drive from a deluge to a dry zone in an afternoon. It's one of the most dramatic examples of a rain shadow on Earth.
Okay, so that's the Arabian Sea branch. Meanwhile, the Bay of Bengal branch is taking a different route.
It's moving north up the Bay of Bengal. Some of it hits the coast of Myanmar and gets deflected west up the Gangetic Plains, guided by the Himalayas. But a crucial part of it gets funneled into a very specific geographical trap.
In northeast India, Meghalaya.
The Garo Khasi, and Jaintia hills. If you look at them on a map, they form a funnel shape, with the wide opening facing south, directly into the path of the monsoon winds.
So the winds just pour into this funnel.
They pour in, and as the valley narrows, the air gets compressed and forced upwards. It's an extreme version of the orographic effect.
And that's why this tiny corner of the world gets more rain than anywhere else on the planet.
That's why Masinram and Cherrapunji are the wettest places on Earth.
Yeah.
It's not magic. It's just the perfect geometry for squeezing every last drop of moisture out of the air.
Which brings us to the opposite extreme, Western Rajasthan, the Thar Desert. The monsoon winds actually pass over this area, but almost no rain falls. Why?
It's a cruel trick of geology and geometry. There's a mountain range there too, the Aravalli Range. But unlike the Western Ghats, which stand like a wall across the wind's path.
The Aravallis run parallel to the wind direction.
Exactly. So the winds just slide right past them. They're never forced to rise significantly, so they never cool enough to produce heavy rain.
So the wind just keeps its moisture and moves on.
It does. And to make matters worse, the intense heat rising from the desert floor can actually cause any potential droplets to evaporate before they even hit the ground. So it's a combination of factors. The alignment of the mountains is everything.
It's mind-boggling. You could theoretically rotate the Aravalli Range by 90 degrees and turn a desert into a forest.
You absolutely could. It shows how profoundly geology dictates climate.
Yeah.
Now, another important thing the sources mentioned is that the monsoon isn't just 4 months of nonstop rain.
Right, it takes breaks.
They're called breaks in the monsoon. You can have dry spells that last for a week or more. This typically happens when the main engine of the surface monsoon, a low-pressure line called the monsoon trough, shifts its position.
It moves north.
It moves north, right up to the foothills of the Himalayas. When that happens, the rain effectively stops over the Great Plains of India.
Which must create a really dangerous situation for farmers.
It's a paradox. The farmers in Punjab or Bihar are looking at clear skies, their crops are wilting, and they're facing a drought. But because the trough is over the mountains, the rainfall intensifies dramatically in the Himalayas.
And all that extra rain in the mountains has to go somewhere.
Downhill.
Yeah.
Into the rivers. So at the exact same time you have drought conditions in the plains, you have catastrophic floods in rivers like the Brahmaputra or the Kosi. It's a water management nightmare.
Drought and flood, side by side. And speaking of water, outside the main season, there's one more piece to the puzzle. The winter rains.
The western disturbances. This is crucial for understanding the full picture of water in North India.
So these aren't part of the monsoon system at all.
Not at all. They're a completely different phenomenon. For most of India, winter is the dry season. The winds have reversed. But in the northwest, they get rain.
And these storms come from the Mediterranean?
That's right. They are temperate cyclones born in the Mediterranean Sea. They're then picked up and carried east by the subtropical westerly jet stream, a different jet stream from the monsoon one.
So they travel all the way across the Middle East, Iran, Afghanistan.
And finally arrive in northwest India, Punjab, Haryana, Kashmir. They bring crucial winter rain and snowpack in the mountains.
And this is essential for the winter crops.
Absolutely vital for the rabi crops, especially wheat. The Green Revolution in that part of India depends as much on these winter western disturbances as it does on the summer monsoon.
Okay, so the atmospheric engine is working, the rain has fallen, both in summer and winter. Now we have to look at what happens on the ground, because once that water lands, it forms these river systems that...
Well, they seem to have a mind of their own.
They really do, especially the rivers that come from the extra-peninsula region. The Himalayas...
They're young rivers from young mountains.
Exactly. The Himalayas are geologically very young and still rising. The rock is crumbly, the slopes are steep. So the rivers flowing off them are incredibly energetic and carry a mind-boggling amount of silt and sediment.
So they're not content to just stay in one place.
Not at all. When they hit the flat plains, they lose energy, dump all that silt, which clogs up their own channels. Then, during the next flood, the river just breaks out and finds a new, easier path. They meander, they braid, and sometimes they just move entirely.
Right. And the most incredible example of this in the sources was the Lost River, the Saraswati. The Saraswati is a fascinating case. For a long time, it was known mostly from ancient Hindu scriptures, the Vedas, where it's described as a mighty river. Many thought it was just mythological.
But it was real.
Oh, very real. Modern satellite imagery and geological surveys have mapped its paleochannels, the ancient dry riverbeds. And it was enormous, Back around 2000 or 3000 BC, it was a major river system flowing through what is now the Thar Desert.
So what on earth happened to it? How does a river that big just vanish?
It was a victim of a process called river capture, which sounds like something out of a pirate movie,
River piracy.
essentially. Tectonic uplift, the ground itself tilting and rising, changed the landscape.
Mm.
The Yamuna River, which used to be a major tributary of the Saraswati from the east, was captured. The slope of the land changed and it was diverted east to join the Ganga instead.
And from the other side?
A similar thing happened. The Sutlej River, its main water source from the west, was captured by the Indus River system.
So the Saraswati was essentially starved of its water sources from both sides.
It was beheaded. It lost its headwaters. With its main sources gone, it slowly dwindled, turning into a series of disconnected pools and marshes, and eventually it dried up completely, leaving only a ghost riverbed in the desert, the Gagar Channel.
That is an unbelievable story of how dynamic the landscape is. And it's not just ancient history. The text says the Brahmaputra made a massive shift much more recently.
Yes, very recently in geological terms. Until the late 18th century, so around 1720 to 1830, the main channel of the Brahmaputra River used to flow much further east, joining the Meghna River in what is now Bangladesh.
And what changed?
Again, tectonics. There was significant uplift in an area called the Madhopur Tract. The ground literally rose up and blocked the river's path, so the river was forced to find a new way. It cut a new channel westward and joined the Ganga, creating the river we now call the Jamuna in Bangladesh.
Imagine living through that. One day the river is over there, and a few decades later it's moved miles to the west.
Or worse, imagine the river deciding to move through your village. That's the story of the Kosi River in Bihar. It's known as the sorrow of Bihar.
Because it's so unpredictable.
Notoriously so. It carries more silt than almost any other river. It builds up its own bed so high that it's flowing above the level of the surrounding plains. Then during a major flood, it just bursts its banks and carves a new path through the lowlands. It has shifted its course by over 110 kilometers in the last 250 years, causing untold destruction.
These rivers really aren't just lines on a map. They're living, moving things. So we have water that flows and moves. What about water that stands still? The lakes. The text had this really interesting genetic classification.
Right, classifying them based on how they were born, what geological or natural process created the depression that holds the water.
So let's run through the family tree. First up, tectonic lakes.
Born from the Earth's crust, bending, breaking, or faulting. The classic example is Wular Lake in Kashmir, which is India's largest freshwater lake. It sits in a depression formed by tectonic activity. Pangong Tso in Ladakh is another famous one, a long, narrow lake formed along a fault line.
Then there are the more violent origins, crater lakes.
Yes, specifically Lonar Lake in Maharashtra. This is a truly unique place. It's a large lake sitting in a crater formed by a meteor impact about 50,000 years ago. It's one of the best preserved impact craters in basaltic rock anywhere in the world.
Up in the mountains, we have glacial lakes.
Also known as tarns. These are carved out by the immense power of glaciers. As a glacier moves, it scours and plucks out rock, creating hollows. When the glacier melts and retreats, it leaves behind these beautiful, crystal-clear lakes high in the Himalayas, like Tundra Tal in Himachal.
And then there are the ones made by rivers and wind.
Right, fluvial lakes are formed by rivers themselves. The most common are oxbow lakes, which are old meanders that the river has cut off. And aeolian lakes are formed by wind, especially in the desert. The wind blows out depressions, or cans as they're called, which fill with water during the rains. Samvar Lake in Rajasthan is the largest of these.
Okay, but there were two lakes in the notes that were just bizarre. Let's start with the one that sounds like a horror movie. Rupkund, the mystery lake.
Ah, yes. Rupkund is a small, high-altitude glacial lake in Uttarakhand. For decades, it was famous, or infamous, for one reason. When the ice melts each summer, hundreds of human skeletons and bones are revealed at the bottom and around the edges of the lake.
And no one knew who they were. The theories must have been wild.
They were lost armies, pilgrims who died of an epidemic, ritual suicide. But modern science, DNA testing, and radiocarbon dating have pieced together a likely story. It appears to be a large group of people from around the 9th century who were caught in the open on a high mountain passed by a sudden, freakishly severe hailstorm.
Hail. That's what killed them all.
We're talking about massive hailstones. The skulls show evidence of fatal blows from above. There's nowhere to hide up there. They were killed by blunt force trauma from the sky, and the cold, icy conditions perfectly preserved their remains, for over 1,000 years.
That is just a chilling story. The other unique lake, a much happier one, was Loktok Lake.
Loktok in Manipur. This place is incredible. It's famous for its fumdis.
And Fumdis are. They're floating
They
islands.
are. They are these thick, circular mats of vegetation, soil, and organic matter, all tangled together that float on the lake's surface. They are so strong and buoyant that people live on them. They build their huts on these floating islands.
And there's a national park that floats?
The Kaibal Lamjo National Park. It's a large fumdi that has been designated as a park, making it the only floating national park in the world. It was created to protect the endangered sangai, or brow-antlered deer, which lives its entire life on this floating ecosystem.
A floating park for dancing deer. That's incredible. Okay, so we have this incredibly dynamic water system, but now we have to get to the so what of it all. This is the water that sustains a billion-plus people, and the sources described a fundamental paradox.
The great paradox of water in India. There's a huge amount of it in total, but it's never in the right place at the right time. The country gets an immense amount of rainfall, but something like 75% of it falls in just the 4 months of the monsoon.
So you have a season of flood followed by a season of drought.
Exactly. And since agriculture is the biggest user of water, by far about 77% of all water use, you have to bridge that gap. To grow food in the dry season, India turned underground.
Groundwater. This brings us to the section on groundwater provinces. I never really thought about it this way, that the type of rock beneath your feet basically determines your water security.
It's geology's destiny all over again. The sources break India down into 3 broad provinces based on their capacity to store groundwater.
Let's start with the south, peninsular India.
That's the Precambrian crystalline province, a fancy name for very old, very hard rock. Granite. Nice. This rock is not porous. It doesn't act like a sponge.
So where's the water?
It's only held in the cracks, the fissures, the weathered top layer. The storage capacity is extremely low. It's hard to find water, and if you pump a well dry, it can take a very long time to recharge.
Now, compare that to the north, the Indo-Ganga plains.
It's a completely different planet, geologically speaking. This is the Ganga-Brahmaputra alluvial province. It's not hard rock. It's thousands of feet of soft sediment sand, silt, gravel, and clay washed down from the Himalayas over millions of years.
So it's a gigantic sponge.
It is one of the richest, largest aquifers in the entire world. It holds an estimated 44% of India's total recoverable groundwater. This is the geological foundation of the Green Revolution. You could drill a tube, well, almost anywhere in Punjab, Haryana, Uttar Pradesh, and hit abundant, easily accessible water.
But I'm guessing even a giant sponge can be overused.
And that's the crisis we're seeing now. The water was treated as an infinite resource. It's not. It's a bank account. And for decades, the withdrawals have been greater than the deposits from the monsoon.
Overexploitation.
Exactly. In states like Punjab, Haryana, Rajasthan, and Tamil Nadu, water tables are plummeting. People are drilling deeper and deeper, and the deeper you go, the more problems you find.
The quality of the water gets worse.
Yes. You start hitting layers with high concentrations of fluoride, or, in the Ganga Delta, naturally occurring arsenic. So we're not just running out of water. In some places, the water we have left is poisoning people.
This scarcity, this competition, it naturally leads to conflict. The next section in the sources was all about disputes and engineering.
Because water crosses borders. In India, water management is a state subject under the Constitution, but of course, rivers don't respect state lines. This sets up inevitable conflicts.
And the oldest and most bitter one is the Kaveri dispute.
Karnataka versus Tamil Nadu. It's the classic upstream versus downstream fight. The Kaveri River originates in Karnataka. They build dams to use the water for their cities and farmers, but the river then flows into Tamil Nadu, which has a huge ancient agricultural delta that is completely dependent on that same water.
And in a year with a weak monsoon.
There simply isn't enough water to satisfy both. And that's when it explodes. Protests, court battles, political crises. It's been going on for over a century. And you see similar disputes over the Krishna, the Godavari, the Ravi Beas rivers.
It's not just internal, they're international rivers too, like the Indus.
And the Indus is actually a fascinating story of cooperation against all odds. The Indus Water Treaty, signed in 1960 between India and Pakistan, brokered by the World Bank.
How did they solve such a complex issue between two rival nations?
They did something very clever. Instead of trying to argue about sharing the flow of each river every single day, which is a recipe for constant conflict, they just divided the rivers themselves.
They split the whole system.
Yes. India was given exclusive rights to the 3 eastern rivers, the Ravi, Beas, and Sutlej. Pakistan was given the rights to the three western rivers, the Indus, Jhelum, and Chenab. It's a clean separation.
You take these, we'll take those.
Exactly. And incredibly, despite multiple wars and a state of near constant tension, that treaty has held. It's one of the world's most successful water-sharing agreements because both sides know that the alternative is just too catastrophic to consider.
Okay, so to solve this problem of distribution water in the wrong place at the wrong time, there's this enormous, almost mythical project that keeps coming up, the National Water Grid.
The interlinking of rivers. It is the ultimate engineering dream. The concept is simple on the surface. If the Brahmaputra Basin has surplus water causing floods, why not build a giant canal to transfer that water to the deficit basins of peninsular India?
Treat the country's rivers like a national plumbing system.
Precisely. But the reality is just mind-bogglingly difficult. Take the most famous proposal, the Ganga-Kaveri Link Canal. You're talking about a canal over 2,600 kilometers long. But that's not even the hard part.
What's the hard part?
The geography of central India. To get the water from the Ganga Basin to the south, you have to cross the Vindhya Mountains. You would need to lift a volume of water equivalent to a large river up and over a ridge that's more than 400 meters high.
The energy cost of that pumping alone would be astronomical.
It would require dedicated power plants just to move the water, not to mention the environmental cost of damming these rivers, the ecological disruption, the displacement of millions of people. It's a dream that many engineers have, but many ecologists see as a potential nightmare.
So if these mega projects are too big and complex, what's the alternative? The sources ended on a more local solution.
Water harvesting. It's a shift in philosophy. Instead of trying to conquer nature with massive dams and canals, it's about working with it on a small scale.
Going back to traditional methods.
Exactly. For centuries, people in arid regions like Rajasthan perfected water harvesting. They built kunds and tankas, which are beautifully designed underground cisterns to capture every single drop of precious rainwater from a rooftop or a small paved catchment area.
And now this old idea is being implemented on a modern urban scale.
Yes. The state of Tamil Nadu made it mandatory for all new buildings to have rooftop rainwater harvesting systems. The idea is simple. Catch the rain where it falls.
Don't just let it run off into the gutter and out to sea.
Guide it back into the ground. Use percolation pits, recharge shafts, check dams. The goal is to consciously refill the aquifer, that underground sponge, right where you live. It's about shifting from macroengineering to micromanagement of the water cycle.
It really feels like we've come full circle in this deep dive. We started with the sun heating a plateau in Tibet, which creates the wind that brings the rain, which fills the rivers and the aquifers, and we end with a person on their roof guiding that same water back into the ground.
It is one single interconnected system. And understanding that entire chain reaction, that geographical logic from the jet stream down to the village well, is absolutely critical. We're not just managing a commodity, we are participants in a vast planetary cycle.
So after taking this whole machine apart, what's the final provocative thought we should leave everyone with?
I think it has to be about fragility. We've just spent all this time talking about how powerful and inevitable the monsoon seems. But the entire engine runs on very specific temperature differences. The thermal contrast between the hot Tibetan plateau and the relatively cool Indian Ocean.
And a changing climate is messing with those very temperatures.
It is. The science is still evolving, but the risks are clear. If the glaciers and snowpack on Tibet melt, it could change how the plateau heats up. If the Indian Ocean warms faster than the land, that pressure difference, the very thing that drives the wind, weakens. The gears of the machine could start to slip.
So we're tampering with the thermostat of the engine that brings us all our water.
That's the sobering reality. We are fundamentally altering the thermal properties of the planet. And this is a system that is exquisitely sensitive to those properties.
Yeah.
The monsoon isn't just a weather report. It is the rhythmic heartbeat of a subcontinent.
And ensuring that heart keeps beating regularly, that is the challenge of our time.
It truly is. At this point, it is important to understand the geographical logic behind this pattern.
It absolutely is. Because, if you just glance at a rainfall map of India, it can look totally random.
Right. It's like a splotch of blue here, a dry patch there. It seems chaotic.
Exactly, chaotic. But there's a very strict, almost mechanical logic to where all that water falls. And it really all begins with the two massive arms of the monsoon.
The two giants. I've got the Arabian Sea branch and the Bay of Bengal branch.
Correct. And to really get a handle on the pattern, you have to track them almost like like 2 separate delivery trucks on 2 different routes.
Okay, so let's start with the first one, the Arabian Sea branch.
All right, so this one comes in from the southwest. It's just loaded with moisture. The first thing it does is slam right into the Western Ghats.
And it just dumps a massive amount of water there. We see that on the map.
A huge amount. But then it keeps moving inland. And this is where I think a lot of the confusion comes in. It blows right over Gujarat and then Rajasthan.
Okay, and this is the part that I have to admit always gets me. You have this wind, which we know is full of moisture, literally traveling over Rajasthan. But Rajasthan is a desert. If the clouds are there and the wind is there, why on earth isn't it raining?
This is what we call the parallel problem. It's such a classic textbook example of how topography, the actual shape of the land, completely dictates the climate.
So it's about the mountains.
It's all about the Arar Valley Range. Think about how it's aligned.
The Arar valleys run southwest to northeast.
Exactly. They run parallel to the direction of that incoming monsoon wind.
I think I see where this is going.
Yeah. So just think about the physics of rain for a second. To get rain, you usually need what's called orographic lift. You need that moist air to hit a barrier, a mountain, and be forced to rise up.
And as it rises, it cools down.
Precisely. It expands and cools. That's adiabatic cooling. And that's the trigger that turns invisible water vapor into actual liquid water droplets. The mountain needs to act like a ramp.
But the Arar valleys don't.
They can't. Because they're running parallel to the wind, they don't act like a ramp at all. They act more like a guardrail on a highway.
So the wind just slides right past them.
It just skims right along the side. There's no barrier, nothing to force that huge air mass to go up. So the air stays low, it stays hot, and it just holds on to all that moisture.
It's just carrying it.
It carries it right over the desert without dropping a single drop. It's maddeningly efficient in a way.
It's like it's teasing the desert. I have all this water for you, but I'm just going to carry it over your head and take it to the Himalayas instead.
That is exactly what's happening. That same air mass will move all the way to the western Himalayas before it finally finds a barrier big enough and perpendicular enough to force it up and make it rain.
So Rajasthan is a desert not because there's no moisture in the air above it, but because the land itself refuses to squeeze it out.
That's the key. The geography is the problem.
Okay, now let's compare that to the other arm, the Bay of Bengal branch. That one behaves completely differently, doesn't it?
Oh, it's a completely different beast. This current travels north up the Bay of Bengal, and it doesn't have a parallel problem. It has a collision problem.
A collision problem.
It smashes head-on into the coast of Myanmar and the Arakan Hills. It basically hits a dead end.
And since it can't go through the mountains,
It has to turn. A huge portion of that current gets deflected. It takes a sharp left, essentially, and gets funneled west right into the Ganga Plain.
okay, so it's a forced turn.
A forced turn. But before it even goes west, a part of that branch gets caught in this very specific geographical trap up in the northeast.
And this must be the funnel effect that's mentioned in the notes.
Yeah.
This is where we get Masenram and Cherrapunji.
Yeah.
The rainfall numbers here they're frankly absurd. 1,100, sometimes 1,200 centimeters a year.
Yeah.
I mean, for context, a city like London, which is famous for being rainy, gets maybe 60 or 70 centimeters.
Yeah, the scale is hard to comprehend. We are talking about 20 times that amount of water. It's planetary scale rainfall.
So what is the geography doing there? How does it create that?
It's all about the geometry. You have 3 hills, the Garo, the Khasi, and the Jaintia hills. And they aren't just a straight wall, they're arranged in the shape of a funnel, with the wide opening pointing south towards the Bay of Bengal.
So the clouds just fly right in.
They fly into this wide mouth, and as they push deeper, the walls of the funnel start to narrow.
So all that air is getting squeezed.
It's being squeezed and forced violently upwards. It literally has nowhere else to go. It's like trying to push the contents of a fire hose through a drinking straw.
And the result is?
The result is that the clouds just dump almost their entire moisture load in one incredibly concentrated spot. That is the only way you can get those kinds of record-breaking numbers.
But then the system changes again. Once that wind escapes the northeast and starts its journey west, up the Ganga Plain towards Delhi, the story completely flips. It goes from too much to less and less.
Right. A good analogy is to think of it like a delivery truck that starts with a full load of packages in Kolkata. As it drives west, it's dropping off packages at every single stop. By the time it gets to the end of its route in, say, Punjab, the truck is nearly empty.
And we can see this perfectly in the city-level data mentioned in the source.
It's a perfect match. Kolkata is near the start of the journey. It gets about 120 centimeters of rain.
Hmm.
You move west to Patna, the number drops to 105. Keep going to Allahabad, and you're down to 90.
And by the time that same wind system reaches Delhi,
It's exhausted. It's dropped most of its load. It only has enough moisture left for about 65 centimeters of rain for Delhi.
so the geography creates this east to west rainfall gradient. The further west you live along that plane, the harder the wind has already worked, and the less water it has left for you.
Precisely. And then eventually the party ends. The monsoon doesn't just switch off like a light, it retreats. We spend so much time obsessing over the arrival of the monsoon, but the retreat, this autumn phase, is just as dramatic, just in a different way.
This brings us to the phenomenon of October heat. I feel like anyone who's lived in North India in October knows this feeling viscerally, even if they don't know the technical term. It can be worse than the summer.
It is physically much more punishing for the human body, and there's a clear reason for it. By late September, the sun is migrating south, so the big, low-pressure monsoon trough withdraws from the Punjab plains. The clouds vanish.
So you suddenly get these clear blue skies.
You get clear skies, which means the sun's radiation is hitting the ground at full power again, just like in May. But there's one huge difference.
The ground is still soaking wet from 3 months of rain.
Exactly. You are basically heating up a giant waterlogged sponge.
You're creating an open-air sauna.
That's the perfect description. The temperature shoots up, but because of all the moisture evaporating from the ground, the humidity is also sky high. And that combination, very high heat plus very high humidity, is the October heat. It is oppressive.
But while North India is sweating it out, the East Coast is preparing for something far more dangerous. The retreat seems to trigger a really nasty shift in the Bay of Bengal.
It really does. As those low-pressure systems move off the land and back over the warm waters of the Bay of Bengal, they pick up a huge amount of energy and moisture. This transition season is the prime breeding ground for cyclonic depressions.
And these are the powerful storms that slam into the eastern coast, Odisha, Andhra Pradesh, Tamil Nadu.
Yes. And they can be devastating. The source material specifically references the 1999 supercyclone in Odisha. We're talking about winds over 300 kilometers an hour. That single storm killed more than 10,000 people. It's a stark reminder that the retreat of the monsoon isn't some peaceful fading away. It can be incredibly violent.
There is one major exception to this pattern, though, one oddity. While the rest of India is either drying out or dodging cyclones, Tamil Nadu is actually just starting its main rainy season.
The Coromandel Coast is the great outlier. It is completely out of sync with the rest of the country.
Why is that?
Well, during the main monsoon in June and July, Tamil Nadu is actually in the rain shadow of the Western Ghats, so it stays relatively dry. But in October, November, December, those retreating winds blow back over the Bay of Bengal. They pick up a whole new load of moisture, and then they slam right into the coast of Tamil Nadu.
So their monsoon is essentially the rest of the country's exit strategy.
Physically, that's exactly right. The geography just ensures that someone is always getting water, even if the timing is completely different across the subcontinent.
Which brings us to, I think, one of the most critical themes in these documents, the variability paradox. This feels like the most important concept for understanding water security. It's not about the average rainfall. Averages can be so misleading. It's about reliability.
This is truly the cruelest irony of the Indian climate system. If you were to take two maps, one showing the average annual rainfall and one showing the variability of that rainfall, and you put them on top of each other,
They're inverses.
they are almost perfect mirror inverses of each other. The rule is brutally simple. Where the average rainfall is lowest, the variability is highest.
Let's break that down because it's so important. You're saying the places that are the most desperate for every drop of water are the exact same places they can't trust the sky to deliver it.
Precisely. Take Western Rajasthan or Ladakh. The average rainfall is already incredibly low, but the variability is over 60%.
60%. What does that mean in a practical sense?
It means that in any given year, the actual rainfall might be double the paltry average, or it could be zero, absolutely nothing. You cannot plant a farm, you cannot budget your water for your village. It's pure meteorological casino.
Whereas in the really wet areas,
In the Western Ghats or the Northeast, where they get more water than they know what to do with, the variability is very low, maybe less than 15%. The rain is reliable, they get a surplus, and they get it consistently year after year.
and this unreliability is what defines the drought belts that the sources talk about. It's not just the obvious arid regions, but also those rain shadow areas.
Yes, that rain shadow belt, the interior of the peninsula, so parts of inland Karnataka, Andhra Pradesh, that's where the human cost of this variability becomes truly tragic.
The source explicitly links this climatic unpredictability to the high rates of farmer suicides in those regions. That's a very heavy correlation to draw.
It is, but we have to face it based on the data. These farmers are operating in a zone where their primary input, water, is statistically unreliable. They might take out a loan for seeds and fertilizer expecting an average year, but because the variability is so high, the rain just doesn't show up. The crop fails completely, the debt remains. It is a high-stakes gamble every single season, a gamble dictated entirely by these invisible global wind patterns.
Now, on the absolute flip side of that drought coin, we have the floods. The scale mentioned here is just staggering. 40 million hectares of land in India is considered flood-prone.
It's a massive area.
And reading through the causes, it seems like it's a triad of blame. It's not just one thing.
No, it's a perfect storm of causes coming together. First, you have the purely meteorological factor. Simply too much rain falling too fast, often from those cyclones we just discussed.
Okay, the weather itself.
Then you have the geomorphic factor, the shape of the land. Many of these areas have huge catchment basins draining into very flat river plains with inefficient drainage. The water arrives, and it just has nowhere to go. It just sits there.
And the third piece of the puzzle.
The anthropogenic, the human factor. We are actively making the problem worse. Deforestation in the catchment areas removes the natural sponge that holds back the water. Shifting cultivation destabilizes the soil, leading to more runoff. And we build poorly planned embankments that burst, creating catastrophic flash floods.
We have to talk about the specific rivers mentioned, the sorrows. The Kosi is the sorrow of Bihar. The Damodar was the sorrow of Bengal. Why do they get such dramatic, almost mythic names?
Because for centuries they brought regular, predictable devastation. Let's take the Kosi River, the sorrow of Bihar. Its core problem is geomorphic. It's a young river, geologically speaking, flowing down from the high Himalayas, and it's carrying an incredible amount of silt and sediment.
This is a very muddy river.
Extremely. And as soon as it hits the flat plains of Bihar, the water slows down, and all that silt it was carrying settles to the bottom, choking the riverbed.
So the riverbed itself actually rises up.
Yes, over time, the river effectively lifts its own bed higher and higher. Eventually, it overflows its banks and just cuts a completely new path across the landscape. The Kosi is notorious for this, for changing its course by tens of kilometers.
Wow. So you could build your house 5 miles from the river, and the next year, the river has moved and is flowing right through your living room.
That is the historical reality. You cannot build a stable life around a river that refuses to stay in its bed.
And then there's the Brahmaputra in Assam. The floods there seem to be an annual guarantee of chaos.
The Brahmaputra is a different kind of beast. It has the same massive siltation issue as the Kosi, but it's also located in one of the most seismically active zones on the planet.
So you have earthquakes.
Frequent earthquakes, which cause massive landslides in the Himalayas, which then dump even more debris and silt into the river. It's a double whammy of geomorphic instability. It leads to this constant, vicious cycle of flooding and island erosion. Places like Majuli Island are literally shrinking and disappearing year by year.
It's just such a chaotic, aggressive, and powerful system. I suppose that's why scientists have spent more than a century trying to classify it, trying to put a label on the chaos. We see these names in the notes: Köppen, Stamp, True-Artha.
Right, they're all trying to impose some kind of rational order on this immense climatic diversity. Köppen's classification is the one that's most widely used, even if it looks like a bowl of alphabet soup at first glance.
With all those codes like ALM and BWO.
Exactly. He uses these letter codes based on mean monthly temperature and rainfall. So AM is for the tropical monsoon climate you find on the West Coast, while BWHW is for the hot desert climate of Rajasthan.
It feels a bit academic, but does looking at a map with all these codes actually tell us something important about the country as a whole?
I think it tells us the most important thing of all, that India is really a continent masquerading as a single country. When you look at Köppen's map, you'll see a region in Jammu and Kashmir classified as E-type climate.
And E is?
Polar. That's the climate of the Arctic tundra. Then you look down at the map to central India and you see, that's a tropical savanna climate, the climate of the African plains.
So within one single political border, you have the weather of Switzerland and the weather of Central Africa.
Precise. And that immense climatic diversity is what creates what I like to call the green mirror.
I like that phrase from the source material. The idea that the country's vegetation is just a direct reflection of its rainfall patterns.
It is a perfect harmony. Nature is a very strict accountant.
Yeah.
If you show me a photograph of a forest from anywhere in India, I can probably tell you the average rainfall of that region without ever looking at a weather report. The natural vegetation map is almost a carbon copy of the rainfall map.
Okay, so let's walk through that mirror where we saw that deep blue, that really heavy rainfall on the map, the Western Ghats, the Northeast. What are we seeing on the ground in terms of plants?
There, we're seeing the tropical evergreen forests. These are the heavyweights of the plant world. They exist where rainfall is over 250 centimeters. It's hot, it's wet all year round, and the forest is incredibly dense. It's multi-storied.
What do you mean by multi-storied?
I mean, you have different layers. You have a low layer of shrubs and creepers, then a layer of shorter trees, and then a high canopy of very tall trees, all of them fighting to get a little bit of sunlight.
And because it's so dense up top,
Sunlight barely reaches the forest floor. So unlike a park, there's very little grass. It's just this dark, humid, green cathedral. The trees here are hardwoods, rosewood, gurjan, ebony. They're commercially valuable, but also very difficult to extract because the forest is so tangled and dense.
but the real economic engine of India's forests, historically at least, isn't the evergreen, is it? It's the next tier down?
No, you're right. It's the tropical deciduous forests. These are the monsoon forests. They cover the largest single area of India because they thrive in that moderate rainfall zone between 70 and 200 centimeters.
And they have a very distinct behavior that gives them their name.
They do. They shed their leaves. They're deciduous. For about 6 to 8 weeks in the peak of the dry summer, the whole forest goes bare.
Is that just to avoid the heat, or is there another reason?
It's a survival mechanism against thirst, not heat. Trees lose a huge amount of water through their leaves in a process called transpiration. In the peak of summer, when there's no rain, water is scarce. So the tree essentially shuts down its factory. It drops its leaves to stop losing precious moisture. It goes dormant to survive the dry season.
And this is where we find the really famous names in Indian timber.
This is the home of teak and sal. Teak is legendary. It has natural oils that make it resistant to white ants. It doesn't warp or crack. It weathers beautifully. It was the backbone of the British Navy's ships and the Indian railways.
And sal.
Sal is also incredibly hard and durable, used for railway sleepers and house beams. And of course, you find sandalwood in the deciduous forests of Karnataka. These forests are more open, they're easier to travel through, and for that reason, they've been massively exploited for their timber.
Then as we move into the even drier areas where the rain drops below 75 centimeters, the forest seems to go on the defensive.
It absolutely does. It becomes the tropical thorny forest. This is the vegetation of resistance and survival. You see acacias, wild palms, kedra trees. They aren't trying to grow tall and grand. They're just trying to stay alive.
How do they do that?
They have incredibly long roots, sometimes going down tens of meters to find the water table. And of course, they have thorns and very small leaves.
Again, to stop that water loss through transpiration.
Exactly. A big broadleaf is a huge liability in Rajasthan. A thorn is safe.
I want to shift gears for a second and take a ride up the elevator of the Himalayas, the montane forests. This section was fascinating because it's like driving from the tropics to the poles in the span of just a few hours.
It's the best possible example of how altitude mimics latitude. As you drive up a Himalayan mountain, the temperature drops and the entire forest ecosystem changes with it.
So what does that journey look like?
Well, you start at the foothills with those deciduous trees we just talked about, but go up to about 1,000 or 2,000 meters.
You hit the wet temperate zone.
Right. Suddenly you're surrounded by oaks and chestnuts. It looks like an English woodland. Keep driving higher, go up to 1,500 or 3,000 meters. Now you're in the coniferous zone.
Pines and firs.
Pines, silver firs, and the undisputed king of the Himalayan trees, the deodar.
The source calls it the timber of the gods.
It's a fitting name.
Yeah.
Deodar wood is fascinating because it's naturally impregnated with aromatic oil. This makes it incredibly durable and resistant to rot and insects. That's why all the old temples and colonial-era buildings in the hills are built with it. It lasts for centuries.
And if we keep climbing past the tree line,
The trees finally give up. You enter the alpine zone. You'll see stunted silver firs, junipers, and eventually just grasses and mosses. These are the alpine pastures, the summer home of transhumant tribes like the Gujars and the Bakarwals.
transhumant.
It means they move with the seasons. They bring their cattle and goats up to these high pastures in the summer when the snow melts because the grass is incredibly lush and nutritious.
We can't leave the vegetation section without talking about the kidneys of the coast. The mangroves.
The tidal forests. These are just biological marvels. They are specialists that live where no other tree can in salty, brackish water at the edge of the sea. You find them in the deltas of the Ganga, the Mahanadi, the Godavari, and the most famous, of course, is the Sundarbans.
Which is named after the Sundari tree.
That's right. And the Sundari tree yields a very hard, durable timber that's used specifically for building boats.
Why boats?
Because it doesn't rot in water. It has evolved to live its entire life in saltwater, so its wood is perfectly adapted to that environment. It makes for a perfect boat.
So we have this incredible inventory of trees across the country. And naturally, humans look at this inventory and see resources, they see an economy. The sources list timber and fuel wood as the major products, but I was actually more intrigued by the list of minor forest products. It feels like there's this whole hidden economy in the woods.
It is a massive and often invisible economy, especially for tribal and rural populations. Take bamboo, for instance. Botanically, it's a grass, but economically, it's often called the poor man's timber.
Because it's so versatile.
Incredibly versatile, and it grows unbelievably fast. You can build a house with it, you can make baskets and furniture, or you can crush it down and turn it into paper pulp. The entire rural economy of a state like Mizoram revolves around bamboo.
What about tendu leaves? That was a very specific one mentioned.
Hugely important in states like Madhya Pradesh and Odisha. Tendu leaves have the perfect texture and quality to be used as the wrapper for beetus, the local hand-rolled cigarettes. Collecting these leaves is the primary source of cash income for millions of people during the collection season.
Then there is lakak. I'll be honest, I always thought lak was a kind of tree sap or a resin. I didn't realize it was, well, an insect secretion.
It is. It's a secretion of a tiny insect called Caryolacca. It feeds on the sap of certain trees, like the palas or peepal, and it secretes this protective resinous crust all over the branches.
And we just scrape it off.
We scrape it off, process it, and you get lac. India has a virtual monopoly on the global lac market. It's used in everything from dyes and bangles to furniture polish and electrical insulation. It's a classic example of biodiversity translating directly into a unique economic product.
But this translation of nature into cash has a very dark side. The crisis of cover section in our source material makes for pretty grim reading.
The numbers are stark, and we have to look at the targets to understand the failure. The first National Forest Policy of 1952 set a very clear, ambitious goal. 33%, one-third of India's total land area should be under forest cover.
That's the magic number for ecological stability.
It is. And where are we today, more than 70 years later?
According to the source, we're hovering around 22.5%.
Right. We are nearly 10% short of our own target. And if you compare us to other countries, it's frankly embarrassing. Finland is over 70% forest. Brazil is 57%.
And on a per capita basis, it's even worse because of our massive population density.
It's abysmal. The world average is about 0.8 hectares of forest per person. In India, it's 0.07 hectares. We have far too many people pressing against far too little forest.
What's driving this decline? Is it just poor villagers cutting wood for fire?
That's part of it. That's the subsistence pressure. But the real structural damage comes from bigger, more organized forces. Shifting cultivation, what's called shooming in the Northeast, involves clearing and burning forests for temporary farms. And big river valley projects, dams like the Narmada Sagar or the Tehri Dam, they submerge thousands of hectares of prime, dense forest literally overnight.
And then there are the solutions that sometimes end up backfiring. This brings us to the whole concept of agroforestry. On paper, this sounds like a perfect win-win. You encourage farmers to plant trees on their own land, they get a source of income from the wood, and the country gets more green cover.
It sounds great in a policy document.
But the source material calls this out, specifically with the eucalyptus dilemma.
This is a fascinating and cautionary tale of market incentives overriding ecological common sense. The government's social forestry programs told farmers, plant trees. But farmers are rational economic actors. They aren't going to plant a slow-growing oak tree that their grandchildren might one day harvest. They want cash, and they want it now.
So they pick the fastest-growing tree they can find.
They picked eucalyptus and poplar. These trees shoot up like rockets. The paper mills and plywood factories were happy to pay cash for them. But here's the ecological catch. Eucalyptus is a notorious water pump. It has deep roots and it sucks groundwater at a ferocious rate.
So you have a situation where the satellite photos are showing more green cover, but the water table underground is crashing.
That is exactly what happened, especially in states like Punjab and Haryana. Agroforestry in many places became an ecological disaster. It depleted the soil of nutrients and dramatically lowered the water table. It prioritized the short-term market profit of the timber over the long-term survival of the local aquifer. It's a perfect example of a policy that looked good on a spreadsheet but failed miserably in the real ecosystem.
That distinction between market profit and ecosystem survival seems to be the defining split between the two major forest policies that are mentioned, the 1952 policy versus the 1988 policy.
It's a total 180-degree paradigm shift. The 1952 policy was born in a young, poor, developing nation. The overriding focus was revenue. Forests were seen as a resource mine. We need timber for railways, for industry, for expanding agriculture. The mindset was one of exploitation.
And by 1988,
By 1988, the environmental alarm bells were ringing loud and clear. The policy flipped completely. The focus word moved from revenue to conservation. The policy stopped seeing the forest primarily as a timber factory and started seeing it as a crucial life support system.
what changed on the ground, practically speaking?
Well, it explicitly prioritized maintaining environmental stability and checking soil erosion in catchment areas. But the biggest, most revolutionary change was the human element. It introduced the concept of joint forest management.
Okay, what's that?
It was an admission that the old way wasn't working. It acknowledged that you cannot save a forest by building a fence around it and kicking out the tribal and local people who live there and depend on it. You have to make them partners. You have to give them a stake in protecting it, a share of the benefits.
Speaking of inhabitants, we have to touch on the original non-human inhabitants, the wildlife. The numbers are huge, over 81,000 animal species. And the conservation infrastructure is massive.
It is over 100 national parks, more than 500 wildlife sanctuaries. But the concept from the source that I really want to highlight is the biosphere reserve. This is an important evolution in thinking, moving beyond just a simple park.
How is a biosphere reserve different from, say, a national park?
A traditional national park usually focuses on protecting a single charismatic species. Project Tiger is about saving the tiger. Kaziranga is about saving the rhino. A biosphere reserve, which is part of a global UNESCO program, is much more holistic. It's about conserving the entire genetic diversity of that ecosystem, the plants, the insects, the soil microbes, the water systems, everything.
And it includes people.
Crucially, it includes the human communities living in the buffer zones. It's not about fencing nature off from people, it's about finding a way for them to coexist. So places like Nanda Devi in the Himalayas, the Gulf of Mannar for marine life, or Simlipal in Odisha.
They're designated to preserve the integrity of the whole biological web, not just a few famous animals.
Exactly. Because the threats are relentless. As we cleared those forests for the economy we discussed earlier, we pushed the wildlife into smaller and smaller fragmented ghettos.
Which leads to the inevitable and tragic man-animal conflict that we read about all the time.
It does. It is all connected. You cannot understand the plight of the tiger in the forest without understanding the health of the forest. You can't understand the forest without understanding the rainfall that feeds it. And you can't understand the rainfall without tracking those wind currents all the way back to the Arabian Sea and the great deflection off the Himalayas.
It really is a cascade, isn't it? The wind drives the rain drives the vegetation, and the vegetation drives both the human economy and the survival of the wildlife.
And human policy sits right in the middle of that cascade, trying, and often struggling, to manage that incredible flow of energy without breaking the system.
But let's just zoom out for a final thought. We've tracked the monsoon from the middle of the ocean to the highest mountains. We've seen how that water builds the vast and varied forests of India, and how our national policy has shifted from chopping those forests down for revenue to now trying to conserve them for survival.
But as that eucalyptus example showed us so clearly, the temptation to monetize nature, to go for the quick profit, is always going to be there.
Which leaves us with a very difficult, very provocative question for you, the listener. The source material highlights this clear policy shift toward conservation, but the economic pressures on the ground haven't gone away. So can a developing economy ever truly balance the market value of a tree against its ecological value? Or will the thirst for timber always, in the end, outweigh the thirst for water?
That is the billion-dollar question. And looking at the disappearing groundwater tables in Punjab and Haryana, I'd say nature's already giving us the answer, whether we choose to listen to it or not.
At this point, it is important to understand the geographical logic behind this pattern.
That really is the key phrase, isn't it? Geographical logic. Because
Yeah.
when you look at a map of India, you're usually seeing the political boundaries. Maharashtra, Odisha, Karnataka.
Right, the states.
Exactly. But if you could just peel that layer back and look at the actual geology underneath, you would see a completely different country. A country with this massive divide.
And it really does split the nation into two very different stories.
Yeah.
The source material uses this great analogy of a vault versus, well, everything else.
It's the perfect analogy.
Yeah.
And it's the fundamental premise of India's entire economic geography. First, you have the peninsula, so the southern and central plateau. That is the vault.
And that's where all the treasure is buried, so to speak.
Precisely. It's made of these ancient igneous and metamorphic rocks. Geologically, it's old, it's stable, and it is just absolutely packed with metallic minerals. It's the country's treasure chest.
Which you then have to contrast with the Great Plains and the Himalayan belt.
Yes, and the contrast is stark. They are, for the most part, distinctively poor in metallic minerals. Now, the Himalayas are a bit of a special case.
Oh, how so?
Well, they do have pockets of minerals. You'll find copper, lead, zinc, even some cobalt. But just think about the terrain for a second. It's incredibly rugged. The geology is unstable. It's constantly shifting. It's a fortress.
So even if the minerals are there, getting to them is the real challenge.
It's a huge challenge. Accessing them is so difficult and so expensive that it's rarely economically viable. So for all practical purposes, the peninsula becomes the industrial vault, and the Great Indo-Gangetic Plains become the agricultural breadbasket.
And that brings us to the why of it all. This isn't just a fun geology lesson. This distribution dictates the entire industrial destiny of these regions.
You absolutely cannot fight geology. I mean, the location of these mineral deposits directly dictates where heavy industry is going to rise up. That, in turn, dictates where the major transport networks are built, which then influences urbanization patterns.
So if you want to understand why a certain city is a steel hub, or why railways are so congested in one particular corridor.
You have to look at the rock beneath the soil. It all starts there.
Okay, so let's crack open this vault then. The notes we have categorize India's mineral wealth into 5 pretty distinct belts. But one of them is clearly the heavyweight champion here, the Chotanagpur belt.
Oh, without question. This is the industrial heartland of India. We're talking about the northeastern plateau region. It stretches over Jharkhand, Chhattisgarh, Odisha, parts of Bihar, and West Bengal. If India has an industrial engine, this is the core of it.
The statistics in the source material are, frankly, staggering. It says this single belt holds nearly 100% of the country's kyanite, 93% of its iron ore, and 84% of its coal.
It's a geological jackpot, and the real key isn't just the sheer volume of the stuff, it's the proximity. You have massive deposits of high-grade iron ore sitting right next to massive deposits of high-grade coking coal.
And in industrial economics, that's the dream scenario.
It's the holy grail.
Yeah.
You need that coal to smelt the iron to make steel. When they're practically neighbors, your transport costs just plummet, and a massive steel industry becomes almost inevitable.
And it's not just the big two, is it? The notes also list mica, manganese, chromite, bauxite, copper. It's like the entire periodic table decided to have a conference in this one corner of the subcontinent.
It's a density of mineral wealth that is rare anywhere in the world. But okay, if we move just slightly west from there, you hit the next belt, the Midland Belt.
Right, this one covers parts of Chhattisgarh, Madhya Pradesh, Andhra Pradesh, and Maharashtra.
A very resource-rich area in its own right, but it has a very different profile from Chotanagpur.
Yeah, the notes give it a very specific claim to fame. It has the manganese and bauxite, sure, but it's the only place in India with significant diamond production.
That's the one. Specifically, the Panna district in Madhya Pradesh. It's this sort of sparkling outlier in a belt that's otherwise dominated by very practical industrial utility metals like copper, graphite, and limestone.
Okay, let's keep moving on our map. Let's head south to the southern belt. So, Andhra Pradesh, Karnataka, and Tamil Nadu. The profile seems to change quite a bit here.
It really does. The biggest difference is the lack of coal. The southern belt just doesn't have the massive coking coal reserves of Chotanagpur. The one major exception is lignite, which is a kind of brown coal in a place called Neyveli in Tamil Nadu.
So, no coal. What does it have instead?
It compensates with ferrous metals, lots of high-grade iron ore, plenty of manganese, and of course the one metal that has driven human obsession for millennia, gold.
We're definitely going to circle back to the gold mines later because that is a fascinating story of extreme engineering. But just to finish our tour of the belt, we have the western and the southwestern belts.
Right. The Western Belt, think Rajasthan and Gujarat, is really the non-ferrous hub. This is where you go if you're looking for copper, zinc, and lead. And because of the sedimentary rock formations in Gujarat and offshore near Maharashtra, this is also the petroleum and salt region.
And that last little strip, the southwestern belt, covering Goa, Kerala, and parts of Karnataka.
It's a narrow belt, but geologically very potent. You have very high-grade iron ore in Goa, which is crucial for the export market. But in Kerala, the really interesting story is in the beach sands. You find monazite sands there.
And the source highlights a nuclear connection with those, right?
Yes, monazite contains thorium. India has this very ambitious three-stage nuclear power program, and the long-term goal, the final stage, is to build reactors that can utilize our vast thorium reserves. So those black sands on the beaches of Kerala are, in essence, a future energy bank for the country.
It's fascinating how specialized these regions are. It's not just a random scattershot of minerals, it's all highly clustered. Okay, let's zoom in on what the notes call the economy builder, iron ore.
The foundation of all modern infrastructure.
The notes break it down into 4 types, but it seems like only 2 of them really drive the market.
That's right. You have hematite and magnetite. There are others, like limonite and siderite, but they're economically negligible in the Indian context. Hematite is the star player. It's often called red ochre.
And it's high grade.
Very high grade. We're talking 60 to 70% metal content. It's a massive, hard, compact ore, and you find it in these very old Darwarian rock systems. This is the stuff that builds skylines and bridges.
And its counterpart is magnetite, the black ore.
Correct. Slightly lower metal content, maybe 60 to 65%. But as the name suggests, it has magnetic qualities, which is actually a huge benefit during the beneficiation process, separating the ore from the waste rock.
And you find that mostly in the south.
Predominantly, yes. The southern belt, Karnataka, Andhra, Tamil Nadu, that's magnetite country.
Now, here's a nuance in the data that I found really interesting. We've established that the Chotanagpur belt, specifically the state of Odisha, has the most reserves of iron ore, the biggest bank account. But when you look at actual production...
The leader is Karnataka.
Exactly. Why is that?
It's the classic distinction between what's in the vault and what you're actually spending day to day. Odisha has the largest known reserves, no doubt. But for a variety of reasons, infrastructure, mining policies, historical development, Karnataka is the one writing the checks right now. It accounts for roughly a quarter of India's total production. The Bellary Hospit region there is legendary in the global steel world.
Even so, the notes draw special attention to a particular set of mines in Chhattisgarh, the Bailadilla mines.
Bailadilla is significant for its sheer scale and its method. These are fully mechanized mines in the Bastar district, and they're extracting some of the highest grade hematite in the world. But the logistics are the really cool part.
What do you mean?
Well, it's in a remote, rugged, hilly area. Getting the ore out via rail is difficult. So what they do is they slurry the ore, they grind it up and mix it with water to turn it into a kind of liquid mud, and then they pump it through a pipeline.
A pipeline, like for oil.
Exactly. A pipeline that runs all the way from the mines in Chhattisgarh to the port of Visakhapatnam on the coast.
Just to bypass the difficult terrain. That's incredible.
It's a marvel of infrastructure overcoming geography. And from that port, it's largely exported to Japan and South Korea.
And what about the other mentioned, Kudarmuk in Karnataka?
Kudarmuk means horse face in the local language, after the shape of the peak. These are huge magnetite deposits, and they were primarily developed with a specific geopolitical purpose in mind. There was a major export agreement with Iran. It's a great example of how a single geological deposit can become the basis of a bilateral economic relationship.
But of course, iron is almost useless for modern infrastructure without its essential partner, manganese, the steel support.
Manganese is the unsung hero of the industrial world. It's what makes steel tough and resilient. Without a small amount of manganese, steel is actually quite brittle.
So it's not just for steel, right? The notes mention other uses.
Oh, sure, it's used in bleaching powder, in insecticides, in dry cell batteries, but something like 95% of all manganese mined goes into making ferroalloys for the steel industry. And when it comes to manganese, Odisha takes the crown back from Karnataka.
The data on that is very clear. Odisha produces over 38% of India's total manganese.
It does. The Bonai and Kenduchar districts are the key centers. It just reinforces Odisha's status as this absolute mineral powerhouse. When you have that much of the country's iron and manganese, you effectively control the foundation of the entire construction sector.
Okay, let's shift gears a bit from the heavy ferrous metals to the non-ferrous and precious ones. Let's start with copper, the great conductor. The notes here sound a little less optimistic.
Well, it's a known vulnerability in the Indian economy. Copper is absolutely vital for electrical machinery, for wiring, for mixing with zinc to make brass or tin to make bronze. But India is not self-sufficient, not even close.
So we import a lot of it.
A substantial quantity, yes. We have some production, of course. The Balaghat district in Madhya Pradesh, specifically the Melanchkhan belt, is the leading producer. And the Khetri Singhana belt in Rajasthan is historically famous. It's been mined for centuries. But the domestic demand from a rapidly digitizing and electrifying nation just completely outstrips what our geology can provide.
Which is the complete opposite story for bauxite, where
Yeah.
we seem to be incredibly well positioned.
It is. Bauxite isn't a specific mineral, by the way. It's more of a rock that's rich in aluminum oxides. It's the primary ore for aluminum. And here, Odisha is just in a league of its own.
Dominant again.
Completely. It produces more than half of India's total bauxite. The Kalahandi-Koraput belt is just massive. And this is hugely important because aluminum is seen as the metal of the future. It's lightweight, strong, endlessly recyclable, and India is quite literally sitting on a mountain of it.
Okay, let's talk about the one metal that always captures the imagination, gold. The source material outlines two very different ways India extracts it. There's hard rock mining and then something called placer deposits.
Right. Hard rock mining is exactly what it sounds like. It's the classic image of mining. Drilling and blasting deep into the earth, following these narrow quartz reefs that contain gold. The Kolar goldfields, KGF, and the Huddy goldfields, both in Karnataka, are the prime examples.
The depth figures mentioned for Kolar are terrifying. 3,000 meters.
3 kilometers straight down. Just try to imagine the engineering challenge there. The rock pressure at that depth is immense, but the real killer is the heat.
The geothermal gradient.
Exactly. It gets incredibly hot. Ventilating those shafts, pumping cool air down 3 kilometers and hot air out becomes this massive energy-intensive operation. It drives the cost of extraction through the roof.
And that's what ultimately happened to KGF, right? It just became too expensive.
That's the story. It reached a point of diminishing returns. The gold is still down there, but it would cost more to get it out than the gold itself is worth on the market.
Now contrast that with the other method, the placer deposits.
This is a completely different world. Placer gold is also called alluvial gold. Here, nature has already done the hard part of the mining for you. Over millennia, the river erodes the gold-bearing rock upstream and carries these tiny particles of gold dust downstream.
And they just settle in the riverbed.
They settle in the sands and gravels of the riverbed. The Subarnrekha River in Jharkhand is the most famous example of this.
Doesn't Subarnrekha translate to something like streak of gold?
Line of gold or streak of gold, yes. It's literally named for it. For centuries, local communities have been panning those sands for gold. It's a very low yield, you're not going to get rich doing it, but it also doesn't require a 3-kilometer deep elevator shaft and a massive ventilation system.
This abundance, though, brings us to a really critical concept. The source material calls the paradox of plenty. We have the iron, the coal, the bauxite, the diamonds. But the regions that hold all this wealth, places like Jharkhand, Chhattisgarh, Odisha, are often not the most prosperous parts of the country. Why is that?
This is the central tension of resource economics, not just in India, but all over the world. Having the resource in the ground is one thing. Being able to efficiently extract it and capture its full economic value for the local population is another thing entirely. The extraction sector in India is plagued by a number of inefficiencies.
The notes list a few specific bottlenecks. Obsolete technology is at the top of the list.
Right. In many mines, especially smaller ones, we are still using older methods that lead to a lot of wastage. If your blasting and scooping techniques are inefficient, you might leave a significant percentage of valuable ore mixed in with the rubble, or you generate far more environmental waste than necessary. It's all about the yield you get per ton of earth moved.
And then there's the infrastructure issue. You mentioned the slurry pipeline, which is amazing, but the notes say that's more of an exception than the rule.
It is. Generally, minerals are heavy and bulky. You need heavy-haul railway networks to move them from the mine to the factory or the port. But the rail density in the mining interiors of, say, Chhattisgarh or Odisha is often inadequate. You get these absurd situations where you have huge stockpiles of mine ore just sitting at the pit head because the trains physically can't move them out fast enough.
which creates a bottleneck for the entire industrial chain.
A massive one. It slows everything down.
There's also a very significant social dimension mentioned here: conflict.
It's unavoidable, really. If you overlay a map of India's mineral belts with a map of its tribal populations and its forest lands, the overlap is almost perfect. The Chodhampur and Midland belts, in particular.
And the source material mentions Naxalite activity specifically.
Yes, the source describes these areas as being infested with Naxalites, which creates a very volatile and dangerous security environment. This disrupts production, it endangers the lives of workers, and it certainly deters new investment. It becomes this vicious cycle. The lack of development in the region fuels the unrest, and the unrest prevents the very development that could solve the problem.
And even putting that aside, there's the safety record of the industry itself. The notes are quite grim about the coal mines.
Mining is an inherently hazardous profession. The casualty rates, particularly in coal mining, have historically been very high in India. The source notes that between 2008 and 2011 alone, hundreds of miners lost their lives. Whether it's from roof collapses in illegal rat hole mines or gas explosions in large-scale operations, it is a very high human price to pay for energy security.
And finally, the environmental cost. The conversion of agricultural land and forests into, well, mining wasteland.
It's not just the hole you dig in the ground. It's the fine dust that settles on nearby crops and stunts their growth. It's the pollution of the local water table from mining runoff. And reclamation, the process of turning a depleted mine back into a functioning ecosystem, like a forest or a farm, is incredibly difficult and expensive. Too often, the land is just left as a scarred, barren landscape.
That feels like a very natural transition point, actually. We spent all this time talking about the dead resources underground, the rocks, the metals. But the source material shifts focus pretty dramatically here to the living resources, the biotic wealth.
Right, from the mineral heart to the living skin of the country. India's wealth isn't just in the planet's crust. A huge part of it is walking around on top of it.
The headline number is pretty impressive. India has the largest livestock population in the entire world.
In terms of sheer headcount, yes, it's number one. But there's a very important caveat in the notes. While we have the numbers, the productivity per animal, so the milk yield per cow, for example, is often quite low by global standards. It's traditionally been a volume game rather than an efficiency game.
And interestingly, the MVP of this whole system isn't the cow, as you might expect culturally. It's the buffalo.
The water buffalo is the absolute economic backbone of the Indian dairy industry. It's amazing. India holds 56% of the world's entire buffalo population. They are much hardier than crossbred cows. They thrive on the coarser fodder that's widely available, and crucially, their milk has a much higher fat content.
Which is essential for making things like ghee and paneer and for industrial processing.
Exactly. Breeds like the Murrah and the Patawari are prized assets in the rural economy. They are the quiet, hardworking engines of the dairy sector.
Then the notes have this wonderful phrase for the next animal, the poor man's cow, the goat.
It's a very telling moniker, isn't it? For a landless farmer or a family with just a tiny plot of land, a cow or a buffalo is a huge capital investment. It's too expensive to buy and maintain. A goat, on the other hand, is like a walking savings account.
You can liquidate it easily if you need cash.
Precisely. And they are incredibly adaptable. They eat the kind of scrub vegetation that cattle wouldn't even touch. That's why you see the highest number of goats in a state like Rajasthan. The goat just thrives in that arid, scrubby terrain.
What about sheep? The notes mention a very specific limitation when it comes to their wool.
Yes, we have huge numbers of sheep, but the climate really dictates the quality of the wool. India produces mostly what is known as carpet wool. It's coarse, it's rough, it's great for making carpets and rugs, but not for clothing.
So the fine apparel wool we have to import.
We still have to import most of it, yes.
Yeah.
Things like merino wool. There are ongoing crossbreeding efforts to improve the quality of Indian wool, but generally speaking, hot climates tend to produce hairier, coarser wool on sheep.
So we have the minerals below, we have the animals above. But the entire system that supports both the animals and all the vegetation is, of course, the soil. The source material defines soil in this very poetic way, the interface between the lithosphere and the biosphere.
It's a perfect definition. It is the most critical few inches of material on the entire planet. It's this complex mixture of weathered minerals from a rock, organic matter, or humus, water, and air. Without that thin interface, the rock just stays rock, and complex life doesn't happen.
The text classifies Indian soils into a few major groups. The big four, we can call them. Let's run through them. First up, covering over 43% of the country, alluvial soil.
This is the agricultural engine room. Remember how we said the Great Plains were poor in minerals? Well, this is their wealth. Alluvial soil is essentially just sediment silt, clay, sand that has been deposited by the great river systems, the Ganga, the Brahmaputra, the Indus. It's incredibly deep and incredibly fertile.
Now, the notes make a key distinction here between Kedar and Bangar. What's the difference?
It's a question of age and position relative to the river. Kedar is the new alluvium. It's the soil that's found in the active floodplains right next to the river. It gets a fresh layer of silt deposited on it almost every year during the floods, so it's fresh, fine-grained, and super fertile.
And Bangar.
Bangar is the older alluvium. It's found on the higher ground, the terraces that are above the normal flood level. It's not renewed every year, so it tends to be a bit less fertile and often contains these lumpy, calcareous nodules called kankar.
So Kedar is the fresh, prime real estate, and Bangar is the older, crustier stuff on the higher ground.
That's a great way to put it. For the most intensive farming, you really want the Kedar.
Okay, next up is red soil.
This is the soil that covers much of the fault we were talking about, the peninsular plateau. It develops on those old crystalline igneous rocks. And the red color is, quite simply, rust. It's from a high concentration of ferric oxides.
And is it any good for farming?
It can be. It's very porous and friable, which means it crumbles easily and doesn't get waterlogged. But its main drawbacks are that it's often deficient in nitrogen and it doesn't hold moisture well, so it needs irrigation and fertilizers to really perform.
Then we have the soil with, I think, the most interesting mechanism. Black soil, or rigor.
Ah, the famous cotton soil. This is formed from the weathering of the volcanic lava flows of the Deccan Trap. Its superpower is its ability to hold moisture. It's very rich in clay.
And this is what leads to that amazing property the text calls self-plowing. What does that even mean?
It's a brilliant natural adaptation. When the soil gets wet during the monsoon, it swells up and becomes incredibly sticky. But then during the long dry season, it shrinks dramatically, and these massive deep cracks open up on the surface. Those deep cracks allow air to penetrate deep into the subsoil, naturally aerating it, which is something farmers usually have to do with a plow. Then when the rains come again, the soil swells, the cracks seal up, and it locks all that moisture and air in. It's why this soil is legendary for growing cotton, which needs that very specific moisture profile.
That is fascinating. Okay, and the fourth major type, laterite soil.
Laterite comes from the Latin word later, which means brick, and that name is quite literal. This soil forms in regions that have very high temperatures and very high seasonal rainfall.
And that combination does something strange to the soil.
It does. The intense rain causes a process called leaching. It basically washes all the soluble minerals, like silica, down and out of the topsoil. What gets left behind is a soil that's very rich in the less soluble things, mainly iron and aluminum oxides.
So it's not great for agriculture.
It's terrible for agriculture without massive inputs of fertilizer, but the amazing thing is what happens when it dries. It becomes as hard as stone. In some parts of India, people literally cut the dry laterite soil into blocks and use them to build their houses. It makes for fantastic building material.
I want to highlight one more specific, very niche soil type mention that sounded beautiful. The Kariwas.
Ah, the Kariwas. They are unique to the Valley of Kashmir. They are what geologists call lacustrine deposits.
Meaning they were formed in a lake.
Exactly. Millions of years ago, the entire Valley of Kashmir is a massive lake dammed up by the rising Pir Panjal Range. As the Himalayas continued to rise, the river eventually cut through the dam, the water drained out, and it left behind these thick, flat-topped mounds of sediment. Those are the Kariwas.
And this is the only place in the world where a very specific, very valuable crop grows.
Saffron, the famous Kashmiri saffron. It requires the unique geological chemistry of the Karawas to thrive, almonds and walnuts too. It's a perfect example of how a very specific geological history can create a niche for a unique and high-value agricultural culture.
But just as with the minerals, the notes seem to end on a bit of a warning. There is a crisis brewing in the soil.
Soil degradation. It is the silent environmental crisis. We are losing our most precious resource, topsoil, much, much faster than nature can replace it.
Erosion is the obvious enemy. Wind erosion in the deserts of Rajasthan, water erosion in the steep hills. But the text makes a special point to mention gully erosion in the Chambal Valley.
Yes, the Chumble Badlands or ravines. It is a terrifying landscape of deep, intricate gullies. The water has carved up the land so aggressively that it looks like a mini Grand Canyon in places. It renders huge tracts of land completely uncultivable. It's a severe, almost irreversible form of land degradation where the topsoil is just stripped away and washed down the river.
And then there's this concept of the irrigation irony. The idea that we irrigate to grow more food, but the source says over-irrigation is actually ruining the soil in some of our most productive areas, like Punjab and Haryana.
It is a tragedy of good intentions. In a hot, dry climate, when you flood the land with canal water, a lot of that water evaporates very quickly. But as it evaporates from the surface, it draws water from deep underground up to the surface through capillary action.
Like a wick soaking up oil from a lamp.
A perfect analogy. But that groundwater contains dissolved salts. So the water leaves as vapor, but the salt stays behind. Over years, it builds up and forms this white, salty crust on the surface. It's locally called ray, or color.
And this salinization makes the land infertile.
It makes it toxic to most crops. We are, in a very real sense, salting our own earth in the relentless pursuit of higher yields. It's a massive problem in the command areas of the big canals.
Then what's the fix? The text lists a few conservation strategies.
Well, the first and most important line of defense against erosion is afforestation. Tree roots are what hold soil together. Then there are smarter farming techniques, like contour plowing.
How does that work?
Instead of plowing up and down a slope, which just creates perfect channels for water to rush down and carry away soil, you plow along the contours of the slope across it. Each furrow acts like a tiny dam, slowing the water down and giving it time to soak into the ground.
And for the lands that are already damaged, the ravines and the saline lands.
Reclamation is possible, but it's very difficult and slow. You can add things like gypsum to the soil to help neutralize the salinity. For the ravines, it's a huge undertaking of building small check dams to stop the flow of water and planting specific hardy vegetation to try and stabilize the gullies.
It all sounds like a constant, difficult battle. We extract the minerals, we graze the animals, we farm the soil.
And all of these systems are deeply interconnected. You can't destroy the soil on the hillsides without causing floods and siltation downstream. You can't mine recklessly without destroying the land surface that supports agriculture and livestock. The source material paints this incredible picture of immense natural wealth, these mineral belts that are the envy of the world, these vast alluvial plains that can feed 1 billion people. But it also flashes a very bright warning light.
And the warning is that none of these resources are infinite.
Especially the soil. We tend to think of soil as just dirt, as something that's always there. But fertile topsoil can take centuries, even millennia, to form naturally, and it can be lost in a single heavy monsoon if we strip away the vegetation that protects it.
So, after going through all of this, what's the final takeaway for you?
I think the takeaway is the critical need for balance between what we've called the mineral heart and the living soil. The notes mention that some estimates put nearly 60 to 70% of India's land as facing some form of degradation. The question is no longer just what resources India has, we know it has the vault and the plains, but how long they can possibly last under the immense pressures of modern technology and a growing population.
That is a very sobering thought, and it really encourages you next time you're walking outside just to look down. Is the ground beneath your feet the self-plowing rigor? Is it the ancient, fertile, alluvial soil? Or are you standing on the red, iron-rich crust of the mineral vault? It completely changes how you see the ground.
It certainly does. You realize you're standing on just one part of a massive, living, and very fragile geological story.
At this point, it is important to understand the geographical logic behind this pattern.
Okay, I have to stop you right there. That's a fascinating phrase, geographical logic.
It is.
Because it suggests that the economy, the way a country works, isn't just about policy or markets. It's almost like it's written into the land itself.
It absolutely is.
So when you say pattern, we're not just talking about a trend line on a chart, are we? This feels bigger.
Much bigger. The pattern here is this immense, almost crushing pressure of the Indian population on a very finite amount of land.
Right.
We talk about India as this, rising economic tech giant, and it is.
Yeah.
But the bedrock reality, the thing everything else is built on, is agriculture.
Yeah.
The numbers from our source material are just, well, they're stark. Something like 58.2% of the population depends on farming.
58%. I mean, let's just sit with that for a second. In most developed countries, that number is what, 5%? maybe less?
Single digits, easily.
Yeah.
So you have this situation where nearly 60% of over 1 billion people are tied to the soil for their living.
But, and this is the crazy part from the reading, they're not generating the value. They make up this huge chunk of the workforce. But agriculture is only about 14.4% of the GDP.
And that mismatch, that asymmetry, is the root of the entire pattern. It's the core of the problem.
So you have a huge number of people sharing a tiny slice of the economic pie.
Exactly. The economist Gunnar Myrdal, he really nailed it. He said, it is in the agriculture sector that the battle for long-term economic development will be won or lost.
And he wasn't being poetic.
Not at all. He was being completely literal. If you can't solve the productivity problem for, almost 60% of your people, the rest of your shiny new economy is basically built on sand.
It puts a hard ceiling on how far you can develop. But let me push back a little on this idea of scarcity. I mean, you look at a map of India, it's enormous. The sources put the total geographical area at 328.75 million hectares.
It's huge.
Right, it's a continent-sized canvas. So why does the data feel so claustrophobic?
Because a map can lie to you. It shows you borders, but it doesn't show you viability. You can't farm on Himalayan Glacier. You can't plant wheat in the middle of Mumbai.
Or in the Thar Desert.
Precisely. So when you start digging into the actual land utilization numbers, the picture changes dramatically. The net sown area, which is the land people are actually farming on, it's only about 46.15%.
So less than half the country is actually available to feed the whole country.
Correct, and you can't really expand that number. You've got about 22.5% that's forest, which you need for ecological balance. Another 6.25% is just barren wasteland.
The frontier is closed, basically.
The frontier is closed, the land base is static, but the population relying on it has been exploding for decades. That's the geographical logic right there.
Which brings us to what the text calls the subsistence trap. I think we really need to unpack this because it's a devastating concept. It's not just about being poor, is it? It's about a system that's designed to keep you poor.
It's a vicious cycle. The very character of Indian agriculture is subsistence. That means the farmer's main goal isn't to make a profit. It's not to sell on the global market.
It's just to survive.
It is to grow enough food so that his family does not starve before the next harvest. That's it. That's the entire business plan.
And the reason for that survival mode thinking is the sheer scale, or lack of scale, of the farms themselves. The number that really jumped out at me, and I think this might be the most important statistic we discuss, is the per capita agricultural land.
It's 0.10 hectare.
0.10. Let's try and visualize that for a second. A hectare is about 2.5 acres. So we're talking about a quarter of an acre.
Maybe 2 tennis courts.
2 tennis courts. That is the entire economic engine for one person. It's mind-boggling.
And then you compare it to the world average, which is 0.30 hectare. 3 times bigger.
Mm-hmm.
So when you're working with that tiny of a plot, you have no margin for error.
Well, you can't afford a tractor. It wouldn't even fit.
You couldn't even turn it around. And you definitely can't risk planting some fancy high-value cash crop, because if it fails, you starve. So what do? You stick to the crops of survival.
The food grains. Rice, wheat, millets, pulses. It's not about what's most profitable per square foot.
No.
It's about what provides the most calories per square foot. It's a calorie economy, not a cash economy.
Exactly. And this pressure cooker, so many people on so little land, it means that the physical details of that tiny piece of land become everything. They dictate your entire life. This is what the source material calls the architecture of agriculture.
Right, the physical determinants.
If you own 1,000 acres, you could reshape the land, you can flatten hills, you can bring in water. If you own a quarter of an acre, you are completely at the mercy of the terrain and the weather.
Let's get into that terrain. The source material draws this really sharp contrast. It's not one single farming reality in India. You have, say, the alluvial plains versus a place like the Chambal Valley.
Oh, it's night and day. The alluvial plains, think of Punjab, Haryana, the whole Gangetic Belt. That's the breadbasket. The soil is deep, it's fertile, it's perfect for intensive farming.
Well, it's the ideal.
It's the ideal. But then you go to the Chambal Valley in Madhya Pradesh. The notes describe the land there as guld.
As in, full of gullies, ravines.
Yes. The landscape looks like it's been clawed at by some giant animal. You have these deep ravines from centuries of soil erosion. The text is blunt. It says this land is least conducive for cropping.
So it's basically a geographical lottery.
It's a complete lottery. You can have 2 farmers, both with the same tiny plot of land. One is sitting on the rich soil of the Gangetic Plain. The other is in Shamball, literally watching his farm wash away. Their economic futures are decided before they even buy a single seed.
And layered on top of the terrain is the climate. You can't talk about Indian agriculture without the monsoon. But it's more than just farmers need rain, isn't it? The notes call moisture the absolute dictator.
It is a dictator, and here's why. 55% of all the farmland in India is entirely dependent on rainfall. No canals, no wells, just rain.
That's called rain-fed agriculture.
Right, and what that means in economic terms is that over half of your national food factory has no roof. If the rain comes, you get production. If it doesn't, the assembly line just stops cold.
And the text points to the 2009 drought as a kind of case study in this vulnerability.
2009 was a massive wake-up call. It showed just how fragile the whole system is. When the monsoon fails, it sets off this terrible chain reaction. The soil dries up. The crops don't just yield a little less. They wither and die completely.
And that's not just a farming problem.
No, it's a macroeconomic crisis. Food prices shoot up. You get inflation. And then rural demand for everything else, for tractors, for clothes, for cell phones, it just collapses because the farmers have no money.
Yeah.
The monsoon is, in a very real sense, India's finance minister.
But we can't pin it all on the weather. There's a human element here, a historical one. The source material gets into these institutional factors, especially the history of land tenure. It really seems like the ghost of the British Empire is still walking these fields.
It is, absolutely. You can't understand why the plots are so small today without going back to the 19th century tax systems the British set up. There were three main ones, and each one left a different kind of scar. The most famous, or infamous, was the zamindari system.
That was mostly in Bengal, right? Lord Cornwallis, 1793.
That's the one. The British didn't want the hassle of collecting taxes from millions of individual farmers, so they created a class of middlemen, the zamindars.
Landlords, essentially.
Or tax farmers, really. The British told them, you officially own this land, you pay us a fixed amount of tax every year, and whatever extra you can squeeze out of the peasants working the land is your profit.
That sounds like a recipe for pure exploitation.
It was. It completely destroyed any incentive to invest in the land. The farmer, the tenant, wasn't going to improve the soil because the zamindar would just take any extra profit. And the zamindar, who often lived in a city far away, had no reason to improve the land either. He was just a rent collector. It led to decades of stagnation.
And then there were the other systems, Mahalwari and Ritwari.
Right. Mahalwari, in places like Punjab, made the whole village community responsible for the tax. Raiwari in the south and west was a bit better on paper. The cultivator, the Rayat, owned his land and paid tax directly to the government, but the tax rates were often brutally high.
So these systems set the historical stage. But the thing that's actively chopping up the land today is the law of inheritance.
This is the mechanism that's driving the modern crisis. It's simple math, but with just devastating results.
How'd it work?
In India, traditionally, ancestral land is divided equally among the male heirs. So let's just imagine this playing out. You have a grandfather with, say, 4 hectares, a decent, viable farm. He has 4 sons.
Okay, so each son gets 1 hectare. They've gone from being comfortable farmers to small farmers.
Exactly. Now, let's say each of those 4 sons also has 4 sons, the next generation.
So that 1 hectare is now split into 4, 0.25 hectares each.
Right. In just 2 generations, you've gone from a farm that generates a surplus to a tiny plot that's barely enough for subsistence. That process, repeated millions of times over a century, is the fragmentation of holdings.
And it's not just that the total holding is small, is it? The notes say a single farmer's land might be scattered all over the place.
That's the other part of the fragmentation. Your 0.25 hectare might not be one single plot. It could be 3 or 4 tiny strips of land, sometimes kilometers apart. It makes farming incredibly inefficient.
Which connects back to the technology problem you mentioned.
It's directly linked. The source calls it primitive technology. You can't get economies of scale on a tiny strip of land. You can't justify buying a modern harvester or a tractor, so you get stuck using wooden plows and bullocks, just like your great-grandfather did. It puts a permanent cap on productivity.
Surely the government saw this happening after independence. What about land reforms? That was a huge political promise.
Oh, they saw it, and they tried. The first step was easy abolishing the zamindars. That was done pretty quickly. But the next step, consolidation of holdings, was much, much harder.
Consolidation being the idea of swapping plots so each farmer gets one single contiguous piece of land?
Exactly. It makes perfect logical sense. But in most states, it was a complete failure.
Why? It seems so obvious.
Because land in rural India isn't just an economic asset, it's your identity. It's your connection to your ancestors. A farmer wouldn't want to trade his plot because, this one has the better soil, or my grandfather's tree is on this land.
So an emotional attachment.
A deep emotional attachment and also a deep distrust of the government officials who were supposed to be arranging the swaps. There was a lot of corruption. The only places it really worked on a large scale were Punjab, Haryana, and parts of western Uttar Pradesh.
And it's probably no coincidence that those are the very places that became the heartland of the Green Revolution.
It's no coincidence at all. Where they managed to consolidate the land, modern agriculture could take root. Where they didn't, subsistence farming just continued.
Okay, so we've got fragmented land and unreliable rain. The obvious answer to unreliable rain is to build your own water supply. Let's get into the quest for water irrigation.
Right. And here again, geography is destiny. The text breaks it down into three main methods: canals, wells, and tanks.
And where you are determines which method you use. Let's start with canals. They irrigate about 29% of the area.
If you look at a map of India's canal system, it's almost entirely in the northern plains, and that's pure geographical logic.
What do you need for a canal?
Two things. First, you need a perennial river that has water all year round. The Himalayan rivers, fed by snowmelt, provide that. Second, you need flat, soft, alluvial soil that's easy to dig through. The northern plains have both.
You can't just carve a 1,000-kilometer canal through the hard, rocky Deccan Plateau in the south.
It's practically impossible and prohibitively expensive. So the north got the canals. But this created a whole new set of problems. The notes talk about waterlogging and alkalinity.
This is a huge irony, isn't it? You solve the problem of not enough water, and you create the problem of too much water.
That's what happened.
Yeah.
Due to, over-irrigation and poor drainage, the water table in these areas started to rise. And as it rises, it brings dissolved salts up with it to the surface,
And the water evaporates, leaving the salt behind.
leaving a white crust of salt that poisons the soil and makes it useless for farming. Huge tracts of land in Punjab and Haryana are now dealing with this man-made desertification.
Which maybe explains the huge move towards the second method, wells and tube wells. This is the real giant now, right? 61%.
This is the tube well revolution. It's just exploded from the 1960s onwards, and the big driver was control.
Control.
Yes. If you rely on a canal, you have to wait for some government official to decide when to open the sluice gate. If you have your own tube well, you just flip a switch whenever you want water. It was a massive empowerment for individual farmers.
But it sounds like it also privatized the destruction of a shared resource.
That is the perfect way to describe it. It created a classic tragedy of the commons. Because nobody owns the groundwater, everybody pumped as much as they possibly could. It was a race to the bottom of the aquifer.
And now we're seeing the consequences.
We are. Water tables in Punjab, Haryana, Rajasthan are plummeting by meters every year. Farmers are having to drill deeper and deeper. We are effectively mining ancient water that took thousands of years to accumulate. It's completely unsustainable.
Which brings us to the third method, which feels like the tragic hero of the story, tank irrigation.
The tanks. This was the traditional and, frankly, brilliant solution for the Deccan Plateau in South India.
And why the South specifically?
Again, geology. The hard rock underneath means you can't easily dig canals, and digging deep wells was very difficult. But the landscape is naturally undulating. It has lots of dips and depressions.
So they just built walls to trap the rainwater in those natural bowls.
For centuries, that's what communities did. They'd build a small earthen dam, an embankment across a slope and capture the monsoon runoff. It was a local, sustainable, community-managed system.
But the data shows it's basically collapsed. It went from providing 17% of irrigation in the 1950s to less than 5% today. Why would you abandon a system that works so well with the local geography?
A combination of factors. The convenience of the electric pump for tube wells was a big one. But also a social breakdown. A tank requires constant community effort. You have to desilt it every year. You have to maintain the dam. As village life changed, that collective responsibility it eroded.
It's a pattern we see over and over, a shift from a community-managed, low-impact system to an individual-managed, high-extraction one.
And that takes us to the ultimate extraction industry. We've been talking about the energy from the soil in the form of food. Now we have to talk about the energy that powers the machines, the fossil fuels.
Let's pivot to powering the nation. This is where the story moves from farms to factories. And just like with agriculture, the location of the resources is a matter of geological destiny.
Absolutely. The spine of India's commercial energy system, we're talking 67% of it, is coal.
The industrial black gold. The source material makes a really important distinction, though, between two different types of coal, separated by hundreds of millions of years, Gondwana and Tertiary.
And this ancient geology has massive modern economic consequences. 98% of India's coal is this old Gondwana coal. It was formed about 250 million years ago when this part of the world was a supercontinent.
And where do you find it?
You find it in old river valleys, the Damodar Valley, the Mahanadi, the Godavari. If you put that on a modern map, you're talking about the states of Jharkhand, Odisha, West Bengal, Chhattisgarh. That eastern belt is the Ruhr of India. It's the engine room.
But there's a huge geographical logic problem here, isn't there? The coal is all in the east. But a lot of the big industrial cities and factories are in the west, in Gujarat and Maharashtra, or in the north, around Delhi.
You've just identified one of the biggest bottlenecks in the entire Indian economy. We have to physically move millions and millions of tons of coal across the country. It puts an incredible strain on the railway network. A massive chunk of all freight traffic on Indian railways is just coal trains, chugging from the mines in the east to the power plants in the west.
And the quality of the coal itself makes that problem even worse. The notes mention it has high ash content.
Yes. Indian coal is, to be blunt, not great quality. It's dirty. It can have an ash content of 30, even 40%. That means for every truckload of coal you burn, nearly half of it is just unburnable rock and dirt.
So you're spending all that fuel and clogging up the railways just to transport waste across the country?
It's incredibly inefficient. And this becomes a critical problem for the steel industry. They need a special high-grade type of coal called coking coal.
And we don't have much of it.
We have very little. So even though India has some of the largest coal reserves in the world, our massive steel industry is dependent on importing coking coal, mostly from Australia.
Okay, what about the other 2%, the tertiary coal?
That's the young stuff, only about 15 to 60 million years old. It's got more moisture, less carbon, it's lower quality. But its importance is all about location, location, location.
Where is it?
It's found in the frontier areas where you don't find Gondwana coal places like Assam in the northeast, Kashmir, Rajasthan, and most importantly as lignite or brown coal in Tamil Nadu at a place called Neyveli.
So Neyveli becomes this critical energy hub for the South.
Exactly. It allows Tamil Nadu to have its own source of fuel for thermal power plants without having to drag coal all the way from Jharkhand.
Okay, let's move from solid to liquid. Petroleum.
Liquid gold? The geology changes completely here. You're looking for oil trapped in sedimentary rock formations. For the longest time, the only place we had it was in Assam, the old fields at Digboy and the Harkatia. But the real game changer was finding Bombay High in the 1970s.
That's the offshore field.
Yes, about 176 kilometers off the coast of Mumbai. A single offshore field that today accounts for something like 65% of India's entire domestic oil production. It shifted the whole energy map of the country towards the west coast.
But once again, you have the tyranny of distance. The oil is offshore in the west or in the far, far east in Assam. The big refineries and the customers are inland in the north.
And the solution to that is the pipeline. The source mentions the HBJ pipeline Hazira Vijaypur Jagdishpur. This isn't just a pipe. You should think of it as a major artery for the national economy.
What does it connect?
It takes natural gas from the west coast and carries it hundreds of kilometers inland to power fertilizer plants and refineries in the heartland, in places like Mathura and Panipat. Without that pipeline, the fertilizer factories in Uttar Pradesh don't run.
Which means the farmers in the breadbasket don't get fertilizer.
Which means food production falls. It's all connected. The geology of the West Coast directly impacts the agriculture of the North Gangetic Plains.
And what ties this all together is electricity generation. We have the thermal plants burning all that coal, but then there's hydroelectricity. Nehru called the big dams the temples of modern India.
Hydro is the most direct conversation with geography you can have. You need two things: uneven terrain, like mountains and waterfalls, and a reliable flow of water. This gave us huge projects, like the Bakra Nangal Dam on the Satluj River.
And that dam basically powered the Green Revolution in Punjab and Haryana.
It did. It provided the cheap, reliable electricity needed to run all those new tube wells. Another great example is the Damodar Valley Corporation. The Damodar River used to be called the Sorrow of Bengal because it flooded so catastrophically every year.
They tamed it.
They built a series of dams, turned a geographical liability into an asset, and generated huge amounts of power in the process.
But hydropower has a built-in vulnerability, doesn't it? It's tied to the same thing as the farmers.
It's tied to the monsoon. If you have a weak monsoon, the reservoirs behind the dams don't fill up, and that means power generation drops. and it drops at the exact moment when farmers need electricity the most to run their pumps to make up for the lack of rain.
So we come full circle, back to the energy crisis. The source material is pretty clear here. Demand is constantly outstripping supply. You have brownouts, industries forced to shut down, the fossil fuels are running out. We need a new plan, a new logic.
We need non-conventional energy. The logic of the last century was to dig down into the earth. The logic of this century has to be to look up at the sun and out towards the wind.
Let's start with solar. The potential here just seems immense for a tropical country like India.
The geography couldn't be better. The country gets something like 5,000 trillion kilowatt hours of solar energy every single year. It's an insane amount. But the real revolution here might not be the giant solar farms, but the small-scale rural applications.
You mean going back to that farmer on his .10 hectare?
Exactly. If you can put a small photovoltaic panel on the roof of a hut in a remote village, you change everything. They can have light at night. They stop burning firewood for cooking, which saves the forests. They stop burning cow dung, which is a major source of indoor air pollution and health problems. It's energy security at the most basic level.
And then there's wind energy. This feels much more location-specific.
It is entirely dependent on geography. You need places with steady, strong winds. India actually ranks 5th in the world in installed wind capacity, but it's very concentrated. Tamil Nadu, down in the south, is the absolute superpower, especially around a place called Mupendal. And then you have the coast of Gujarat.
It's like natural wind tunnels.
That's exactly what they are.
Yeah.
Places where the topography funnels and accelerates the wind.
What about bioenergy? This feels like it fits the whole agricultural picture perfectly.
It is the ultimate rural solution. India has the world's largest population of cattle. That means it has a virtually endless supply of cattle dung, of organic waste.
Turning waste into wealth.
You take that waste, put it in a simple biogas plant, and it produces methane gas for cooking and lighting. And the best part, the leftover slurry is a fantastic, nutrient-rich organic manure that you can put right back on the fields.
That closes the loop.
It completely closes the loop. It solves an energy problem, a sanitation problem, and a fertilizer problem all in one go. The state with the biggest potential here is Uttar Pradesh, simply because of the sheer density of livestock.
And just to round it out, the sources mention the really niche stuff, tidal and geothermal.
Right, using the massive tides in the Gulf of Kampat and Kash, or tapping into the Earth's natural heat in places like the Puga Valley in Ladakh or Manikarn in Himachal. These are small, but they show that every single part of India's diverse geography has some kind of energy potential if you can find the right technology to unlock it.
So we've covered a lot of ground. We've gone from the microscopic view of that one farmer on his tiny, fragmented plot,
All the way up to the macroscopic view of the national power grid and moving millions of tons of coal.
and the pattern that emerges, the geographical logic. It seems to be one of constant negotiation.
That is the perfect word for it. The Indian economy is a constant, difficult negotiation with its own physical reality. The farmer has to negotiate with the monsoon. The civil engineer has to negotiate with the terrain to build a canal. The industrialist has to negotiate with the low quality of the coal.
And the stakes of that negotiation are just getting higher and higher. You have this massive growing population that wants more food, more electricity, more everything, and it's all pushing up against the hard limits of the land and its resources.
That heavy pressure of population is the force that's driving this whole story. It's what caused the land to fragment. It's what forced the unsustainable drilling of millions of tube wells. And it's what's now forcing this urgent, almost desperate push into renewable energy.
Which really brings us to the final thought here, the so what, for you, the listener. Why does all this geography matter?
It matters because it reframes the entire challenge. The challenge for India isn't just economic growth in the abstract, it's conservation. The source material ends on this really powerful idea. Energy saved is energy produced.
In a system that is this constrained, efficiency isn't just a buzzword to save money.
It's a core survival strategy.
That is a really provocative place to leave it. We tend to think of technology as the thing that will save us, that will just invent our way out of scarcity. But what this deep dive into the geography suggests is that maybe you can't just consume more, you have to consume smarter.
The fundamental question India is trying to answer right now in real time is this. Can our technology outrun the limitations of our geography? Or will the sheer weight of the population ultimately force a complete change in how we live?
A fascinating look at the very bedrock of an economy. Thanks for taking us through that.
It was my pleasure.
And for you listening, the next time you read a headline about India's GDP growth or a new tech startup or a drought in the Deccan, just remember that geographical logic that's humming away underneath it all. The map is always talking. We just have to learn how to listen. Until next time.
At this point, it is important to understand the geographical logic behind this pattern.
It absolutely is. I mean, you can't understand the story of modern Indian agriculture without first understanding the ground it's grown on. It's the master key to everything that follows.
Right, and what's so compelling in the sources is how they encourage you to, forget the political map of India for a moment.
Exactly. Forget the state borders, Punjab, Haryana, Tamil Nadu.
And instead, look at the geological map, the blueprint of the rock and the soil.
Because that blueprint, that geology dictates everything. It dictates how a farmer gets water to a plant. And in a monsoon country like India, well, water is destiny.
It really is. The source material kind of sets up this dramatic split, this tale of two Indias, based entirely on what's under your feet. You have the Great Northern Plains on one side.
And the old rocky peninsular plateau on the other. Two completely different worlds facing completely different engineering challenges when it comes to water.
So let's start with the north, the Satluj-Ganga Plains. The sources paint this as basically an engineer's dream.
Oh, absolutely. If you were tasked with designing a massive irrigation system from scratch, this is where you'd want to do it.
Why? What makes it so perfect? Is it just that it's flat?
The flatness is a huge part of it, yes. The source material calls it low-leveled relief. But it's more than that. It's the depth and the softness of the soil. You have to imagine millions of years of the Himalayas eroding, washing down silt, sand, and clay.
And filling up this massive basin.
Exactly. It's a gigantic trough filled with soft alluvium. And that softness is the key. It means you can dig, you can move earth easily. You're not going to hit a sheet of granite 10 feet down.
Which is why we see those iconic sprawling canal networks there. You look at a map in Uttar Pradesh, Punjab, Haryana, they're just crisscrossed with these blue veins.
That's the logic. You take these massive perennial rivers coming out of the Himalayas, rivers that flow year-round because of snowmelt, and you can carve channels out from them, guiding the water across hundreds of kilometers of flat, soft land.
And the sources mention this pattern repeats, but on a smaller scale in the coastal deltas too.
Right, the Mahanadi, Godavari, Krishna, Kaveri deltas. It's the same principle. A reliable river-dropping sediment and creating flat, soft, fertile land. That's where you can build canals. You can't just decide to build a canal through, a rocky, uneven plateau. It's geographically prohibitive.
But here's where the story takes a fascinating turn. Because I think most people, when they picture Indian farming, they picture those canals, it feels very, monumental, like a big state-run project.
Yeah, a mid-century infrastructure dream, yeah.
But the data in our sources shows a quiet revolution has happened. The canals, while important, are no longer the dominant force. They've been overtaken by something much smaller, much more individual.
And tube wells.
And the numbers are just staggering. The sources say wells and tube wells now account for over 61% of the total irrigated area in the country.
61%. It's a landslide.
So the big question is why? Why did this shift happen? If you're a farmer and there's a government canal flowing right past your field, why would you go to the expense and effort of drilling a hole in the ground?
It comes down to a combination of geology and autonomy. Let's stick with the geology first. Remember that soft alluvial plain we were talking about?
Yeah, the Himalayan silt.
Well, that soft ground isn't just easy to dig canals in. It's also incredibly easy to drill a well in. And because it's so deep and porous, it acts like a colossal sponge that's been soaking up water for millennia. You're literally standing on your water source.
So the water's right there, accessible.
It's right there. You don't have to drill through a kilometer of hard rock to find it. So the installation is relatively easy. But that's only half the story. The other half is autonomy.
The control factor.
The control. Think about what it's like to rely on a canal. You are part of a massive bureaucratic system. The water is released on a schedule. Maybe your turn is on Tuesday. Maybe the official is late. Maybe the guy upstream with more influence takes more than his share, and you're left with a trickle.
It's public transport. You have to wait for the bus, and it might not show up on time.
That is a perfect analogy. A tube well, on the other hand, is your own private car. You have a pump in your field connected to your power source. You want water. You flip a switch.
Water on demand.
Water on demand. And that control, that ability to give your crop a drink the exact moment it needs it, is worth a huge premium to a farmer. Even though it's more expensive to operate, you're paying for diesel, you're paying for electricity. That reliability is priceless.
But this entire drilling revolution, as you call it, it hits a wall when you go south.
A literal geological wall. When you move into the peninsular plateau, so large parts of Andhra Pradesh, inland, Tamil Nadu, Karnataka, you're on some of the oldest, hardest rock on the planet.
Deccan traps, granite.
Exactly.
Yeah.
Ancient crystalline rock. You can't just drill a tube well with a cheap rig. It's incredibly difficult and expensive. And you also can't easily dig long canals because the terrain is all rolling hills and rocky outcrops.
So geography has you in a corner. You can't dig down and you can't dig across. What's the solution?
You look up, you look to the sky, and you catch what it gives you.
The rain?
The rain. And this is where we see the third major type of irrigation, the tank. And we should probably clarify for the listener, we're not talking about military vehicles.
Right. The sources describe them as, what, artificial reservoirs? Basically man-made ponds or small lakes?
That's a great way to put it. They're ancient, ingenious pieces of engineering. You find a natural depression or a valley where a stream flows, and you build an earthen wall, a bund across it.
Trap the runoff.
You trap the monsoon runoff. When the rains come pouring down, the tank fills up, and you've created a reservoir that can hopefully last you through the dry season. It's a brilliant adaptation to a hard rock environment where you can't access groundwater easily.
But there's a huge vulnerability baked into that system, isn't there? Something the northern farmer with his tube well doesn't have to worry about nearly as much. The source material calls it the problem of seasonality.
It's the Achilles heel of the whole system. The rivers in the south, they're almost all rain-fed. There are no Himalayan glaciers melting in the summer to keep them flowing.
So in the hot season, they just dry up.
They shrink to a trickle or dry up completely, which means your whole irrigation system, your tank, is entirely dependent on one thing. A good monsoon, if the rains fail, the tank doesn't fill, and you have nothing.
The northern farmer with a canal tied to a snow-fed river has a buffer. The farmer with a tube well is sitting on an ancient aquifer. But the southern tank farmer is gambling everything on one season's rainfall.
It's a tightrope walk. And it also means the command area, the amount of land you can reliably irrigate from a tank, is much, much smaller and less reliable than what a canal or tube well can support.
So this is the stage. This is the setting for our story. A north that is geologically blessed, soft, flat, water-rich, and a south that is rocky, rugged, and at the mercy of the seasonal rains. This geological lottery, as the sources imply, basically predetermined who's going to win and who's going to lose in the next great upheaval.
The Green Revolution, the engine of change.
And we have to be clear about the stakes here. When we say green revolution, it's so positive and gentle. But this wasn't just about growing bigger vegetables. This was a national survival strategy.
It was a response to a crisis. The sources pinpoint the mid-1960s as the start. India was facing massive food shortages, living, as they said, ship to mouth, dependent on food aid from the U.S. Famine was a real looming threat.
And the response wasn't just an evolution. It was a complete reboot of the entire agricultural operating system. And we have to give credit to the architects. The sources named Norman Borlaug, the American agronomist who's seen as the global father.
And crucially, Dr. M.S. Swaminathan, the Indian geneticist. Swaminathan is so important because he understood you couldn't just, copy-paste what Borlaug had done with wheat in Mexico and drop it into India.
That had to be adapted.
It had to be adapted to Indian soils, to the climate, to the day length. He was the one who made it work on the ground. But I think we need to dig into what this revolution actually was.
Yes. There's a phrase in the source material that I think is the single most important concept for understanding this whole deep dive. It's called package technology.
That's it. That's the core insight. Because there's this common misconception that the Green Revolution was just about inventing a super seed.
Like magic beans.
Right. You just throw these new seeds in the ground and suddenly you get 3 times the food. It's a nice story, but it's completely wrong.
It wasn't a silver bullet. It was a system.
It was an integrated system. The analogy I like is building a high-performance race car. The high-yielding variety, or HYV seed, is your powerful new engine. But if you drop that engine into a regular car without upgrading the transmission, the brakes, the fuel system...
The whole thing falls apart or explodes.
Exactly. The package was all or nothing. You needed the HYV seeds, yes. But you also absolutely needed assured irrigation, chemical fertilizers, pesticides, and down the line, machinery to handle the massive new harvest. If any one of those components was missing...
The whole package fails.
Yeah.
The farmer is worse off than before.
Catastrophically worse off.
Okay, so let's break down that package. Let's start with the star of the show, the seeds themselves. The revolution started with wheat. these Mexican dwarf varieties, and then it expanded to rice with this famous IR8 variety they called miracle rice.
They did, and it felt like a miracle at the time.
So beyond the obvious, it produces more grain. Why were these seeds so attractive to farmers? What were the technical merits that made them so compelling?
Well, the biggest one, and it's one that often gets overlooked in the discussion about yield, was actually about time.
Time.
How so? The short duration of the crop cycle. This was an absolute game changer. Your traditional local variety of wheat or rice might take, say, 130 to 150 days to grow and mature.
4 or 5 months.
Right. Long season. These new HYV seeds were bred to mature in 100 to 110 days.
So you're shaving off a month, maybe even more, from the growing cycle. Why is that 30 or 40 days so critical?
Because that month is a window of opportunity. It's the difference between getting one crop per year from your land or two. It allowed for what's called multiple cropping.
Ah, so you harvest your wheat, and you still have enough time left in the season to prepare the field and plant a second crop, maybe rice or something else.
Precisely. You are effectively doubling the productivity of your land without buying a single extra acre. You're making the land work harder. Before this, for much of the year, the land would just lie fallow. Now, the factory is running a double shift. That's where the real explosion in food grain production came from.
It's like a time machine for agriculture. You're literally manufacturing an extra month in the growing season.
That's a great way to think about it. Then you have this other concept the sources mention, scale neutrality.
This was the big selling point, right? The idea that this technology was democratic.
In theory, yes. The biology of a seed is neutral. The seed doesn't know if it's being planted on a huge 100-acre farm or a tiny 1-acre plot. It has the same genetic potential to grow in either place.
So the promise was that this would lift all boats. The rich farmer and the poor farmer would benefit equally.
That was the promise. The seed itself was scale neutral. Unfortunately, as we'll see, the package required to make it grow was anything but.
We'll definitely get to that, but there's one more merit listed that seems almost paradoxical. Water efficiency.
Yeah, that one requires a bit of nuance, because in a minute we're going to talk about how incredibly thirsty these crops are.
Right.
But on a purely biological cellular level, they are more efficient. They convert each liter of water they absorb into more grams of grain than the traditional varieties did. They're better factories.
So more bang for your buck, water-wise.
More grain per gallon, yes. The catch, and it's a massive catch, is that they need that water delivered with the precision of an IV drip. They have no tolerance for error.
And that leads us straight into the hidden cost, the dark side of the miracle. The sources call them the hidden constraints. Because after the initial excitement, farmers started to realize these miracle seeds were, well, high-maintenance divas.
That's the perfect word for it. They were divas. Let's break down that diva behavior, starting with what you just mentioned. The text calls them thirsty.
So if they're technically water efficient, what's the problem?
The problem is timing and reliability. Think about the old traditional Indian crops, the millets, the old strains of wheat. They had evolved in that environment for thousands of years. They were tough. They were like, a rugged off-road vehicle.
They could handle bumps in the road.
Exactly. If the monsoon was a week late, they'd struggle a bit, maybe wither, but they were resilient. When the rain finally came, they'd bounce back. They were built to survive the unpredictability of nature.
And the HYV seeds.
They're Formula One race cars. Incredibly high performance on a perfect track, but you hit one pothole and the whole thing shatters. They have zero resilience.
The sources have this terrifying statistic about wheat.
It's unbelievable. It says that if you miss the crucial watering window during what's called the crown root initiation stage, which happens precisely 21 days after you sow the seed, your final yield can drop by 50%.
50%. Half your crop is gone because you were a day or two late with the water.
Gone. The plant essentially gives up on producing a full head of grain. So put yourself in the shoes of a farmer. Can you rely on the rain to arrive exactly 3 weeks after you plant your field?
Never. It's impossible.
It's a gamble you can't afford to take. And that's the moment where the farmer realizes, I cannot grow these seeds with rainfall. I must have my own controllable source of irrigation.
I must have a tube well.
You must have a tube well. The Green Revolution didn't just encourage the tube well, it mandated it. It was a tube well revolution in disguise. It forced farmers to divorce themselves from nature's schedule and create their own artificial one.
Okay, so they're thirsty, or rather they're picky drinkers.
Yeah.
Then there's the other side of the coin. They're hungry.
Insatiably hungry. And again, this comes back to how they were designed.
The dwarf structure.
Right. They were bred to be short and have thick, stiff straw. The old tall varieties had a problem. If you gave them a lot of fertilizer, they'd grow very tall and leafy, but the grain head would get so heavy the stalk would snap and fall over. It's called lodging.
So all that fertilizer was wasted.
Wasted. The dwarf plant, however, stays short and stocky. It can physically support a much bigger, heavier head of grain. It channels all that energy from the fertilizer directly into making seeds, not useless stalk.
But to build that massive grain head, it needs the raw materials.
It needs a feast. The natural fertility of the soil, the organic matter that had sustained agriculture for centuries, it just wasn't enough. It was like packing a small lunch for a marathon runner.
The soil's pantry was emptied very quickly.
Instantly. So farmers had to start force-feeding the plants with chemical fertilizers. We're talking about massive amounts of NPK, nitrogen, phosphate, and potash.
And the numbers in the source material comparing the heartland of the Green Revolution, Punjab, with a state that was largely left out, like Arunachal Pradesh, they're just mind-boggling.
They really are. Punjab's fertilizer consumption is around 225 kilograms per hectare.
225.
And Arunachal Pradesh, about 5 kilograms per hectare.
It's not even the same sport.
It's a different planet. It tells you that the soil in Punjab is no longer a living ecosystem providing nutrition. It's become an inert medium, a physical substrate, whose only job is to hold the plant's roots while it's fed an artificial chemical diet from a bag.
And you create this whole new environment in the field. You have these very dense, lush, green plants, pumped full of nitrogen, often withstanding water from the irrigation.
You've just described paradise.
For the farmer.
For insects and fungus, you've created a hot, humid, sheltered microclimate right at the base of the plants. It's a 5-star hotel and an all-you-can-eat buffet for pests that previously weren't a major problem.
So the Green Revolution inadvertently rolled out the welcome mat for a massive pest explosion.
It amplified the problem exponentially. Traditional farming had wider spacing. The wind could move through the crops, keeping them dry. These HYV fields were dense, humid jungles. So, of course, the package had a solution for that, too.
Pesticides.
More chemicals. Herbicides for the weeds, insecticides for the bugs, fungicides for the rot. And you see how this cascade works. Each solution creates a new problem that requires another expensive purchased solution.
The seed needs the water needs the tubal, the seed needs the fertilizer creates the pests need the pesticide.
And every single one of those things costs money.
Which brings us to the capital barrier.
Yeah.
This is the point where farming stops being about subsistence,
Yeah.
about, growing what you eat and saving your own seeds for next year.
And it becomes agribusiness. It becomes a capital-intensive enterprise. You need cash up front before you even planted a seed. You need it for the seeds themselves, which were often hybrids you had to buy fresh every year. You need it for the bags of NPK. You need it for the diesel to run the pump and the tractor.
For a small farmer with very little savings, where does that cash come from?
That's the million-dollar question. And the answer, as the source material points out, was often the credit trap.
The village moneylender.
Exactly. The big, established farmers could go to a bank. They had land titles for collateral. They knew how to fill out the forms. But the small, marginal farmer, the banks often wouldn't touch them. So they had to go to the informal lenders.
Who charge exorbitant interest rates.
Crippling rates. And then you're on a treadmill. If your crop does well, you might just about pay off the loan. But if you have one bad season, a pest attack, a hailstorm, a drop in market prices, you're ruined. The debt balloons. And that's when you lose your land.
So that beautiful idea of scale neutrality.
It was a myth. The seed might have been scale neutral, but the economic system required to grow it was brutally biased towards those who already had capital and land.
Which leads us directly into the massive social consequences of this. The Green Revolution didn't just remake the fields, it remade the village. It created a society of clear winners and a lot of losers.
A huge number of losers. And the divide happened on 2 levels. Between regions and within the village itself, between classes.
Let's start with the regional inequality. We've already touched on this, but the sources make it clear the revolution didn't happen everywhere.
Not at all. Because the package was so dependent on reliable irrigation, it naturally concentrated in the areas that already had it. So, Punjab, Haryana, Western Uttar Pradesh, the places with the canals, and the easily accessible groundwater.
They had a head start.
A massive head start. So these regions just took off, their economies boomed. Meanwhile, the vast rain-fed tracts of India in the East, in the center, were largely left behind. They didn't have the water, so they couldn't adopt the package.
And this created a huge development gap within the country itself.
A chasm. You had what was effectively a first world agricultural economy in the Northwest and a struggling traditional third world one almost everywhere else. But the story gets even more granular.
The class divide. Even within a successful Green Revolution village, it wasn't a success for everyone.
Far from it. The outline breaks it down perfectly. You have the big farmer, the small farmer, and the tenant farmer. And their fates were completely different.
Let's start with the winner, the big farmer. Who was he?
The big farmer was the person who started with, say, 10 acres or more. He had enough land to use as collateral to get a proper bank loan at a reasonable interest rate.
So he could afford the whole package from day one. The tractor, the best seeds.
He could, and crucially, he had a buffer. He had the capacity to take a risk. If one crop failed, it was a setback, but it wasn't starvation. He had savings. He could survive.
And when his crops didn't fail, the profits were enormous.
Life-changing. And what did he do with that new wealth? He reinvested it. He bought the latest thresher. He bought more land, often from his struggling smaller neighbors who were falling into debt. And he invested in his family's future, sending his children to private English medium schools in the cities, setting them up for white-collar jobs. A new rural elite was born.
And the smaller marginal farmer, the person with maybe 1 or 2 acres?
Their story is one of stagnation and struggle. They were caught in a terrible bind. They saw the huge yields their big neighbors were getting, so they knew they had to try and adopt the new technology to keep up.
So their costs went up. They had to buy the seeds and the fertilizer.
Their costs shot up, but they couldn't achieve the same economies of scale. Buying a tractor for a 2-acre farm makes no economic sense. It sits idle most of the year. So their yields went up a bit, but their profits were marginal. They were living constantly on the edge.
One bad season away from disaster.
One pest attack, one family illness, one failed crop, and they were forced to go to the moneylender. And that was often the beginning of the end.
But there's a third group that the source material says got hit the hardest. The ones who lost everything? The tenant farmers.
Their fate is the cruelest irony of the Green Revolution.
Why? How did it affect them so badly?
Well, think about the system before. Land was valuable, but it wasn't a gold mine. A landlord with a lot of land was often happy to lease it out to tenant families who would farm it and give him a share of the crop, say 50%.
It was a stable, if unequal, arrangement.
It was. The landlord got an income without doing any work, and the tenant family had land to farm and a place in the village society. But then, the Green Revolution happens, and suddenly that land is capable of producing 3 times as much grain.
That land just became incredibly profitable.
It turned from dirt into gold. And the landlords, who were often the big farmers we just talked about, did the math. They realized, why should I lease this out and only get 50% of the profit? I can buy my own tractor, hire a couple of laborers for cheap during the harvest, and keep 100%.
So they kicked the tenants off the land.
Mass evictions. The sources call it a process of reverse tenancy. Land that had been farmed by the same families for generations was suddenly taken back by the owners for self-cultivation. Or, if they didn't evict them, they'd jack up the rent to astronomical levels, arguing that it was now high-yield land.
And this created a whole new class of people in the village.
The landless laborers. Families who were once farmers were now reduced to selling their daily wage, competing for scarce work.
And speaking of labor, you mentioned earlier that in the very beginning, the Green Revolution actually created more jobs.
It did for a short time. It was a temporary boom. Because you were planting 2 crops a year, you needed more hands for weeding, for applying fertilizer, for harvesting. For a brief period, labor demand went up.
But that didn't last.
It didn't last because of mechanization. Remember, the big farmer getting richer, the first thing he does after buying more land is buy a combine harvester.
A single machine that can do the work of dozens of people.
And that was the death knell for rural employment. The tractor had already replaced the plowman, the thresher replaced the people who separated grain from stalk, the harvester replaced everyone else.
And this triggered that massive wave of migration that we still see the effects of today.
Absolutely. What do you do when you are landless and there are no jobs in the village? You move to the city. You move to the slums of Delhi or Mumbai looking for work on a construction site. The village economy, which once had a place for everyone, now only had a place for the landowner and his machines.
The sources mention this broke the traditional social fabric, something called the Jajmani system.
Right. The Jajmani system was this old network of reciprocal duties. The farmer gave grain to the blacksmith, who in return mended his plow. The potter got grain, the carpenter got grain. It was a community built on exchange,
And it was replaced by what?
a cold, hard cash economy. Why barter with the local blacksmith when you can just buy a new part from a shop in town? The social glue dissolved. The gap between the newly rich landowners and the newly impoverished landless laborers grew into a chasm. And as the sources note, this led to a rise in social tension, conflict, and sometimes violence in the countryside.
It's a heavy toll, a deeply divided society. And that's just the human cost. We haven't even gotten to the environmental cost.
The ecological bill has come due. And reading through this section of the source material, it really does feel like watching a slow-motion catastrophe.
Because it's the story of us trying to fight geography. And in the long run, geography always wins.
It always wins. Let's start with the most obvious consequence, the water crisis.
We're back to Punjab and Haryana, which geologically are semi-arid regions. They don't get a huge amount of rainfall. They should be growing crops like wheat, maize, millets.
Crops that are suited to that climate. But driven by government policies like the minimum support price, farmers were incentivized to grow one crop above all others.
Rice.
Paddy. Growing rice in Punjab is an act of ecological warfare.
It's like trying to grow a rainforest in the desert.
That's barely an exaggeration. Rice is essentially an aquatic plant. It loves to have its feet wet. It's traditionally grown in floodplains like Bengal or the Mekong Delta. To grow it in semi-arid Punjab, you have to create an artificial wetland in every single field.
And that water has to come from somewhere.
It comes from the ground, pumping relentless amounts of groundwater from those deep aquifers we talked about.
And that aquifer is not a bottomless tank.
It's a fossil resource in many ways. The source material uses the term dark zones, especially in Haryana. These are areas where the rate of withdrawal is so much higher than the rate of recharge from rainfall that the water table is in freefall. We are mining ancient water that took thousands of years to accumulate, and we're using it in a single season to grow a crop that shouldn't be there.
And what happens when that water is gone?
The desert reclaims what was always its own.
So the water below is vanishing. What about the soil on the surface? The text uses these local terms, calor or thur, to describe a process called salination. Can you break down the chemistry of that? It seems so counterintuitive that adding fresh water to a field can make it salty.
It does seem strange, but it's simple physics. In a hot, dry climate like northwest India, the rate of evaporation is incredibly high.
The sun is just baking the earth all day.
Exactly. So when a farmer floods his field with irrigation water, some of it sinks down into the soil. But then the intense sun starts pulling that moisture back up to the surface to evaporate.
It's like a wick in an old kerosene lamp, drawing the fuel up.
That's the perfect analogy. It's called capillary action. The water moves up through the tiny pores in the soil. When it reaches the surface, the pure water, H2O, turns into vapor and disappears into the air. But the water was never pure. It had tiny amounts of dissolved salts that it picked up from the soil particles.
And the salt can't evaporate.
The salt is a solid. It gets left behind. And this happens irrigation after irrigation, year after year. A tiny film of salt is left behind each time. Eventually, it builds up into a hard, white, sterile crust on the surface of the field.
The calor.
The calor lands. It looks like a dusting of snow, but it's a death sentence for most crops. It makes the soil chemically toxic. And the sources say that vast areas of the Satluj-Ganga plain and parts of Gujarat are now facing this.
So we have aquifers running dry underneath and salty crusts forming on top. And in the old canal-irrigated areas, we see the complete opposite problem, waterlogging.
Yes, the Indira Gandhi Canal Command area is the classic example. You have these massive, often unlined earthen canals seeping water into the surrounding land to the 47. Or you have farmers who over-irrigate because the canal water is so cheap.
So the water table, which is falling in the tube well areas, is actually rising here.
It rises and rises until it reaches the root zone of the crops. And plants need to breathe through their roots. If the roots are permanently submerged in water, they drown. The fields turn into useless, stagnant swamps. So you have this insane paradox of a region creating both deserts and marshes at the same time.
And all this time, the wheat-rice cycle has been hammering away at the soil's natural fertility.
This is the monotony problem. A healthy ecosystem is diverse. Traditional farming understood this. Farmers would practice crop rotation. Crucially, they would plant pulses, lentils, chickpeas, beans in between the big cereal crops like wheat.
And pulses do something special for the soil, right?
They perform magic. They're legumes, and they have bacteria in their root nodules that can take nitrogen from the air, which is abundant but useless to plants, and fix it into a form that plants can absorb. They are natural fertilizer factories. They heal the soil.
But I'm guessing lentils don't have the same government price support as wheat and rice.
Not even close. So economically, it made more sense for the farmer to stop planting pulses and just do wheat in the winter, rice in the summer. Wheat, rice, year after year for 50 years.
It's like a person eating nothing but sugar and caffeine every day.
The body breaks down. The soil is exhausted. It's been stripped bare of specific micronutrients. The sources mention zinc, manganese, sulfur, that the wheat-rice cycle demands in huge quantities.
Which means, to get the same yield he got 10 years ago, the farmer now has to apply even more chemical fertilizer to make up for the depleted soil.
It's the law of diminishing returns playing out in real time. The land is like an addict. It needs ever higher doses of the chemical fix just to perform at the same level.
And of course, all those chemicals, the nitrates from the fertilizer, the pesticides, they don't just stay in the field.
They run off into the canals, into the rivers, and they leach down into the groundwater, poisoning the drinking water for millions of people. We're seeing horrifying public health crises, like cancer clusters in the farming belts of Punjab, that directly correlate with the rise in chemical-intensive agriculture. The golden harvest has turned out to be toxic.
It is a truly grim picture. When you
Right.
put it all together, the social inequality, the class conflict, the ecological collapse, it's easy to look back and question the whole thing.
It is, but we have to be careful not to be too cynical. We have to remember the context. We have to remember the 1960s. The alternative was not a beautiful organic paradise. The alternative was potentially mass starvation.
The Green Revolution, for all its faults, worked. It did what it was supposed to do.
It did. It prevented famine. It made India self-sufficient in food grains. It saved, without exaggeration, millions and millions of lives. That is a colossal achievement that we can never, ever dismiss. It was an emergency measure, and it averted the emergency.
But the sources seem to be telling us that the bill for that emergency survival has finally come due.
I think that's the perfect way to phrase it. We bought our food security on a credit card. The currency we used was our topsoil and our groundwater. And for 50 years, we've been making the minimum payments. Now the debt collector is at the door.
And we're seeing it in the yields themselves, which the sources say are now plateauing.
They are. The very tools that created the boom, the intensive irrigation, the chemical inputs, have now become the limiting factors. They've damaged the underlying resource base so badly that the land is losing its ability to produce.
So where does that leave us? The material gestures towards this idea of a second green revolution. What would that even look like?
Well, it's clear what it can't look like. It can't be a repeat of the first. It can't be about finding a new chemical to pour on the problem. The sources use this phrase, a judicious and scientific approach.
Which sounds like academic code for we need a radical rethink.
It is. It means we have to start working with our geography, not against it. We have to ask the really difficult economic and political questions. Does it make any sense to grow water-guzzling rice in the semi-deserts of Punjab? Why are we subsidizing the electricity that encourages farmers to drain the last drops of water from the aquifers?
Should we be bringing back those millets and pulses that heal the soil and sip water?
It seems like the first Green Revolution was a conquest of nature born out of desperation. The second Green Revolution, if it's to succeed, has to be a partnership with nature, born out of a desire for sustainability.
That's the only path forward. We solved the problem of hunger, but in the process, we mortally wounded the earth that feeds us. If we want to keep eating in the year 2050, the healing has to start now.
That's the challenge. And the damage to the water table and the soil in that green bowl of India may, in some ways, be irreversible.
And that's the thought we want to leave you with. Technology gave us the power to bend the rules of geography for a while, but it never gave us the power to break them. In the end, the map always wins. Thanks for listening to this deep dive.
We'll see you next time. At this point, it is important to understand the geographical logic behind this pattern.
It really is.
You see, when we look at the environmental crisis that's been unfolding in places like Western Haryana, it's easy to just blame, bad policy or over-farming.
Which are factors, of course.
Of course. But what the data really shows is something more fundamental. It's geology fighting back.
That's a great way to put it. It's a classic case of what's happening underneath the ground dictating the chaos that we see on the surface. We have this tendency to treat the Earth as sort of a blank canvas, but it's not.
And in Western Haryana, it's definitely not blank.
Far from it. There's this hard subterranean reality that's completely messing with the agricultural model. There's a layer of gypsum buried down there.
Gypsum. So for anyone listening who just thinks of that as the stuff inside their drywall, what does that mean in a geological sense? It acts as a kind of barrier, right?
Precisely. You should think of it like a waterproof sheet that's buried, I don't know, a few meters underground. It's impermeable. It does not permit water to percolate downwards.
Okay, I see where this is going.
So think about the whole mechanism of the Green Revolution. The advice to farmers was simple. Irrigate. Irrigate heavily. Flood your fields to grow these new, very thirsty crops like rice.
But the water has nowhere to go?
Exactly. It hits that gypsum floor and it just sits there. It can't drain away.
The bathtub effect. You've left the tap on, but the drain is completely plugged.
A perfect analogy.
Right.
And this, in turn, causes the water table to rise, and rise dramatically. Now, this is where the physics gets interesting because it triggers a mechanism known as capillary action.
Right.
As that water table rises up through the soil profile, the soil itself acts like a wick. It just pulls that moisture upward, right toward the surface.
And I'm guessing that water isn't exactly pure, is it?
Oh, not at all. It's a solvent. So as it's rising, it's dissolving all the mineral salts that are naturally present in the Earth's crust. It carries them all the way to the top.
So it's bringing the salt with it.
And then, when that water finally reaches the surface and evaporates under that hot Indian sun, the water itself is gone. But the salts are left behind.
And the result.
The result is the formation of these massive, barren stretches of saline and alkaline soils.
So in the very act of trying to hydrate the crops, the farmers are essentially poisoning their own land, salting the earth.
You're effectively sterilizing your own soil. And this leads to one of the most bitter, almost tragic ironies in this entire deep dive.
I was reading this in the notes, and it's just astounding.
You have farmers in the Jajjar district of Haryana, a region that historically is arid, it's dry, they would have been desperate for rain, and now they're literally praying for drought.
That just stops you in your tracks. A farmer praying for the rain to stop.
It sounds completely counterintuitive, maybe even insane to an outsider. But you have to understand, it's a survival mechanism for them. Their fields are so waterlogged because of this gypsum trap that their traditional crops, things like bajra, millets, artar, they're literally rotting in the mud.
So they need a drought just to dry the land out enough to even try to plant something.
Yes, just to sow a seed. It is such a stark illustration of what happens when you apply a one-size-fits-all agricultural model like heavy irrigation without ever consulting the local geology.
And this fallout, it isn't just limited to the soil chemistry, is it? If we zoom out a little, the sources we're looking at describe the broader environmental impact of the Green Revolution as a kind of comprehensive ecosystem collapse.
That's not an exaggeration.
I was looking at the deforestation data for Punjab and Haryana. It's shocking.
Shocking is absolutely the right word. In that rush to expand the area under cultivation, to plant every single available inch of land with these new high-yield varieties of wheat and rice, we basically declared war on the forests.
And what's the figure now?
Today, less than 5% of the area in Punjab and Haryana remains under any kind of forest cover.
Less than 5%. So
Yeah.
we just traded the entire ecosystem for more acreage.
We did. We stripped away all the natural buffers, and it's not just the visual loss of the trees. It's the sonic landscape, too.
The noise pollution. That's a phrase I didn't expect to see linked with farming.
Me neither, initially. We have this romantic idea of the countryside, don't we? Quiet, pastoral, you hear birds, the wind in the crops.
Right, but the Green Revolution was never that. It was basically an industrial revolution that happened on farmland.
Correct. It mechanized everything. Tractors, thrashers, combine harvesters, even stone crushers. These are loud, heavy diesel machines running day and night, especially during the harvest seasons.
Yeah.
The rural tranquility has been fundamentally disturbed. It's an industrial zone now, not a pastoral one.
But if the noise is a nuisance, the health data is a tragedy. This is the part of our deep dive where we really need to pause and process what the sources are telling us. We have to talk about the chemicals.
This is the darkest entry in the entire ledger. To get those miracle yields that the new seeds promised, the plants needed constant protection. And that meant heavy, relentless doses of insecticides, pesticides, and chemical fertilizers.
And the Indian Council of Medical Research, the ICMR, they flagged the consequences of this, didn't they?
They did. Because these chemicals, They don't just stay on the plant or in the soil.
We're getting into the food chain.
Traces of heavy metals. We're talking lead, zinc, copper. They're showing up in the milk you drink, in the vegetables you eat. The soil is soaked in it, so the plant absorbs it. The animal eats the plant, and then
it ends up with us. But the consequences for the people right there, at ground zero of this revolution, the farmers themselves, it's lethal.
it is. The sources, they mention a specific train. They call it the cancer train.
Yes, tell us about that. It's a chilling phrase.
It's a recognized socio-medical phenomenon.
Yeah.
There is a train that runs from the Malwa region of Punjab to a city called Bikaner.
Mm.
In Bikaner, there's a specialized cancer hospital.
And the train is full of farmers.
Packed with them. On any given day, it's full of farmers and their families seeking treatment for malignancies that are being directly linked to that chronic, high-level chemical exposure.
That's a haunting image. A train full of the very people who fed the country, now traveling to get treated for the cost of that food production.
It's absolutely heartbreaking. And it's not just cancer. We're also seeing a resurgence of vector-borne diseases, things like malaria in regions that should be too dry for them, places like Rajasthan and parts of Punjab.
And that links back to the waterlogging we were talking about earlier.
Precisely. The extensive canal irrigation systems, the poor drainage, it's all created these stagnant bodies of water in places that used to be arid. We have, in effect, engineered perfect breeding grounds for mosquitoes right in the middle of the desert.
So if we step back and look at this socioeconomic ledger of the Green Revolution, the debit column is just incredibly heavy. You have ecological destruction, major health crises, poisoned soil. But, and this is important, we have to be intellectually honest here, we can't critique this in a vacuum. We have to remember why this all happened in the first place.
Absolutely. We cannot lose sight of the context. Before the Green Revolution, India was, and this was the term used, living ship to mouth.
Meaning reliant on foreign food aid.
Completely. The country could not feed itself. It was dependent on imports and aid just to stave off famine. The Green Revolution was, first and foremost, a production boom that saved millions of people from starvation.
And it fundamentally changed the economy. It transformed India from a subsistence economy to a market-oriented one.
That is the key shift. We achieved self-sufficiency in staple foods: wheat, rice, maize, bajra. And that intensification, especially the increase in what's called the double-cropped area, where you can harvest twice a year instead of once, it generated jobs.
Real jobs, real money.
Huge amounts of rural and urban employment were created. Money started to flow into the hands of farmers and laborers. There was genuine prosperity and, for the first time in many areas, real capital formation.
But that prosperity wasn't a rising tide that lifted all boats equally, was it? The sources point to a pretty severe polarization happening in rural society.
It was very, very uneven. The technology of the Green Revolution, the tube wells for irrigation, the tractors, the expensive fertilizers and seeds, it all required capital. It was expensive.
So the large farmers, the ones who already had money, could invest and get much, much richer.
While the small farmers couldn't keep up, it drove a wedge right through rural society.
The sources we looked at identify three distinct conflicts that really emerged from this. The first, as you said, was large farmers versus small farmers.
Correct. The gap between them just widened enormously. Second, you saw a new level of conflict between landowners and their tenant farmers. As land suddenly became more valuable and profitable, the owners wanted to take it back to farm themselves.
So they'd evict the tenants who had been working that land for generations.
Often, yes. And third, the relationship between employers and employees on these new mechanized agricultural farms changed. It became purely transactional, about wages, not the old systems of obligation.
And that brings us to what might be the most profound cultural loss mentioned in the notes: the complete breakdown of the Jajmani system. Could you unpack that for our listeners? Because Jajmani isn't just about jobs, is it? It's a whole social structure.
It is, yes. The Jajmani system was this traditional, intricate system of labor exchange within the village economy. You had your artisans, the carpenters, the ironsmiths, the barbers, the washermen. They served the landed farming families all year round.
How did it work?
Well, they would fix the wooden plows, they'd shoe the oxen, they'd cut hair. And in return, they didn't really get a wage in the modern sense. They received a guaranteed share of the harvest. It was a symbiotic, customary relationship built on mutual dependence.
But the Green Revolution brought the market, and it brought the machine.
Exactly. And the machine has no need for custom. If I buy a tractor, I don't need the village blacksmith to shoe my ox anymore because I don't have an ox.
And if you buy a factory-made metal plow, you don't need the carpenter to fix your old wooden one.
Precisely. So those artisans didn't just lose a gig, they lost their entire place in the village ecosystem. Their skills became redundant overnight.
What happened to them?
They were forced to migrate to urban areas to survive, looking for any kind of wage labor. It fundamentally dismantled the traditional self-sufficient village economy.
And even for the agricultural laborers who remained, the machines were a double-edged sword.
A huge one. A single combine harvester can do the work of dozens of people and do it faster. So while overall production soared, rural unemployment for the poorest landless laborers actually spiked in many areas.
Which brings us really to the present day. If we look at the trajectory of all this, the data seems to suggest that in these very heartlands of the revolution, production has hit a wall.
It has. Agricultural production in these areas is now either completely stationary or, in some cases, declining. The growth rate of the entire agricultural sector is hovering at around 2%.
But to keep up with population growth and demand, we need, what, 4%?
At least 4% annually. So we're falling behind. Economists have a term for this. They're calling it the plateau stage.
At the plateau stage.
Yes, for both cereal and non-cereal crops. We're basically squeezing a dry lemon at this point. You can't just keep adding more fertilizer to dead soil. You can't just pour more water onto a waterlogged field and expect yields to go up.
So the call now, and we're seeing this in all the policy documents, is for a second green revolution.
Yes, but this second revolution sounds very different from the first. It's not just about brute force volume anymore. The key word that keeps popping up in the sources is holistic.
It has to be different, doesn't it?
It does. The new objective is a holistic framework that's focused on sustainability. We have to start thinking about resource efficiency, about conserving the soil, the water, and the ecology, rather than just exploiting them until they break.
And a huge part of this seems to be diversification, moving beyond that old obsession with just rice and wheat.
Correct. The strategic plan now is to move toward high-value outputs, things like fruits, vegetables, spices, even crops for biodiesel. And there's a massive, massive emphasis on biotechnology using genetically modified or hybrid varieties to boost production without destroying the land in the process.
I noticed a very specific, almost panic tone in the notes regarding pulses. So beans, lentils, that sort of thing. Why is there such a specific call out for them in the second green revolution?
That's because of what's known as the pulse crisis.
Yeah.
You have to remember, for the majority of the Indian population, pulses are the primary source of protein. It's the staple. But unlike wheat, you can't just easily go out and import pulses from the global market. The international supply just isn't there in the volumes that India needs. So growing them domestically isn't just a good idea, it's a strategic imperative for food security.
Plus, from a biological standpoint, they're nitrogen fixers, right? They actually heal the soil.
Exactly. They fit perfectly into this new holistic framework they give back to the land. All of this is codified in documents like the 11th Five-Year Plan, which talks about doubling the rate of irrigated area, bridging the knowledge gap for farmers, and essentially trying to fix the ecological damage of the first revolution while we launch the second.
Okay, so that's a huge topic. That covers the Green Revolution and its legacy. But the story of India's agricultural revolutions is famously color-coded. We need to shift gears now and talk about the White Revolution, Operation Flood.
This is, and I don't think this is an overstatement, arguably one of the world's greatest rural development stories. It really kicked off around 1970. And if you're talking about the White Revolution, you have to talk about one central figure, Professor Varghese Kurian.
The father of the White Revolution in India.
The very same. He was the architect who helped scale up what became known as the Anand pattern. This started in the state of Gujarat with the National Dairy Development Board, or NDDB. And the core idea was simple, but it was absolutely revolutionary.
Cooperative societies.
Cooperative societies, it completely flips the traditional power dynamic. Instead of a big corporation owning the cows and the farmers just being employees, in this model, the farmers own the entire system.
It cuts out the middleman.
It completely eliminated the middleman. Before this, a poor farmer in a village would sell their milk to a local trader, who'd then sell it to a distributor, who'd sell it to a retailer. At each step, someone takes a cut, and the farmer at the beginning gets pennies.
But under the Anand pattern,
The cooperative, which is owned by the farmers, collects the milk directly. The producers act as their own distributor. All the profit flows back to them.
the logistics described here, though, it sounds less like a business and more like a military operation. I mean, dealing with fresh milk in a hot, tropical country seems like a logistical nightmare. It must spoil instantly.
The timeline has to be incredibly rigid. The entire system is designed with zero margin for error. The milk is collected from these village collection centers twice a day, every day. It's immediately put into trucks and taken to chilling centers to stop any bacterial growth.
And from there.
From there, it's transported in massive insulated tankers to the main dairy plants for processing and packaging. A standard tanker carries about 14,000 liters of milk. It's a massive, synchronized moving cold chain.
And this all rolled out in phases, right? Phase 1, starting in 1970, it wasn't a national thing straight away.
No, not at all. Phase 1, which ran from 1970 to about 1981, was about proving the concept. It was about connecting the rural milk producer to the urban consumer in the 4 biggest metros. They set up what were called mother dairies in Mumbai, Kolkata, Delhi, and Chennai. It was all about proving that the link could work on a large scale.
And then phase 2, in the early 80s, expanded on that.
Phase 2, from 81 to 85, expanded the network to 144 more cities. But crucially, Phase 2 wasn't just about moving milk. It was also about improving the asset itself, the cow.
Okay.
This is when they introduced the Raksha vaccine to control major cattle diseases. They started investing heavily in animal health and better feed. It was about improving the factory, essentially.
By phase 3, which ran from 85 all the way to 2000, the consolidation was just massive.
Unbelievable. We're talking about 1.35 lakh societies. That's 135,000 village co-ops with about 14 million farmer members. The result of all this, India went from being a milk deficit nation to the #1 milk producer in the world,
Surpassing the USA.
surpassing the United States.
The numbers are just staggering. The data shows production went from 17 million tons in 1950 to over 112 million tons in recent years. And per capita availability more than doubled, from 124 grams a day to 263 grams. That's a massive nutritional shift for a whole country.
It is a game changer. But we have to be balanced here. The sources do highlight some lingering issues. Despite the huge volume, the hygienic conditions of the cattle in many places remain poor. The indigenous breeds of cattle often have lower yields compared to, say, European or American breeds.
And that cold chain we were admiring.
It's incredibly expensive to build and maintain, which keeps the collection costs high, so improving efficiency is still a constant struggle.
So plenty of milk, but the infrastructure is always straining to keep up. Okay, let's trade the white of milk for the blue of water, the blue revolution.
Fisheries and aquaculture. This was the name given to the package program designed to increase the production of fish and other marine products. And if you want to see the ground zero, or maybe I should say water zero of this revolution, you have to go to the Nellore district of Andhra Pradesh.
Which is known as the shrimp capital of India.
Indeed it is. Now here's a common misconception most people have. When we think blue revolution, we picture fishing boats out on the ocean.
Right, marine fishing.
And while marine fisheries are still very significant with states like Kerala and Maharashtra leading the pack, the real growth engine has been in inland fisheries.
So freshwater, ponds, tanks, rivers, reservoirs.
Exactly. Inland fisheries now contribute about 50% of the total fish production in India. We're farming fish far more than we are hunting them in the sea.
Which is interesting because the sources also say that India has this massive exclusive economic zone, over 2 million square kilometers of ocean, but we barely even touch the deep sea.
It's a huge untapped potential. We have about 180 registered deep-sea fishing vessels, but on any given day, only about 60 of them are actually in operation. The deep sea remains a frontier. The focus has been on aquaculture because it's more controlled, more predictable.
And the terminology in the notes gets very specific here. You have mariculture versus algaculture.
Right. Mariculture is the cultivation of marine organisms, but in seawater. So think of oyster farming or prawn farming in coastal estuaries. Algaculture is the farming of seaweed or algae for commercial uses like food or biofuel. And then you have your standard fish farming raising species like salmon, catfish, or tilapia in tanks and enclosures.
There's a specific type of prawn mentioned as being the real backbone of the freshwater industry, the Macrobrachium rosenbergi.
The giant river prawn.
Yeah.
It's the absolute workhorse of the freshwater aquaculture industry. But the concept that really caught my eye in these notes, the one that feels like the future, is something called IMTA.
IMTA. It sounds like a mouthful. Let's break that down.
It stands for Integrated Multi-Trophic Aquaculture. Think of it as a form of ecosystem hacking. In a standard fish farm, the waste from the fish, their poop, the uneaten food, is just pollution. It settles on the bottom and destroys the water quality.
Yeah.
In an IMTA system, you view that waste as a resource. You design a balanced system where the waste from one species, say the shrimp you're feeding, becomes the fertilizer for another species, like seaweed, or the food for another, like shellfish, which are living in the same system.
So it's an organic extractive process. It cleans the water while creating more product.
Exactly. It turns pollution into production. It's a brilliant, sustainable concept. But again, the blue revolution isn't without its dark side. General pollution in our rivers and lakes is rising, and the socioeconomic factor is a huge challenge. Most traditional fishermen are very poor. They lack good boats, good nets, good equipment,
And the inland fisheries are totally reliant on the weather.
completely at the mercy of the monsoon. If the rains fail, the ponds and tanks dry up, and your entire livelihood is gone. It's a very precarious existence.
From the water, let's move on to the insects and the birds. We have the golden revolution, which is honey, and the silver revolution, which is eggs.
Let's start with the Golden Revolution. Apiculture, or beekeeping. Globally, China is the largest producer, but India is a major player. The really interesting story here is a technological one. It's what I'd call the battle of the boxes.
The traditional hives versus the modern hives.
Exactly. Traditionally, in India and elsewhere, you had what are called fixed-frame hives. To get the honey, you basically had to break open the hive and destroy the colony. It was incredibly destructive and inefficient.
And the modern alternative.
The modern alternative is the movable frame hive, and the most famous version is the Langstroth hive. With this, you can just slide the frames out, spin the honey out in a centrifuge, and then put the frames right back. The bees are fine, the colony is undisturbed, and they get back to work immediately.
But the sources also mention a sort of low barrier to entry option for poorer farmers who can't afford a Langstroth hive, the top bar hive.
Yes, this is very popular in parts of Africa and Asia. It's much simpler to build. Now, it only produces about 20% of the honey that a Langstroth hive does, but it's cheap, and it's much easier for the bees to manage themselves. It lowers the capital needed to get started, so it really helps to democratize the industry.
And speaking of valuable insects, we can't skip sericulture, the silk industry.
India has a very unique distinction here. We're one of the only countries in the world that produces all 5 of the known commercial varieties of silk: mulberry, oak tazar, tropical tazar, Erie, and the golden muga silk.
And the state of Karnataka is the king of mulberry silk, isn't it?
It is. It's a massive employer in rural areas. The whole process involves rearing the Bombyx mori silkworm, feeding them mountains of mulberry leaves, and then carefully reeling the single continuous thread from their cocoons. It's highly labor-intensive, which is actually a good thing in this context because it creates so many jobs.
Okay, let's move to the Silver Revolution poultry. The growth here has been explosive. Egg production apparently quadrupled between 1970 and 2011.
It did. But this brings us right into a major modern debate: quantity versus quality, or ethics. This explosive growth is almost entirely driven by industrial factory farming, high productivity, but also high containment.
The ethical dilemma of modern agriculture.
And a health dilemma, too.
Yeah.
The sheer density of these factory farms makes them a ticking time bomb for diseases like avian flu. The birds are packed in so tight that if one gets sick, they all get sick very, very quickly.
So what's the strategy to counter that risk?
That's why the Central Poultry Development Organization is pushing to diversify the species. They're encouraging farmers to raise not just chickens, but also ducks, turkeys, even guinea fowl.
Basically, don't put all your eggs in one basket. Literally.
Precisely. Diversification is a form of biological insurance against a catastrophic disease outbreak.
We're in the home stretch of our deep dive now. We need to touch on 2 final crucial areas: horticulture and what the sources call the neglected majority, dry farming.
Horticulture is a real bright spot in this story. India now produces about 10% of the world's fruit. We're number 1 globally in mango and banana production. And we're number 2 in vegetables, right after China.
And flowers are now big business, floriculture.
Yes, the sources attribute this to what they call westernization. There's a rapidly rising urban demand for cut flowers like roses and gladiolus, for gifts, bouquets, corporate offices. It's no longer just a small-scale thing for temples and festivals. It's a high-value cash crop, especially for farmers who are located near big cities.
But then we have dry farming. This feels like the complete underdog of this whole story.
Is the underdog. A dry farming region is defined as an area that receives less than 75 centimeters of annual rainfall and has no access to irrigation facilities. And it covers about 60% of the net cultivated area in India.
60%. That's the majority of the farmland.
It is the majority. And yet, it provides only about 40% of the total food production. These are the regions growing the coarse grains millets, bajra maize, and the pulses and oilseeds we talked about. These are the poorest regions, home to the most vulnerable farmers. The risk is incredibly high because the yields fluctuate wildly with the erratic rainfall.
So the strategy here isn't about profit maximization like it was in the Green Revolution areas. It's more about resilience, about survival.
Exactly. It's about risk mitigation. The strategies are things like water harvesting buildings, small check dams and ponds to catch every single drop of rain, and soil conservation is key. Methods like contour plowing to prevent soil erosion. And mixed cropping is absolutely essential.
Explain that.
You plant multiple different types of crops together in the same field. That way, if the rain fails at a critical time and one crop dies, another more drought-resistant one might survive. It's about working with the harsh environment, not trying to force it to be something it isn't.
Finally, let's tie all of these threads together with the business side of things, agribusiness and national policy.
This is the current evolution. We are seeing a major shift from farming as a way of life to farming as a business. And agribusiness involves the entire value chain, not just growing, but storage, processing, and distribution.
This is where the big corporations come in.
Yes.
Yeah.
Large conglomerates are entering the field in a big way. They aren't just selling seeds and fertilizers anymore. They're moving into processing, making the jams, the pickles, the ketchups, and even into direct retail. And this requires the development of that sophisticated cold chain we talked about with milk, but now for fruits and vegetables to prevent spoilage between the farm and the supermarket.
And this whole shift is supported by government policies, specifically the National Agricultural Policy of 2000.
That policy document set the goal that we are still chasing today, achieving a consistent 4% annual growth rate in agriculture. It officially opened the door for private sector investment. It established the National Agricultural Insurance Scheme to help protect farmers from the risks we've discussed, and it aimed to dismantle the old restrictions on moving agricultural commodities across state lines, creating a single national market.
So if we synthesize this entire journey, it's really a remarkable story. We started with the Green Revolution, which was driven by the sheer biological imperative to stop mass starvation.
Then we moved to the white and silver revolutions, which were about adding crucial nutrition milk and eggs to the national diet, improving health.
And now we're looking at the second Green Revolution and the rise of agribusiness, which is all about sustainability, diversification, adding value, and processing. It feels like a maturing of the entire agricultural economy.
It is a very complex, often painful, but undeniable maturation.
But the thought that really sticks with me, going back to where we started, is the cost. We have supermarkets full of mangoes and milk and chicken, but we also have the cancer train running every day.
And that raises the fundamental question, doesn't it? Has the modernization of Indian agriculture prioritized sheer volume over vitality? We conquered the famine, which was a monumental achievement, but we might have poisoned the well in the process.
And as we now rush headlong toward this second revolution, with all its talk of biotech and corporate farming and GMOs, we have to ask, what will the biological cost be this time? If we don't listen to the lessons of the gypsum layers and the rising water tables, the next bill that comes due might just be too high to pay.
That is the crucial warning from this whole story. Nature always keeps a ledger.
And that is a lot to think about. Thanks for listening to this deep dive.
At this point, it is important to understand the geographical logic behind this pattern.
It really is, because when you look at an agricultural map of India, it can seem, well, a little chaotic. You just see this patchwork of colors.
Right, it looks almost random.
Right.
A splash of yellow for wheat here, a patch of white for cotton there.
Exactly. But there is a deep, a profound logic to it. It's not random at all. This is what geographers call the cropping pattern.
And pattern is really the key word there. It implies there's a system at work, some kind of design, or at least a set of constraints. We're not talking about a farmer just waking up and deciding, I think I'll plant sugarcane today.
Far from it. That farmer's decision is, it's the end result of a massive silent tug of war. The cropping pattern of any region, which is really just the proportion of land under different crops at a given time, is shaped by so many forces.
But you have nature on one side of the rope.
You do. You have the physical factors. Things like relief or the terrain. Is it flat and easy to plow, or is it hilly? Then you have climate, temperature, and rainfall are the absolute dictators. And of course, the soil type. You can't escape the soil.
But then you have the human element pulling on the other side.
Precisely. You've got historical factors, Traditions, what your grandfather grew. Political factors are huge, government policies, minimum support prices, things like that.
And the big one, I assume, is economics.
Always, economics is often the tiebreaker. A farmer might have perfect soil for crop A, but if crop B fetches twice the price, or if their farm is just too small for the machinery that crop A needs, well, they're going to plant crop B. It's that simple.
So it's this dynamic interplay. Nature proposes a setup, and then history and economics come in and rearrange the furniture. And to make sense of all this, geographers have developed some pretty clever tools. One that really jumped out at me was this idea of crop concentration and something called the location quotient.
Ah, yes, the location quotient. It sounds very technical, but the idea behind it is actually surprisingly simple.
It seems like a way to figure out what a region is truly good at, its specialty.
That's it, exactly.
Okay.
It's how we decode a region's agricultural character. The location quotient helps us cut through all the noise and answer a very specific question. Is this region, let's say a district, punching above its weight for a certain crop compared to the country as a whole?
Okay, so let's break down the math just for a second. It's a ratio of ratios, right?
It is. You're basically taking the share of a crop's area in a district and dividing it by that crop's share of area in the entire nation. You're looking for a baseline.
And the magic number is 1.
The magic number is 1. If the index, the final number you get, is greater than 1, it tells you that the region specializes in that crop. It has a high concentration. It's doing more than its fair share, so to speak.
So if we apply this to the map, say, for wheat in Punjab and Haryana, that index must be, what, way off the charts?
Way off the charts. The location quotient for wheat there is very, very high. And the reason is simple. The agroclimatic conditions are perfect. You've got the rich alluvial soil, the cool winters for the growing season, and this is the critical part assured irrigation from the canals.
It's the perfect storm for wheat.
It is, and you see the same thing elsewhere. Go to the Black Earth region of the Deccan Plateau, and the index for cotton spikes. Go to the really arid parts of Rajasthan, and suddenly you see a high concentration of bajra or bulrush millet, a crop that can handle those dry conditions.
This isn't just an academic exercise, though.
Oh.
Identifying this regional character has real-world implications, because if you specialize too much, you get monoculture.
And that's the danger zone. High concentration might be efficient economically in the short term, but biologically, continuous monoculture can be devastating for the soil. It's like a slow poison.
How so?
Well, if you only grow wheat year after year, you are only pulling the specific nutrients out of the soil that wheat needs. You're stripping it bare of those particular elements. This is why understanding these patterns is so crucial for planning. It tells you where you need to encourage or even mandate crop rotation.
Like throwing in some leguminous crops.
Exactly. Plant some pulses to fix nitrogen back into the soil and give it a chance to recover.
That actually leads perfectly into another set of metrics I found fascinating. The yield index versus the spread index. Because it seems just because a crop is planted everywhere, it has a high spread, that doesn't mean it's actually growing well.
That is such a critical distinction, and one that gets missed a lot. The relative spread index tells you how much land is being used for a crop. You can think of it as a measure of its popularity.
How common it is.
Right. But the relative yield index tells you how productive that land is compared to the national average. It's a measure of performance.
So the ideal scenario, the gold standard, would be high yield and high spread.
That's the dream. That tells you the crop is biologically suited for the region, it's performing well, and farmers recognize this, so they're planting a lot of it. That is peak agricultural efficiency.
But the data often shows this paradox. Low yield, but high spread. That just seems to fly in the face of logic. Why would farmers keep planting a crop that isn't performing well?
That's where you see the tragedy of subsistence farming or just a lack of options. When you see that combination, low yield, high spread, it's often a red flag. It tells you the physical conditions probably aren't great for that crop.
But they're growing it anyway.
They're growing it anyway. Maybe it's the only staple food they know how to grow to feed their family. Maybe they don't have the irrigation needed to switch to a more demanding high-yield crop. Or maybe they just can't afford the better seeds and fertilizers. It's a sign of inefficiency driven by pure necessity.
So a truly suitable cropping pattern is about more than just what can technically grow. It has to be sustainable, efficient. And the research points out it should provide year-round employment.
That employment piece is massive, especially in a country with such a huge rural population. If your crop cycle leaves the entire village idle for 6 months of the year, That's an economic failure for the region, no matter how good the harvest was. You need a rhythm, a pattern that keeps people working.
Now, we've mostly talked about single crops, but most farmers don't put all their eggs in one basket. They grow a mix of things. And this brings us to the idea of crop combinations. There's a specific statistical method mentioned here, Weaver's method. This felt a bit abstract, so could you help me visualize it?
Weaver's method, yes, this is a classic piece of geographical analysis. It was developed to map out the American Midwest, but it works perfectly for India. Weaver was trying to solve a puzzle. How do we objectively classify a region? Is it a monoculture region, a two-crop region, a five-crop mix?
And he used standard deviation to figure this out.
He did. It's a clever bit of statistical work. What he did was he created theoretical ideals. For instance, a theoretical one-crop region is 100% of the land under one crop. A theoretical two-crop combination is 50% under crop A and 50% under crop B. Three crops would be 33.3% each, and so on.
Okay, so he sets up these perfect imaginary scenarios.
Exactly. Then he takes the actual data from a district, the real percentages of land under each crop, and measures how much it deviates from each of those theoretical models. The combination with the lowest deviation, the one that is the closest match to reality, is declared the winner.
Let's use a real example. The notes mention Gorakhpur district.
Right, so for Gorakhpur, you'd calculate the deviation from the 100% model, the 50-50 model, the 33-33-83 model, and so on. The analysis found that the deviation was smallest when the area was classified as a three-crop combination.
And those three crops were rice, wheat, and barley.
Rice, wheat, and barley. So statistically speaking, Gorakhpur is a rice, wheat, barley region. It's a way of bringing statistical rigor to what you might otherwise just guess by looking at a map.
And when you apply this across the entire country, you see these incredible contrasts. You look at, say, the Brahmaputra Valley in Assam or coastal Andhra, and Weaver's method basically just flashes monoculture. It's rice, rice, and more rice.
It really is. It highlights the specialization, but also the vulnerability. But then you shift your gaze to Western Uttar Pradesh, and the calculations show this incredible diversity. You find 8 crop combinations.
8 crops.
Yes. You've got wheat, rice, sugarcane, maize, pulses, oil seeds. It's a true agricultural buffet.
Which implies a much more resilient system.
Yeah.
If one crop fails due to pests or bad weather in western UP, the farmer has 7 others to fall back on. If the rice crop fails in coastal Andhra.
You're in serious trouble. Diversification spreads the risk. It's like having a balanced stock portfolio versus betting everything on one hot tech stock.
Okay, so that covers the what and the where.
Yeah.
The patterns and the combinations. But now we have to talk about how well these regions are doing. This brings us to the next section of our deep dive, agricultural productivity.
Productivity, which is really just another term for agricultural efficiency. At its core, it's about yield per unit of area. And so the farm's report card.
And to grade that report card, geographers use something called Kendall's ranking coefficient. Another complex-sounding name for a surprisingly straightforward idea. It's basically a ranking system.
It's beautifully simple, really. You take every district in the country and rank it for the yield of each major crop it grows. So if a district has the highest wheat yield in all of India, it gets a rank of 1 for wheat. If it's the worst, it might get a rank of, say, 500.
And you do this for every crop in that district.
For every significant crop. Then you simply average all those ranks together to get a final coefficient for the district.
So, like in golf, a lower score is better.
Exactly. A low coefficient means that district is consistently a top performer across multiple crops. It's a sign of high overall productivity.
And based on this method, who are the star pupils? Which parts of India have the lowest scores?
Well, it's probably not a huge surprise. The top of the class is the Satluj-Ganga Plain. We're talking Punjab, Haryana, and Western Uttar Pradesh, and some of the coastal delta regions. These areas consistently rank near the top for almost everything they grow.
And the reason for that is the Green Revolution package.
It's the whole package. It all comes back to assured irrigation. That's the foundation. On top of that, you have the high-yielding variety seeds, the widespread use of chemical fertilizers, and a high degree of mechanization. Agriculture, there isn't just a way of life. It's a highly efficient business.
And on the other end of the spectrum, the low productivity areas with high scores.
That would be the rain-fed areas of the country. The plateaus of Jharkhand and Chhattisgarh, large parts of interior Maharashtra and Rajasthan. Here, the ranking coefficients are high, which means yields are consistently low.
Because they're at the mercy of the monsoon.
Completely. The rainfall is highly variable. One year you get floods, the next you get a drought. In that environment, a farmer is not going to risk spending a lot of money on expensive seeds and fertilizers. So they stick to subsistence farming, yields stay low, and it becomes a vicious cycle.
Seeing these stark disparities on a map must make planners very anxious.
Yeah.
And that leads to the impulse to zone the country, to carve it up into manageable regions, to create targeted policies. We've seen a few attempts at this over the years.
Oh, many attempts. It's been an evolving science. One of the earliest was by Rand Howe back in 1958. He proposed 5 broad regions based mostly on climate: temperate Himalayan, northern dry, eastern wet, and so on. It was a solid first draft.
A good starting point. But then the Planning Commission got involved.
Yes, and they came up with their famous 15 agroclimatic regions. This was a big leap forward because they didn't just look at climate. They combined topography, soil type, and climate.
So it was more holistic.
Much more. They could distinguish between, say, the Western Himalayas, with its unique needs for horticulture, and the vast Gangetic Plains, with its rice wheat intensity, or the islands, with their coconut and spice economies. It allowed for much more specific planning.
But even that has been refined. The modern approach, according to the sources, is to use agroecological regions. What's the difference? Why was agroclimatic not quite enough?
The difference is precision. The agroclimatic zones were still a bit general. The agroecological approach adds 2 incredibly important layers of data: very detailed soil information and a concept called the length of growing period, or LGP.
Length of growing period.
It's the number of days in a year when both the temperature and the available moisture are right for a plant to actually grow. This single metric changes everything.
Can you give me an example of how that changes the map?
Sure. Take the Western Himalayan region. Under the old system, it's just one big mountain zone. But with the agroecological lens, we can identify that it has a very short growing period, less than 90 days, and specific podzolic soils. Now contrast that with the Bengal Plain,
Which has deep alluvial soil.
and a length of growing period of 180 to 210 days. The potential is just worlds apart.
So in Bengal, you can potentially grow 2, maybe even 3 crops a year.
Absolutely. You can have multiple harvests. In the high Himalayas, you have one very short window to get your crop in and out. By identifying 20 of these highly specific agroecological regions, we now have a much more scientific blueprint for resource planning. It's about matching the biology of the crop to the ecology of the place.
I like that. Matching the biology to the ecology. It's like a matchmaking service for agriculture.
Chuckles. You could say that. It helps prevent a lot of bad pairings between a crop and a piece of land.
All right, let's pivot now. We spent a good amount of time in the fields, but the story of modern India is also about the journey from the farm to the factory. Let's talk about the industrial evolution. And really, these 2 stories are deeply connected.
They're not separate stories at all. They are 2 chapters of the same book. You have to remember, India's industrial journey didn't begin with software parks. It began with what the farms produced: cotton for the textile mills, jute for the sacking industry, sugarcane for the sugar mills. Agriculture provided the raw materials.
But before we get to the modern factories, we have to acknowledge what came before. The colonial impact is just impossible to ignore here.
It's the essential prequel. Before the British consolidated power, India was a manufacturing powerhouse in its own right. We're talking about the legendary muslin of Dhaka, the fine silks of Murshidabad, beautiful metalwork, artistic pottery. The world wanted finished goods from India.
And the East India Company and the British Raj flipped that script completely.
They turned it on its head. The policy became turn India into a supplier of raw materials for Britain's factories and a captive market for Britain's finished goods. It led to the systematic decay of traditional handicrafts. Millions of skilled artisans lost their livelihoods and were forced back onto the land, which just increased the pressure on agriculture.
Deindustrialization, really. But eventually, modern machine-based industry did begin to take root in India.
It did, but slowly and in very specific pockets. The first successful cotton mill was established in Mumbai, then Bombay, in 1854. Just a year later, in 1855, the first jute mill started up in Rishira, near Kolkata.
And steel took a bit longer to get going.
It did. There was an early attempt at Kulti in 1874 that didn't quite work out. The real breakthrough moment for heavy industry was in 1907 with the establishment of Tisco, the Tata Iron and Steel Company in Jamshedpur. That was the game changer.
And then comes independence and the era of the 5-year plans. This was the new government trying to consciously architect an industrial nation from the top down.
It was a monumental effort. Interestingly, the first plan, from 51 to 56, was heavily focused on agriculture. The thinking was, You have to build a strong agricultural base first. You have to feed your people.
But the second plan was the big industrial push.
That was the Mahalanobis model in action, the all-out push for heavy industry. This is when you see the creation of the massive public sector steel plants, Vilai with Soviet help, Durgapur with British help, Rourkela with German help. These were Nehru's temples of modern India.
The idea being that if you build the steel industry, everything else, from railways to dams, will follow.
That was the core idea, and the plans continued to evolve. The fifth plan started focusing on export promotion. The seventh plan brought in high-tech and electronics. The 10th plan introduced the concept of special economic zones, or SEZs.
But the real earthquake, the moment that truly redefined India's economic geography, was 1991.
The new industrial policy of 1991. It was like taking the shackles off the economy.
This was the end of what people call the license Raj.
In essence, yes. Before 1991, if you wanted to start or expand a factory, you needed a mountain of permits and licenses from the government. The new policy abolished industrial licensing for almost every sector. It threw the doors open to foreign investment, allowing up to 51% equity at first, and it made the rupee convertible on the trade account.
It fundamentally changed the logic of where you would build a factory. It was no longer just about where the government wanted you to go. It was about where the market made the most sense.
Absolutely. Which is a perfect segue into our deep dive on specific industries. Let's start with textiles and keep that market logic in mind.
Cotton textiles, the apparel of the masses.
It's the country's largest organized industry, and for a very long time it had one undisputed capital, Mumbai. They even called it Cottonopolis.
So why Mumbai? Was it just because they had a major port?
The port was a big piece of the puzzle, yes. You needed it to import the machinery from Britain and to export the finished cloth. But there was another very specific reason, the climate.
The climate.
Mumbai's high humidity. In a dry climate, cotton thread is brittle, and it snaps constantly during the spinning process. In the humid air of Mumbai, the thread retained moisture and strength. It was a huge natural advantage.
That's fascinating. So you had the humid climate to the port, cheap hydropower from the nearby Western Ghats, and the availability of capital from Parsi and Gujarati merchants.
And you have the perfect recipe for an industrial hub.
But Mumbai isn't the center of the universe for cotton anymore. The industry dispersed. Why did it move away from such a perfect location?
Well, success creates its own problems. The city grew, and land costs in Mumbai went through the roof. It just became too expensive to run a huge, sprawling mill in the heart of the city. Then you had decades of labor unrest and strikes, which made factory owners look for more stable labor markets.
And the railways, I imagine.
The railways were the final nail in the coffin for Mumbai's monopoly. As the network expanded, you no longer had to be at the port. You could set up a mill in the interior, right next to the cotton fields and closer to the massive domestic market.
So where did the industry go?
It spread out. Ahmedabad in Gujarat became a huge center, the Manchester of the East. It moved south to Coimbatore and Madurai in Tamil Nadu, which were close to the black soil, cotton-growing areas. And it developed in places like Kanpur in Uttar Pradesh.
But the industry today faces a whole new set of challenges. The sources talk about sick mills.
Yes, that's a huge problem. A lot of machinery in these mills is ancient, it's obsolete and inefficient. There's also a scarcity of high-quality, long-staple cotton. We lost many of the prime growing areas for that variety to West Pakistan during partition.
And speaking of the impact of partition, that brings us to the story of jute. This feels like the most geographically dramatic tale in the entire data set.
The story of jute is a classic case of geography creating a perfect system and then politics coming in and shattering it. The golden fiber, they call it.
And it is almost entirely concentrated in one tiny area, the Hooghly Basin in West Bengal.
It's an incredible concentration, a narrow belt about 100 kilometers long and only 3 kilometers wide, running along the Hooghly River. Almost all the mills are there.
Why there, specifically?
It was a perfect ecosystem. First, you need enormous amounts of fresh water for retting, which is the process of soaking the jute stalks to separate the fibers. The river provided that. You needed cheap water transport for the bulky, raw jute. The climate had to be humid. You had a ready supply of cheap labor from neighboring states, and you had coal for power from the nearby Raniganj fields. It was a textbook case of perfect industrial location.
And then, 1947, partition happens. What does that do to the jute industry?
It was a body blow, an economic amputation. The vast majority of the jute mills were in India, along the Hooghly, but about 80% of the fertile jute-growing lands went to East Pakistan, which later became Bangladesh.
Wow, so you had all these factories, but the raw material was suddenly in another country.
It was an overnight crisis. India had to launch a crash program to expand jute cultivation within its own borders just to feed the mills. And even today, the industry is struggling. It faces stiff competition from Bangladesh, which now has its own mills, and from other countries. And of course, the big threat is synthetic substitutes. A plastic sack is often just cheaper than a jute one.
Although with the global pushback against single-use plastics, maybe jute is poised for a comeback.
That is the big hope for the industry, that its environmental friendliness will be its salvation.
Let's shift from fibers to metals, the real backbone of any industrial economy. Iron and steel.
This is the classic example of what geographers call a weight-losing industry.
Weight losing. Sounds like it's on a diet.
Chuckles. In a way, it is a diet for logistics. Think about what goes into making steel. To produce just 1 ton of steel, you need roughly 2 tons of iron ore, 1 ton of coking coal, and half a ton of limestone and other materials.
So a lot of the raw material ends up as waste.
A huge amount. So if you build your steel plant in a city far away and transport all those raw materials to it, you're paying enormous freight costs just to haul waste products. The geographical logic is inescapable. You don't move the mountain to the furnace, you move the furnace to the mountain.
You build a plant near the raw materials, which is why all the big integrated steel plants are clustered on or around the Chotanagpur Plateau.
Exactly. Let's run through the big ones. Tisco in Jamshedpur is the textbook example. It's located right at the confluence of 2 rivers for water. It's a stone's throw from the iron ore mines of Normandy and the coal fields of Charia. It's a perfect convergence.
Then you have Bhilai in Chhattisgarh.
That was a public sector plant built with Russian collaboration. It gets its iron ore from the nearby Dalirajhara mines,
And Rourkela in Odisha.
built with German assistance. Rourkela is unique because it was the first in India to use a specific technology to produce flat products like sheets and plates, which are crucial for cars and ships.
The one outlier seems to be the plant at Visakhapatnam, or Vizag. It's on the coast.
That's right. Vizag was the first shore-based plant. Its locational logic is different. It's positioned to easily import high-grade coking coal if needed, and more importantly, to easily export its finished steel to global markets. It's looking outwards.
But the sources also point to a major shift in the industry, away from these massive integrated plants towards something called mini steel plants.
And this is where the old geographical rules start to break down. Mini steel plants don't use raw iron ore. They use electric arc furnaces to melt down scrap metal or something called sponge iron.
So they don't need to be near an iron ore mine or a coal field.
Exactly. Their main raw material is scrap metal, and their main input is electricity. So where do you find a lot of scrap metal? In and around big cities. This makes them footloose. They can be located near markets, which reduces transport costs for the final product. It's a much more flexible model.
Speaking of being dependent on electricity, that brings us to the next industry, aluminum.
If steel is a weight-losing industry, aluminum is an energy-eating one. It's the second most important metallurgical industry after steel, but the process of smelting bauxite ore into aluminum is basically just solidified electricity. It consumes a phenomenal amount of power.
So when you're deciding where to build an aluminum smelter, your number one concern isn't the bauxite mine, it's the power source.
The power source is paramount. You need cheap and, crucially, uninterrupted power. That's why you see plants like Hindalco, located at Renukut in Uttar Pradesh, built specifically to draw power from the massive Rihen Dam, or the INDL plant at Hirakud in Odisha, near that dam. If the power supply is erratic, the molten aluminum in the pot solidifies, and it's a disaster to restart.
Finally, let's talk about an industry that is perhaps the most visible symbol of India's post-liberalization economy, the automobile industry.
This is truly the great success story of the new era. Before 1991, what did the Indian car market look like?
You had the Ambassador from Hindustan Motors and the Premier Padmini. That was pretty much it.
Right. It was a closed, stagnant market. Hindustan Motors was based in Kolkata and Premier was in Mumbai. But after the 1991 reforms, with delicensing and 100% foreign direct investment allowed, the floodgates just burst open.
And very distinct manufacturing clusters began to form.
They did. Gurgaon, near Delhi, became a massive hub, anchored by the success of Maruti Suzuki. The Mumbai-Pune belt became another cluster with domestic giants like Tata and Mahindra. And then there's Chennai.
Which became known as the Detroit of India.
Yes. Global players like Hyundai, Ford, and others set up huge plants there. The attraction was a combination of things. A major port for exporting cars, a strong pre-existing base of auto component manufacturers, and a state government that was very proactive in attracting investment. It's a perfect example of an agglomeration economy. Success breeds success, and companies cluster together.
So we've traced this incredible arc. We started in the soil talking about the location quotient of wheat in Punjab, and we've ended up at a state-of-the-art car factory in Chennai.
And it's all part of the same story. The agricultural surplus from the Green Revolution fed the growing urban population. The cotton grown on the Deccan Plateau provided the raw material for India's first modern industry. The iron ore and coal from the Chotnagpur Plateau built the steel framework for the entire country. It's all connected.
It really drives home the human element behind all these academic terms.
Yeah.
A location quotient isn't just a number, it's a reflection of a farmer's livelihood. A 5-year plan wasn't just a document, it was the blueprint for creating jobs and communities in new industrial towns.
Absolutely. The economic map of India is just a visual representation of millions of individual lives, all shaped by the constraints and opportunities of geography and policy.
And that leads me to a final thought I'd like to leave you with. For centuries, we've seen how physical geography, the location of rivers, coal deposits, fertile soil, was the primary force dictating India's economic map. The steel plant had to be near the mine. The jute mill had to be on the river.
A kind of geographical determinism.
Exactly. But now, with the rise of these footloose industries like software and electronics, with mini steel plants that can run on scrap metal anywhere there's power, with technology that can create artificial climates or bring water to a desert, are we witnessing the end of that determinism? As technology advances, does the map matter less, or does it just start to matter in a completely different way? At this point, it is important to understand the geographical logic behind this pattern.
Exactly. And when we talk about a pattern, especially with something as huge as the automobile industry in India, it's not just a random scattering of factories.
No, not at all. It's funny, you look at the raw numbers, what do the data say? Something like 12.5 million people employed.
Directly or indirectly, yes. It's massive.
It feels huge and just everywhere. But then you actually look at a map, and they're all clustered together.
They are.
You've got that Delhi-Gurgaon belt, then down south in Chennai, and of course the Mumbai-Pune corridor. It's almost like they've all decided to sit at the same few tables in a giant cafeteria.
That's a perfect analogy, actually. But instead of, social status, the seating chart here is all about economics. It comes down to two big drivers: how close you are to your raw materials and how close you are to your market.
Okay, so that's the classic industrial location theory 101, right?
It is. And for cars, when we say raw materials, we're really talking about one thing above all else: steel. It is the absolute backbone of a car. So you'd think, logically, that you'd build the car factory right next to the steel plant.
To save on shipping all that heavy metal around.
Right. But here's the twist. The automobile industry is what economists call a market-oriented industry. The finished product, the car, is actually way more difficult and expensive to transport than the steel.
It's bulky, it can get damaged.
Precisely. So it's often cheaper to bring the steel to where the customers are rather than build the car out in the middle of nowhere and ship it to the city.
Which perfectly explains the Delhi-Gurgaon cluster. That's the home of Maruti Udyog.
The classic Maruti, that's the car that put a whole generation of Indians on the road.
It really is. And Gurgaon, well, it's not exactly famous for its iron ore deposits.
Not in the slightest. Its location was a strategic market calculation. It's sitting right on the doorstep of the national capital region.
A massive, dense, and relatively wealthy consumer market.
Exactly. But then let's go south. You mentioned Chennai. It's often called the Detroit of India.
Right, you got Hyundai, Ashok Leyland, a whole bunch of others down there. So what's the logic for Chennai? It's not a bigger market than Delhi.
No, but it has something else. A massive, world-class port.
Ah, so this is about exports.
It has everything to do with exports. For a company like Hyundai, Chennai isn't just a factory for selling to Indians. It's a global manufacturing hub.
So they're shipping cars out of there.
All over the world. To Africa, to Europe, to Latin America. For them, being near the water, near that port, is way more valuable than being near a steel plant in, say, Jharkhand.
And then you have the third leg of the stool, the Mumbai-Pune belt.
Yeah.
with Tata and Mahindra. That one feels like a bit of a mix.
It is a mix. You've got the port access in Mumbai for that global reach, but you also have this deep historical industrial base. And Pune specifically has developed this incredible ecosystem of engineering talent and component suppliers.
And just to complete the picture, we should probably mention Kolkata, Hindustan Motors,
The ambassador.
the yellow taxis, a true icon.
It is, though, as we know, that specific cluster has faced some pretty serious challenges over the years. That's a whole other story about industrial decline we could probably get into.
Definitely. But the big takeaway here is that this pattern is all about minimizing costs. And because this industry contributes something like 5% to the entire national GDP, where these clusters decide to form, has a huge ripple effect on the economic health of the whole region.
Absolutely. It's this constant tug of war between where the materials come from and where the finished product needs to go.
Okay, so that's cars. Let's flip the script a bit. Does that same logic, that same tug of war, apply to something completely different, say, fertilizers?
Now that's a great contrast.
Because it's a huge industry for an agricultural country like India, but the inputs are totally different.
Completely different. The logic applies, but the variables in the equation change entirely. With cars, steel is king. With fertilizers, you're dealing with a much more complex shopping list of raw materials.
What are we talking about?
Things like naphtha, rock phosphate, sulfur, gypsum, and perhaps most importantly, in the modern era, natural gas.
So you can't just stick a fertilizer plant wherever you want.
Yeah.
The location is constrained by these materials.
Very much so. And because of that, you see three really distinct types of locations emerge, and each one tells a different story about India's supply chain.
Okay, what's the first type?
The first is the most straightforward. Plants located right next to the raw materials. Think of the coal-based plants in places like Talcher or Ramagundam.
Because they're using the coal itself as a feedstock for the process.
Exactly. And coal is heavy, it's dirty, it's expensive to transport long distances, so you follow what's called a weight-losing logic. You process the heavy stuff right at the source, so you're only shipping the lighter, more valuable finished product.
Makes sense? Build the factory on top of the coal mine. What's category 2?
Category 2 is plants located near oil refineries.
What?
Because they're using a byproduct of the refining process, they use naphtha, or natural gas, as their feedstock. So you see a cluster of plants that are tied to the gas coming from, for example, Mumbai High.
So they're not near a mine, they're near the energy source.
Precisely. They're tapping into that pipeline directly from the refinery.
And the third type?
The third type is really interesting because it actually highlights a major gap in India's own natural resources. These are the plants located near ports.
Let me guess. Because we have to import some of the key ingredients.
You got it. We just don't have large domestic reserves of certain key materials, particularly rock phosphate and potash. The geology just isn't on our side for those.
So we have to buy them from other countries?
We import a huge amount from places like Morocco or Jordan. So what you see is a concentration of fertilizer plants in coastal states. Think Tamil Nadu, think Gujarat. They are built right on the coast to receive these massive ships, process the imported material, and then distribute the finished fertilizer inland to the farmers.
Wow. It's fascinating how the planet's geology basically dictates the layout of a national economy.
Here it is.
I mean, the source notes that the very first fertilizer plant was set up in Sindri way back in 1951. And now India is the third largest producer of nitrogenous fertilizers in the world. That's a massive journey.
It is, and it's a perfect segue into the bigger picture here. We've talked about specific industries, cars and fertilizer, but industries don't like to be alone.
They clump together.
They clump together to share infrastructure, to share a labor pool. We call it agglomeration economics, and it leads to the formation of what we call industrial regions.
Okay, and this is where we get into that amazing nickname I saw in the notes, the Ruhr of India.
The Ruhr of India, yes.
I love that. What does it refer to?
It refers to the Choternagpur Plateau region. It's named, of course, after the Ruhr Valley in Germany.
Which was the heartland of German heavy industry, right? Coal, steel, all of that.
The absolute engine room of their industrial revolution. So the Choternagpur region is our equivalent. It's our heavy metal heartland.
And when you say heavy metal, you mean it literally.
Literally.
Yeah.
This area, which spans parts of Jharkhand, northern Odisha, West Bengal, it is just incredibly rich in minerals. Iron ore, coal, manganese, bauxite, you name it, it's there.
And this is why cities like Jamshedpur, Burnpur, Bokaro exist where they
It
did.
is the only reason they exist. This is the steel belt of India. The logic here is pure, unadulterated geology. The minerals are in the ground here, so the heavy industry has to be here. You can't, move an iron ore mine.
Right. Contrast that with, say, the Mumbai-Pune region. That feels completely different. The origin story there feels less about geology and more about history, more colonial.
Very colonial in its origins. The industrial boom there didn't happen because someone discovered a massive iron deposit under Pune. It happened because of the British and one specific event in 1869 that changed everything.
The opening of the Suez Canal.
Exactly, the Suez Canal.
It seems like such a distant thing. How does digging a canal in Egypt spark an industrial revolution on the west coast of India?
Because it slashed the shipping time and distance between Europe and India dramatically. Before the canal, ships had to sail all the way around the southern tip of Africa.
A huge, long, dangerous journey.
Months long.
Yeah.
Suddenly, with the canal, Mumbai was effectively much, much closer to London and Liverpool. It became the undisputed gateway to India for European trade.
And that coincided with the cotton boom, right?
It did. The nearby Deccan Plateau, with its black soil, grows fantastic cotton. So you had the raw material, and now you had this super fast route to the textile mills in Manchester. That combination led to the explosion of the cotton textile industry in and around Mumbai.
And they had the power source, too. I remember reading that the hydropower from the Western Ghats was crucial for running the mills.
Yes, so the geography provided the power, but it was history and global trade that provided the market access. But here's the problem, and it's a theme we'll see again. That region is now facing what the experts call saturation.
Saturation, you mean it's just...
Stop. In a word, yes. The cost of land is astronomical. The infrastructure, roads, power, water is choking under the pressure. And maybe the biggest problem is that a lot of the old industries are working with obsolete machinery.
It's an aging industrial giant.
It is. You can't easily expand a factory in the middle of Mumbai anymore. There's just no space.
Which sounds very similar to the story of the Kolkata-Hooghly region. The notes on that area read like a list of problems. Silting of the river, labor unrest. It sounds like a region that had its golden age and is now really struggling.
The Kolkata-Hooghly region is a classic case study in what can go wrong. It grew up along the banks of the Hooghly River for a very logical reason.
Easy transport.
For sure. Raw materials like jute from the Bengal Delta, indigo, tea from Assam, it could all be brought down the river cheaply. Plus, you had abundant coal nearby from the Raniganj and Choria coal fields. And of course, it was the capital of British India. It was the center of everything.
So what happened? What went wrong?
It was a brutal 1-2 punch of geography and politics. First, the river itself. The Hooghly is a distributary of the Ganges, and it carries a massive amount of silt. The riverbed is constantly rising.
Meaning the river's getting shallower.
Yes, and that is a death sentence for a modern port. The new generation of container ships are gigantic. They have very deep drafts. If your river is too shallow, they simply can't reach your port. They'll go somewhere else.
And the politics. The notes explicitly mention labor unrest.
It was a huge factor, particularly in the 60s and 70s. The source material points to the Naxalite movement as a major cause of what they call a flight of capital.
Industrialists got spooked.
They were terrified there was a perception of instability, so they stopped investing. They packed up their money and moved it to regions they perceived as being more stable.
And that brings us to the Gurgaon Delhi Meerut region. The notes describe it as having a peaceful industrial environment, which sounds like a very polite way of saying the investors felt safer here.
In economic geography, political stability is a resource, just like iron ore or water. This northern region is mineral poor. You won't find any coal mines in Gurgaon.
Right.
But it is incredibly market rich. And when you compare it to the labor turbulence that was happening in the East back in the 70s and 80s, it offered a much more predictable, stable environment for someone looking to build a factory. That stability, powered by cheap hydroelectricity from the Bakra Nangal Dam, was its key advantage.
It's proof that sometimes politics and policy can actually override geology.
They absolutely can.
So we have these different regions, each with its own story. Geology dictates the steel belt, colonial history dictates the coasts, and political stability helps the north. But then the calendar flips to 1991, and everything changes.
The watershed moment.
Liberalization.
Before 1991, from what I understand, the government controlled everything with an iron fist. It was the license Raj. It was. If you wanted to start a factory, you needed a license. If you wanted to expand your factory, you needed another license. The state decided what you could produce, how much you could produce, and where you could produce it. It was incredibly bureaucratic.
And the 1991 reforms just blew all that up.
Pretty much. They abolished industrial licensing for almost everything. They moved India from a command-style economy toward a market-driven one.
I saw there are a few exceptions, right? The list included things like alcohol, aerospace, hazardous chemicals.
Yes, there are 16 specific industries that, for reasons of public health, safety, or national security, still require a license, which, makes sense.
Yeah, you probably don't want just anyone setting up an explosives factory in their garage.
Agreed. But for everything else, the doors were thrown wide open, and crucially, they also threw open the doors to FDI, foreign direct investment.
And that's the cue for the multinational corporations, the MNCs, to enter the stage.
That's right. Firms that own and control production in more than one country. We tend to think of the foreign ones, like Ford or Samsung, coming into India.
But it's also about Indian companies going out, right? Tata, Infosys, becoming global players themselves?
Exactly. Liberalization was a two-way street. It allowed Indian firms to acquire companies abroad and become MNCs in their own right.
Now, this is where it gets complicated, because the source material presents a real debate here. A list of pros and cons. On the pro side, MNCs bring in money, they bring in new technology.
Correct. The argument is they inject much-needed capital into the economy. And they bring advanced technology and management practices, which creates a positive spillover effect. It forces domestic companies to up their game to compete.
Okay, but then there's the con side. And one phrase from the source really stood out to me: obsolescence of technology. That sounds like a polite way of saying they dumped their old secondhand junk on us.
It's a genuine and long-standing concern. The fear is that a multinational might transfer technology to India that is, say, one generation behind what they're using in Europe or Japan. They get to squeeze a few more years of profit out of older machinery while still appearing advanced in the Indian context.
And then there's the impact on the little guy, the damage to local cottage industries.
That's the other big criticism. If a giant MNC starts mass-producing, let's say, plastic buckets with huge economies of scale, what happens to the local artisan who's been making and selling handmade pottery in the village market for generations?
They can't compete on price.
They simply cannot. They get wiped out. And then there's the final issue, which is profit repatriation.
Meaning the money doesn't stay here.
A significant chunk of the profits generated in India are sent back to the parent company's home country. So instead of being reinvested to build more factories in India, that wealth leaves the Indian economic ecosystem.
Okay, so to try and get the benefits of foreign investment while minimizing the downsides, the government came up with a new strategy: SEZs, special economic zones.
A concept borrowed directly from the Chinese playbook. China's meteoric rise was powered by SEZs like Shenzhen and Ximen.
So what is an SEZ exactly? How does it work?
The basic idea is to create a special ring-fenced area that is, for all practical purposes, treated as foreign territory for trade and customs. It's a duty-free enclave.
Wait, foreign territory?
That's
You're
right.
saying a factory in, say, Noida SEZ is technically not in India for trade purposes?
From a trade operations perspective, yes. It's a bit of a legal fiction, but a powerful one. If a company in domestic India sells steel to a factory inside the SEZ, that transaction is officially counted as an export.
Even if it's just going across the road.
Even then. And if that SEZ factory then sells its finished product back into the regular Indian market, that's treated as an import and is subject to customs duties.
That sounds incredibly complicated. What's the point?
The point is to create a frictionless environment for export-oriented manufacturing. Within that zone, you strip away all the domestic taxes, tariffs, and red tape. Companies get long tax holidays, single window clearance for all their permits. It's a VIP lounge for business.
And these zones have to be massive, right? The notes mention a minimum size of 1,000 hectares for a multi-product SEZ.
They have to have scale to be effective. The goal isn't just to build an industrial park, it's to build entire integrated industrial townships with their own power, water, housing, and infrastructure.
Speaking of industries that operate on a massive scale, let's shift gears to what the notes call the invisible industry, tourism.
A fascinating and paradoxical sector.
Oh, so?
Well, according to the data, India's share of total world tourism is tiny. It's only about 0.5%.
That's surprisingly low.
It is. But domestically, it is an enormous generator of employment. It touches everything from hotels and transport to guides and restaurants.
And it's evolving way beyond just, going to see the Taj Mahal. The sources list some really interesting new types. Adventure tourism, for one.
Yes. River rafting and kayaking in the Himalayas, skiing up in Gulmarg, that side of things is booming.
And then there's medical tourism.
This is a purely economic phenomenon. The quality of high-end medical care in India is world-class, but the cost is a fraction of what it is in the West.
So people fly in from the US or the UK for surgery.
All the time. They can fly to India, get a major procedure like a heart bypass or a hip replacement, recover for 2 weeks in a 5-star hotel, and the total bill is still less than what their insurance deductible would have been back home.
That's incredible. But I really want to zoom in on the section about ecotourism, because the source material raises a really sharp, critical point here.
Yes, the problem of greenwashing.
Exactly. The ideal, the marketing pitch, is that ecotourism is socially conscious, it's sustainable, it benefits local communities. But the reality on the ground can be very different.
The notes call a lot of it business as usual, just disguised with a green label.
And they give that heartbreaking example of so-called nature hikes that end up scaring nesting birds away from their nests.
It's the ultimate tragic irony. People go to appreciate nature, and in the process, they inadvertently stress it out or damage it.
Or the garbage and pollution problems that follow tourists into previously pristine areas.
It brings up a really tough, fundamental question. Can you actually commercialize a wilderness without destroying the very thing that makes it special? If you build a luxury eco-resort deep in a forest, you still have to build a road to get there. You still have to deal with the sewage, the diesel for the generators.
It's a real dilemma.
Yeah.
But to get those tourists, or any goods for that matter, to these places, you need transport. You need the arteries of the economy, roads and rail.
And India's road network is, by the numbers, one of the largest in the world. We're talking about 4.1 million kilometers of roads.
That's a mind-boggling number. And the key advantage, as the notes point out, is that door-to-door service.
That is the unique selling proposition of road transport. A train can get goods to the station in the city, but a truck is what takes it that final mile to the warehouse, to the factory, to the shop.
And that flexibility is absolutely critical for perishable goods, right?
Vital. Things like milk, fresh vegetables, flowers, they're on a ticking clock. You can't have them sitting around waiting for a fixed train schedule. A truck can leave the second it's full.
And we've seen these massive, ambitious projects to upgrade the network, like the Golden Quadrilateral.
The GQ, yes. Connecting the 4 metros Delhi, Mumbai, Chennai, Kolkata with 6-lane superhighways. It's been a game changer for long-haul freight.
But, and there's always a but, the quality is not uniform, not by a long shot.
Far from it. The source material states that nearly half of all the roads in India are unmetalled.
Which is a polite word for a dirt track.
It's a mud road, which means come the monsoon season, it's basically useless.
So for 3 or 4 months of the year, vast parts of the country are effectively cut off.
It's a huge structural problem for the economy. You can't run a modern supply chain if your infrastructure dissolves in the rain. And that's before we even get to the checkposts.
Ah, yes. The notes mention multiple checkposts as a source of delay and corruption.
The dreaded octroi and state border checks. You see these endless lines of trucks, sometimes waiting for hours, even days, just to get a piece of paper stamped and pay a tax to cross from one state into another. It's a massive drag on efficiency.
Now, compare that with the railways. 4th largest network in the world. This is the real workhorse for bulk freight, isn't it?
Absolutely. If you need to move thousands of tons of coal or iron ore or cement, you're not putting it on trucks. You're putting it on a train.
But there's this weirdly complicated issue with the railways that I never fully understood. The gauge problem.
The gauge problem. Yes, it's a legacy of history.
Broad gauge, meter gauge, narrow gauge. Why on earth did we have 3 different sizes of track?
Well, the British built the main profitable trunk routes using broad gauge, which is wide and stable. But when they built lines into less populated areas or up into the hill stations, they used the cheaper meter gauge or narrow gauge. They were cheaper to build and could handle the sharper curves in the mountains.
But logistically, it must have been a complete nightmare. You can't run a broad gauge train on a meter gauge track.
It's a nightmare. Imagine you have a train full of food grains coming from Punjab, heading to a town in the northeast. At some point, the gauge changes. The entire train has to stop. Every single sack has to be manually unloaded and then reloaded onto a different, smaller train. The inefficiency is staggering.
Which is why they launched Project Unigauge.
A massive, decades-long effort to convert almost the entire network to a single, uniform broad gauge. It's a hugely expensive and difficult task, but it's essential for creating a truly unified national market.
The map of rail density is also really telling. It's incredibly dense in the northern plains, but then it gets really sparse in the hill states or the deserts of Rajasthan.
Once again, geography is destiny. The northern plains are flat, the land is soft, the population is high, and there's a lot of agriculture. It's the perfect environment for building railways.
And the opposite is true for the Himalayas.
Exactly. Trying to build and maintain a railway line in steep, geologically unstable mountains with heavy rainfall and landslides is an engineering and financial challenge of a whole different magnitude.
Okay, so if road and rail are difficult, that leaves water. Let's talk about ports.
India's coastline is its gateway to the world. And we have a fascinating variety of ports. You mentioned Chennai earlier, which is actually an artificial harbor.
Artificial. How do you build an artificial harbor?
Well, the coast at Chennai is very straight, and the water is naturally quite shallow. There's no natural bay or inlet to protect ships. So over a century ago, they had to build these enormous man-made walls called breakwaters out into the sea to create a calm, protected area for ships to dock. And they have to constantly dredge the seabed to keep it deep enough.
Contrast that with something like Vishakhapatnam.
Vizag is the complete opposite. It's one of the best natural harbors in the country. It's deep, it's landlocked, and it's perfectly protected from storms by a huge rock promontory called the Dolphin's Nose.
And then there's Kandla. The story behind Kandla is really a story about partition.
It is. Before 1947, the primary port serving all of northwest India, Punjab, Rajasthan, Gujarat was Karachi.
Which, after partition, ended up in Pakistan.
Exactly. Overnight, India lost its main port on the west coast. There was a huge logistical vacuum.
So Kandla had to be built from scratch to fill that void.
It was developed specifically for that purpose, to handle the trade, especially the import of crude oil and petroleum products that used to flow through Karachi. Today, it's one of our most important ports for energy security.
But while our seaports are bustling, the notes describe our inland waterways as a missed opportunity. We have over 14,000 kilometers of navigable rivers and canals, but we barely use them for transport. Why is that?
There are a few key reasons. The first is seasonality. Most Indian rivers are rain-fed, not snow-fed. This means they are raging torrents during the monsoon.
And then just a trickle in the dry summer months.
Right. You can't run a reliable year-round commercial shipping service if the river itself disappears for half the year.
What's the other big reason?
Silting, which we talked about with the Hooghly, is a problem in many rivers, making them too shallow. But honestly, the biggest factor is competition. Road and rail are just so much faster. In a modern, just-in-time economy, speed often trumps the lower cost of water transport.
Speaking of speed, air transport.
The fastest of all. And in some parts of the country, it's not a luxury, it's a lifeline.
You're talking about the Northeast.
Absolutely. The terrain there, the dense forests, the mountains, the heavy rains, makes building and maintaining roads and railways incredibly difficult and expensive. For many places, air travel is the only reliable link to the rest of the country. It's what holds the region together.
And just like with industry, there was a big policy shift here in the 90s, the open sky policy of 1992.
Yes. Before that, domestic air travel was a government monopoly. It was just Indian Airlines and Air India.
And it was expensive and often inefficient.
The open sky policy changed all of that. It allowed private airlines, Jet Airways, Indigo, SpiceJet to enter the market. The competition led to a massive increase in connectivity and a dramatic drop in prices. It democratized air travel in India.
Now, I want to pivot to a really specific and controversial topic that brings together geography, transport, religion, and politics. Adam's Bridge or Rem Setu.
A very complex and sensitive issue. This revolves around the Setu Samudram Ship Channel project.
Okay, so the goal of the project, on paper, seems straightforward enough. Ships traveling from India's west coast to the east coast currently have to go all the way around Sri Lanka.
A long detour.
Right. So the project's goal was to dredge a navigable channel through the shallow waters between India and Sri Lanka to create a shortcut. The claim was it would save about 30 hours of shipping time.
It's a classic economic efficiency argument. Save time, save fuel. The problem is what lies in the path of that proposed channel.
A chain of limestone, shoals, and sandbars.
Which, from a geological perspective, the evidence suggests are natural formations. Coral reefs and sandbanks formed over millennia. However, that same formation is revered in Hinduism as Ram Setu. The bridge believed to have been built by Lord Rama's army, as described in the Ramayana, to rescue Sita from Lanka.
So you have a direct clash between a modern infrastructure project and a site of immense religious and cultural significance.
It's the ultimate conflict. Save 30 hours of fuel versus preserve a sacred ancient structure. The project has been stalled for years precisely because of this. It's a powerful reminder that in India, geography isn't just about rocks and rivers. It's layered with millennia of culture and belief. You can't just look at a satellite image and draw a straight line.
That is a fascinating point. And moving from ancient bridges to the absolute cutting edge, let's talk about the communication revolution and, of course, the space program.
Two of the biggest Indian success stories of the last few decades, without a doubt. The telecom sector's transformation is just mind-blowing.
I still remember the days of landlines, where you had to book a trunk call or wait literally years to get a phone connection installed.
And now India has one of the highest rates of mobile phone penetration and some of the cheapest data rates in the entire world.
What was the key to that transformation?
The shift from wired to wireless. India was able to leapfrog an entire generation of technology. We didn't need to spend decades laying copper wires to every single village. The mobile phone and the cell tower allowed us to connect the country almost overnight.
And then you have ISRO, the Indian Space Research Organization. The notes tell that incredible rags to riches story,
Yeah.
literally transporting rocket parts on the back of a bicycle in the early days.
It's an iconic image from the early launch station in Thumba. A rocket nose cone being wheeled along a village path on a bicycle. To go from that humble, almost unbelievable beginning to successfully sending a mission to Mars on the first attempt. It's one of the most remarkable scientific journeys of any nation.
And it's so important to stress that ISRO's mission was never just about prestige. It wasn't just planting a flag for the sake of it.
No, from day one, the vision of its founders, like Vikram Sarabhai, was to use space technology for national development.
The source highlights satellites like INSAT.
INSAT is a perfect example. Its primary job is weather prediction. The ability to accurately forecast the path and intensity of cyclones has saved countless thousands of lives along India's coastline. That's a direct, tangible benefit.
Or AGUSAT, the education satellite.
Using satellite technology to beam quality educational content to remote classrooms that don't have specialist teachers, it's about using high technology to solve grassroots problems.
And then there's the PSLV, the Polar Satellite Launch Vehicle. It's called the workhorse of ISRO.
Because it's just so incredibly reliable. It's had dozens and dozens of successful launches in a row. It's become so reliable, in fact, that other countries now pay India to launch their satellites for them. Space has become a commercial export.
Which brings us neatly to the final piece of the puzzle, the money, international trade, and the balance of payments.
The country's official bank statement, essentially.
And the data shows that what we sell to the world has changed dramatically over time. We used to be an exporter of raw materials.
Jute, tea, iron ore, rawhides, we exported the basic stuff.
And now,
Now we're exporting manufactured goods, complex engineering products, pharmaceuticals, and, of course, software and IT services. We've moved up the value chain. That's the hallmark of a developing economy.
but despite this progress, we still have a persistent problem, a trade deficit.
An unfavorable balance of trade. Year after year, the value of the goods we import is greater than the value of the goods we export. We buy more than we sell.
And the sources are very clear on the two main culprits driving this deficit.
Petroleum and gold.
The oil bill makes sense. We have a huge growing economy. All those cars we talk about need fuel, and we have to import the vast majority of our crude oil. But gold,
It's a massive, and some would say unproductive drain on our foreign exchange reserves. There is a deep-seated cultural obsession with buying and holding physical gold and silver.
so we're basically spending billions of dollars, which we earn from our exports, to buy gold from other countries, only to have it sit in bank lockers and private homes here.
That's a fairly accurate summary. It's a huge economic drag.
So here's the big question. If we are consistently buying more from the world than we're selling to it, why aren't we bankrupt? How do we pay the bill at the end of the year?
The answer lies in the invisibles.
That sounds like an economic superhero team.
In a way, they are. Invisibles refers to two main things. First, our exports of services, all that software and IT work we do for the world. And second, and this is the really crucial part, remittances.
Money sent home by Indians working abroad.
Exactly. The software engineer in Silicon Valley, the doctor in the UK, the construction worker in Dubai, all sending a portion of their earnings back home to their families in India.
And that flow of money is big enough to make a difference.
It's enormous. For many years, India has been the world's largest recipient of remittances. Those billions of dollars flowing in every year are what bridges the gap. It's what pays for our excess imports of oil and gold.
Wow. So to recap this entire deep dive,
Hmm.
we've gone from the geographical logic of why a car factory is in Chennai to the historical logic of why Mumbai became an industrial hub. We've talked about the Ruhr of India, the problems with our roads, the challenge of our railways, the missed opportunity of our rivers, and we ended up in space.
And the common thread, the red line connecting every single one of those points, is geography. Geography dictates where the coal is, which dictates where the steel plant has to be. But then human ingenuity and policy building roads, digging ports, creating SEZs is this constant attempt to either leverage geography or, in some cases, to overcome its limitations.
We're constantly either working with the map or actively trying to redraw it.
Precisely. We build an artificial port where the coast is straight. We fly planes over mountains that are too difficult to build roads through. We use satellites to connect villages that don't have fiber optic cables. It's a constant dance with the physical reality of the land.
So as you, our listener, think about all this, the takeaway is that to really understand an economy, you can't just look at the stock market tickers.
Yeah.
You have to look at the map. You have to see where the rivers flow, where the mountains rise, and where the roads end. That's where the real story is written.
Well said.
And with that, let's leave you with a final provocative thought to mull over. We have spent this entire time talking about physical geography, coal, ports, soil, rivers. But as India increasingly becomes a powerhouse in the digital realm, in software, in fintech, in space, is a new kind of digital geography starting to matter more?
That is the multi-trillion-dollar question. In a future of remote work, artificial intelligence, and cloud computing, will it still matter if your city is near a coal mine or a deep water port? Or does the physical reality of moving things, the fact that your online order still has to travel on a real truck on a real road, mean that physical geography will always be the ultimate ceiling on our growth?
Something to think about. Thanks for joining us for this deep dive.
Thank you.
At this point, it is important to understand the geographical logic behind this pattern.
Exactly. And when we use the word pattern here, we're not just, talking about a random scattering of people.
Not at all.
We are talking about what is perhaps the most complex human mosaic on the planet.
It's a really bold claim, but all the sources we're looking at today seem to back it up.
Right.
We've got a whole stack of anthropological and geographical studies on India.
Mm-hmm.
And usually when you look at a map, you see the physical stuff first, right? Mountains, rivers, plateaus.
Of course.
But the core argument in this material is that you can't actually understand who lives where in India without understanding the shape of the container they fell into.
The container is the perfect analogy. It really is. Anthropologists have often described the Indian subcontinent as a massive funnel-shaped museum. It's a geographical cul-de-sac.
A cul-de-sac, you mean like a dead-end street?
In a way, yes, a
Yeah.
big one. Just think about the layout on a continental scale. To the north, you have the Himalayas.
The highest, most formidable wall in the world.
Right. And then you have the oceans surrounding the south, the east, and the west. So for the last, million years, and the sources are looking back that far, you've had these diverse groups of humans drifting into this funnel.
They came through the mountain passes in the northwest.
Or the dense corridors in the northeast, yeah.
And once they got in, the geography acted as a kind of trap.
Or a sanctuary. That's the key duality, you see. They couldn't easily back out because of the pressure of new waves of people coming in behind them.
And they couldn't go forward into the ocean.
Exactly. So what happens, they find a niche, a fertile river valley, a dense forest up in the hills, a high-altitude plateau. They settle there. And because the geography of India is so segmented, riven by all these rivers and hills, they stay distinct.
So they don't just blend into a single gray mass.
No, not at all. They remain like separate, colorful pieces of confetti.
It's like a game of geographical Tetris. The pieces just fell in and got stuck where they fit.
That's a great way to visualize it. And this brings us to this concept of geographical determinism. The physical landscape. It didn't just provide a background for Indian history.
It dictated it.
It dictated it. It determined that the big armies would march through the open plains, but the indigenous tribes would survive up in the hills where the cavalry couldn't go.
So our mission for this deep dive is to decode that map. We're not just doing a history lesson with dates and battle.
Yeah, this is different.
We're trying to peel back the layers, race, tribe, caste, religion, and figure out why they are where they are. We're moving beyond the what into the geographical why.
It's the only way to really get it. You just can't separate the culture from the land.
Okay, let's unpack the first layer then. The source material starts with something that feels a bit controversial in modern terms. Race.
It is sensitive, yeah.
Yeah.
And the source explicitly mentions that race is biologically very difficult to define. Human beings are incredibly variable.
We're all Homo sapiens.
Exactly. We're all distinct individuals, but, you know, early anthropologists and geographers, they needed a way to classify the immense physical diversity they saw in India.
Right. And they suggest ethnic group is probably the better term to use now.
Much better. Groups bound by culture, religion, language. That's more practical.
But to understand the history, we have to look at how they used to classify people physically. The sources mention the protagonists of the theory of evolution.
Yes. The prevailing anthropological view is that the ancestors of modern man originated in East Africa, and about 1 million years ago, they migrated into Asia and eventually into the Indian subcontinent.
So everyone in India is ultimately a migrant if you go back far enough.
If you go back far enough, absolutely.
But some arrived much, much earlier than others. And the classic classification, the one that really set the baseline for how we think about this, comes from Sir Herbert Risley in 1901.
Sir Herbert Risley, he was the census superintendent during the British Raj. Now, his methods were of his time, let's put it that way.
He was literally measuring nose bridges and head shapes.
He was. But his broad classification created a map that geographers still reference, to understand the base stock of the population. He tried to classify the entire population into 7 distinct groups.
And if you look at his map, you see this really clear north, south, and east-west gradient.
A very clear one.
Okay, let's break those down.
Yeah.
If I'm standing in the northwest, say Punjab, Rajasthan, Kashmir, what am I looking at, according to Risley?
You're looking at the Indo-Aryans. Risley described them as typically tall, fair-complexioned with long heads. These represent the waves of migration that came from Central Asia through the passes.
Got it. So that's the northwest. Then if you travel all the way south,
To Tamil Nadu, Andhra Pradesh. There you have the Dravidians. This is the foundational stock of the peninsula.
okay.
Risley noted they were typically shorter in stature with darker complexions. They represent one of the oldest settled civilizations in the region.
And they might be linked to the original Indus Valley people who moved south when the Aryans arrived.
That's one of the leading theories, yes.
Okay. And then if you look at the map over towards the Himalayas in the northeast.
That's the Mongoloid group. So
Okay.
Assam, the Nepal border, Ladakh. Their physical characteristics are very distinct. The most notable being the epicanthic fold.
The distinctive shape of the eye.
Right. Along with less facial hair and a shorter stature, these groups have strong affinities with Tibet and East Asia.
So you have these 3 big poles, Aryan in the northwest, Dravidian in the south, Mongoloid in the northeast. But India isn't just 3 separate blocks. There's a massive middle ground.
Exactly. And Risley called these the mixed zones. For instance, in the vast plains of Uttar Pradesh and Bihar, he identified the Aryo-Dravidians.
A melting pot region.
A real melting pot, where the upper strata of society often show more Aryan traits and the lower strata show more Dravidian traits. It suggests centuries of social mixing that eventually got sort of frozen in place by the caste system.
And what about over in the west? Maharashtra and Gujarat.
He called them Scytho-Dravidians, which suggests a mix of that Dravidian base with Scythian invaders, the Sakas.
Oh, right.
They came from Central Asia but took a different route than the Aryans.
It really paints this picture of waves just crashing into each other. You have these waves of people coming in and blending at the edges. But there were other views too, right? Risley wasn't the final word on this.
No, definitely not. Later scholars like B.S. Guha and J.H. Hutton, they refined this. They looked even deeper into the past. And they identified the Negritos as likely the absolute earliest arrivals.
Negritos.
Yes. When we say Negrito, we're talking about a group that physically resembles the peoples of Africa, or, say, Australian Aboriginals, more than the typical Indian look.
And where are they now?
Today, they're found mostly in the Andaman and Nicobar Islands groups like the Jarawar or the Sentinelese, who've remained isolated for tens of thousands of years.
Wow.
But you also find very small pockets in the hills of Kerala, like the Kadar tribe. They're characterized by very dark skin and frizzly hair.
So they're the remnants of the very first human migration out of Africa along the coastlines.
Precisely. They represent the first human footprint in India.
And then there's the group that forms the bedrock of the tribal population.
That would be the Proto-Australoids. Guha identifies them as the people who came after the Negritos, but before the Dravidians and Aryans. This is the genetic and physical bedrock of the tribal communities in central India. The Bhils, the Gonds, the Santhals.
So why does all this classification matter today? I mean, like you said, we don't go around measuring people's noses anymore.
It matters because it helps explain the cultural geography. It sets up this visual map of India not just as political states, but as distinct genetic zones. It helps explain why a farmer in Punjab might look different from a fisherman in Kerala or a tea planter in Assam.
So it validates the idea that India is a collection of these distinct ecological niches that preserve differences for millennia.
That's the core idea, yes.
Speaking of ecological niches and preserving differences, let's talk about the people who live in the deepest niches of all. The sources call them the Fourth World.
The scheduled tribes, or as they're known in India, the Idavasis, the original inhabitants.
Yes. This is a fascinating designation. We've all heard about the Third World, but Fourth World? That implies something even more marginalized, or at least distinct.
It refers to indigenous people who live within a larger nation state, but maintain their own distinct culture, often geographically isolated. And in India, these are people who are distinct from the caste society of the plains.
I love the quote the source uses to describe their philosophy. It says their cooperative attitude is, from everybody according to his capacity to everyone according to his needs.
It sounds a bit like Marx, doesn't it?
It really does.
But it's actually ancient tribal communalism. In many tribal societies, the concept of private property is much, much weaker than in the caste-based agricultural plains.
The land belongs to the community.
Right. Resources are shared. If you hunt a deer, the meat is shared. If you need to build a house, the whole village helps.
So where are they? If I'm looking at that map, where do I find the tribes?
You find them in the rough terrain. Remember our geographical logic.
Right.
The fertile plains were taken over by the agrarian caste society. The tribes were either pushed into or just survived in the hills and forests. There are three main belts.
Let's hit the belts.
Okay, first, the northeast. Nagaland, Mizoram, Meghalaya. Here, the percentage of tribal population is huge, over 80 or 90% in some states.
But the absolute numbers are smaller.
Exactly, because the overall population is lower. And these are largely Mongoloid tribes.
Okay. Second belt.
The central tribal belt, this is the heartland. Madhya Pradesh, Chhattisgarh, Jharkhand, Odisha, this is where the sheer numbers are. We're talking millions of people. This is the home of the Gonds, the Santals, the Bhils.
And the third?
The southern pockets. These are smaller, more isolated groups in the Western Ghats and the Nilgiri Hills. These are often the most ancient groups, geographically cut off by dense jungles for centuries.
I really want to zoom in on some of these specific tribes because the details in the source material are they're wild. They completely overturn the stereotype of the conservative Indian villager. Let's start with the Gonds.
The Gonds, one of the largest tribal groups in the world, not just India. They are concentrated in the Vindhya and Satpura mountain ranges in central India.
What jumped out at me was this concept of the go tool.
Ah, yes, the Go Tool, a fascinating institution.
It sounds like some kind of modern social experiment, but it's ancient. It's a youth dormitory.
It is. In traditional Gond society, unmarried boys and girls sleep in separate apartments or a large communal house, and that's the Go Tool. But it's not just the place to sleep, it functions like a club.
Or a secret society.
In a way, it has its own hierarchy, its own officers, captains, masters of ceremony, and the very strict rules.
And the purpose is basically courtship, right?
Courtship and social training. It's where they learn the songs, the dances, the folklore of the tribe. It's where they learn how to interact with the opposite sex. It culminates in marriage, but until then, it's a space of relative freedom and education, managed entirely by the youth themselves.
That is just such a contrast to the rigid, conservative social norms we usually associate with rural India.
And that's the key difference. Tribal societies often have much more liberal social norms, particularly around gender and marriage, compared to the caste Hindu society. The Fourth World really does operate on a different set of rules.
Speaking of liberal norms, let's look at the Bhils.
Yeah.
They're in western India, Rajasthan, Gujarat.
The name Bhil is believed to come from the Dravidian word for bow.
So they were archers.
Historically famous as archers and guerrilla fighters, yes.
And the source mentions their social quirk when it comes to marriage.
Yes, the Bhils grant significant freedom to women in choosing their partners. The practice of elopement is actually a recognized social mechanism. If a couple runs off, the village panchayat, the council, often just validates the marriage later.
So it's not seen as a crime.
Not at all. It's a recognized path to marriage.
And they also have a fondness for madhu.
Alcohol. Mahul. to be specific. It's
Ah.
very central to their social life and their rituals. Again, this distinguishes them from orthodox Hindu castes, where alcohol might be taboo or seen as polluting. For the Billas, it's a gift from the forest.
Okay, let's move east to the Santals. West Bengal, Jharkhand.
The Santals are fascinating because they're very settled, they aren't nomadic, they're excellent agriculturalists who cleared the forests of the Chotanagpur Plateau. Their villages are extremely organized.
Usually with a straight main street.
And a designated headman called the Manji,
Yeah.
very structured.
And they love music.
Oh, obsessively. The source notes their love for dance and the flute. Their life cycle rituals are almost entirely musical. They also have a very clear social contract. Monogamy is the norm, but divorce and remarriage are allowed and regulated. It's a very pragmatic society.
Finally, let's go all the way to the northeast, the Nagas.
The Nagas are hill people. They live on the ridges of the mountains in Nagaland. And because the terrain is so steep, they practice jimming shifting cultivation.
And also terrace farming.
Yes, very sophisticated terrace farming on the hill slopes.
They also have a dormitory system, don't they? Similar to the Gonds.
Yes, it's called the Morung. But the Morung was historically more than just a social club. It was a defense institution.
Oh, interesting.
In the days of intervillage warfare, the Morung was where all the young men slept so they'd be ready to defend the village at a moment's notice. It was a guardhouse as much as it was a school.
And the source notes something interesting about language there, that English is widely adopted.
That's a direct result of missionary activity during the British era. It's become a unifying language among the many different Naga tribes who all speak their own, often mutually unintelligible dialects. It connects them to the wider world.
So we have the tribes in the hills. Let's now descend into the plains. And this is where we run into the massive social structure that defines so much of India, the caste system.
If the tribe is the social structure of isolation, caste is the social structure of interaction.
That's a great line. The source traces the roots all the way back to the Rig Veda, specifically the Purusha Sukta hymn.
Yes, the famous metaphor where society is created from the body of the creator god. The Brahmins, the priests, came from the mouth. The Kshatriyas, the rulers, from the arms.
The Vaishyas, traders from the thighs, and the Shudras, the servants, from the feet.
That's the one.
And originally, this might have been a flexible system, but over time, it hardened into a rigid hierarchy.
Correct. The post-Vedic period saw the consolidation of power by the Brahmins. It transitioned from a classification of labor to a rigid hierarchy defined entirely by birth.
But here's where it gets really interesting for me. We usually think of caste as just, I don't eat with you or I don't marry you. But the source dives deep into the Jajmani system. And this isn't just social, it's profoundly economic.
It is the economic glue of the traditional Indian village. The Jajmani system was a system of hereditary exchange of services.
How did it work exactly?
Well, you had the Jajman, usually the landowning patron caste, and then you had the Kemin, the service providers, the barber, the blacksmith, the carpenter, the potter.
So if I'm the village barber, I cut the Jajman's hair all year round. I don't get paid cash every time, do I?
No, that's the key. You don't get cash per haircut. Instead, you get a fixed share of the grain at harvest time. You might get free food during festivals, fodder for your animals, or protection in times of trouble. It was a cashless, mutual obligation society.
It sounds kind of nice in theory, job security. But the source notes it was pretty unequal.
Oh, very unequal. The Kamin, the worker, was always regarded as inferior. And the relationship was hereditary. You couldn't just quit and find a new patron. You were bound to your Jajman's family, generation after generation.
But it did keep the village self-sufficient.
Completely. Every village had every service it needed to survive without outside help.
And geographically, this system is most prevalent in the fertile plains, right?
Exactly. The agrarian belt Uttar Pradesh, Bihar, West Bengal, Punjab. The source notes that while the scheduled tribes are in the hills, the scheduled castes, the Dalit communities who perform the most menial tasks in this system, are ubiquitous in the plains.
And there's a paradox mentioned here, too. Caste is a Hindu concept, theoretically.
Yes, but the geography of culture is sticky. The source is very clear that the caste system permeated into Indian Islam, Christianity, and Sikhism.
Wow.
You find castes among Muslims and Uttar Pradesh weavers, butchers, all with their own distinct hierarchies. You have Dalit Christians in the south. The social hierarchy was so dominant that even egalitarian religions adapted to it in the Indian context.
It's like the land itself enforces hierarchy. Okay, let's zoom out again and look at the cultural map through language and religion.
If you look at a linguistic map of India, you are looking at a map of its history. It's It's that clear.
And we have 4 main families.
The biggest, by far, is Indo-Aryan. It covers about 73% of the population. This is the North and the West Hindi, Bengali, Punjabi, Gujarati. All these languages have roots in Sanskrit and the migrations from Central Asia.
Then you go south.
And you're in Dravidian territory. About 20% of the population, Tamil, Telugu, Kannada, Malayalam, and these are totally, completely distinct from the northern languages.
The Hindi speaker cannot understand Tamil at all.
Not a word. The syntax, the vocabulary, the roots, everything is different. This linguistic line represents the geographical divide between the Gangetic Plain and the peninsula,
And the other 2 families.
Austric and Sino-Tibetan, and these match the tribal belts we just discussed. Austric languages are spoken by the tribes in central India, like the Santhals.
And Sino-Tibetan by the tribes in the northeast.
Exactly. It perfectly overlaps with the racial map we started with.
It's incredible. Geography, race, and language are 3 maps that you can just stack right on top of each other.
Almost perfectly, yes.
Now, religion, Hindus are the majority, obviously, at about 82% according to the source data. But the minorities have very specific geographies.
They do. And looking at the minority concentrations tells a story. Muslims, for example, are not evenly spread. There are huge concentrations in the Kashmir Valley, in the Ganges Delta on the Bengal-Assam border, and in pockets of Kerala.
And Christians.
That's a coastal and a hill phenomenon. You find them in Goa and Kerala coastal regions that had early contact with European traders and missionaries.
Right.
But you also find very high concentrations in the tribal northeast Nagaland, Mizoram. That's the result of 19th and 20th century missionary work in those isolated hill tracts. Highly, highly concentrated in Punjab. And the source makes an interesting connection here to the Green Revolution. The prosperity of the Sikh community is deeply linked to the agricultural boom in that specific region.
So the geographers, they synthesize all of this, language, religion, race, into what they call cultural regions. I like some of the names they gave these regions.
They are quite poetic, aren't they? For example, the Himalayas are called the Kinari Devbhumi region.
Which means land of the gods.
It does, because the geography, the high peaks, the isolation, fostered a culture deeply rooted in shrines, pilgrimages, and distinct mountain deities. It's a culture of verticality.
And then you have a place called the Tribo-Hindu region.
That's the Chotnagpur Plateau. It acknowledges that this is a transition zone. It's where the tribal world of the forest meets the Hindu world of the plains. The culture there is a true hybrid.
It's amazing to think of these regions not as states on a political map, but as these living, breathing cultural ecosystems.
That is the geographer's eye.
All right, we've covered the who and the where.
Yeah.
Now we need to look at the how many. Demographics.
Ah, the numbers. They tell the story of India's modernization. And the source breaks it down into 4 distinct phases of growth.
Okay, phase 1, 1891 to 1921.
This is the period of stagnant population.
Stagnant. I always thought India had a huge and growing population.
Well, it was huge, but it wasn't really growing. The birth rates were incredibly high, yes, but the death rates were just catastrophic. Famines were common. Epidemics swept through cholera, plague, and of course the devastating 1918 flu.
So high birth rate canceled out by high death rate.
Exactly. The population barely inched forward because so many people were dying young.
Then comes the year 1921. The source calls it the year of demographic divide.
It is the absolute turning point. After 1921, India never saw a decadal decline in population again. We enter phase 2, steady growth. The death rate started to drop, mainly due to better transport of food, which prevented localized famines and some basic control over epidemics.
And then comes phase 3, 1951 to 1981. This is the population explosion.
This is the one everyone talks about. Independence comes in 47. Health services improve dramatically. Antibiotics, vaccines, better sanitation. The death rate plummets. But, and this is the crucial part, the birth rate stays high.
Why did it stay so high?
Cultural inertia. People were used to having large families because, for centuries, many of their children simply wouldn't survive to adulthood. So even as survival rates improved, the habit of having large families continued for a few decades.
And that gap between the low death rate and the high birth rate
Caused the population to skyrocket.
And what about now? Phase 4.
Post-1981, we are in the phase of slowing down. The growth rate is declining. The fertility rate is dropping quite significantly.
But the total number of people is still going up.
Yes, and that's because of demographic momentum. We have a massive base of young people from that explosion phase. So even if they each have fewer kids, there are just so many of them having kids that the total number keeps rising. But the rate of growth is definitely slowing.
The source highlights a massive north-south divide in these numbers, though.
This is absolutely critical for understanding modern India. The southern states, Kerala, Tamil Nadu, have effectively stabilized their populations. They have hit or are below replacement levels of fertility.
And why the south?
In a word, development. The source explicitly links this to female literacy and standard of living. Kerala has very high literacy, especially among women, and when women are educated and empowered, birth rates drop. It's a universal demographic rule.
Meanwhile, the north.
The so-called Hindi belt, Uttar Pradesh, Bihar, Rajasthan, still lags behind. Lower literacy, lower socioeconomic indices, and as a result, higher birth rates. The demographic future of India is currently being written in the north.
So we have this incredible layered picture, a country that acts as a museum of races. Tribes tucked away in the hills with these surprisingly progressive social norms, a caste system that organized the entire economy of the plains, and a demographic shift that's moving at different speeds in different regions.
It connects right back to that salad bowl versus melting pot idea.
Explain that for us.
Well, a melting pot implies everything blends together into one, indistinguishable goo. India is much more like a salad bowl. The tomato is still a tomato. The lettuce is still lettuce. The different races, tribes, and religions live side by side. They interact, but they maintain their distinct flavors.
Because of the geographical niches they occupy.
Exactly. The hills protected the differences. The plains connected them, but through a very structured system.
But I have to wonder, and I guess this brings us to our final thought for you to take away.
What's that?
The geography is changing. Not the mountains themselves, of course, but the barriers they represent. We have roads cutting through the tribal belts now. We have the internet reaching the high Himalayas. We have millions of people migrating from their villages to the cities, leaving that Jajmani system behind for corporate jobs.
That is the big question, isn't it?
As all this modernization accelerates, will the geographical logic we've been talking about today finally break down? Will the distinct lines on the map between tribe and caste, between Dravidian and Aryan, will they finally blur into some new, unrecognizable mix?
Or the opposite.
Or will the rise of political identity, like the demand for separate tribal states that the source mentions, will that actually reinforce these ancient lines, creating new borders in our minds even as the physical ones start to disappear?
It's a tension between the map of the past and the politics of the future.
Something to think about next time you look at a map of India. It's not just land, it's a living history. Thanks for listening to this deep dive.
It was a pleasure. Stay curious.